Good morning. Let me start the first conference. I'm Jiří Mareš and I will be chairman of this session. And we will have three talks, three welcome addresses. The first one will be given by the oldest member of the local organizing committee. The second one will be given by the vice director of the Nuclear Physics Institute in Řeš, Mrs. Macková, Professor Macková. And the third one will be given by the Dean of the Faculty of Nuclear Sciences and Physical Engineering of the Czech Technical University in Prague, Professor Václav Čuva. So, the first speaker is me. So, dear colleagues and friends, welcome to Prague, to my hometown. So, looking around, I should admit that I'm deeply touched by a number of people in the audience, because I haven't seen so many physicists at one spot for 2.5 years. So, welcome on behalf of the hosts of the conference, Nuclear Physics Institute in Řeš, and the Faculty of Nuclear Sciences and Physical Engineering of the Czech Technical University in Prague. And also on behalf of the local organizing committee of the 14th International Conference on Hypernuclear and Strange Particle Physics, HYPE 2022, held in Prague this week. Originally, we planned to have this meeting in October 2021, a few months ago, but we had to step back to a strong enemy, COVID-19. And few months later, the situation has not improved much. As you see, we still have COVID-19 around, and moreover, we have some political situation which enabled a lot of our colleagues to come here. At some moment, we did not believe that we will succeed to attract so many participants to Prague. So thank you very much for staying with us and for coming here. I have some notes here, but as you see, it's almost useless, but because I can't read it. We have more than 100 on-site participants, plus above 50 participants, virtual or remote. Our colleagues who could not come due to severe restrictions in their home institutions and countries. In fact, this year is not too bad in view of certain symbolism, because the first hypernucleus was found or observed on September 19 in the year 1952. This means 70 years ago. And the first hypernuclear conference in Heidelberg took place in June 20 to 24th, 1982, this means 40 years ago. So we have at least 2 anniversaries this year. And I am happy to see here many good old friends and colleagues, but I am impressed also by the number of young people in the audience. This is a very good signal for our field of physics. This means that nuclear and hypernuclear physics is still attractive to the younger generation in spite of its age of 70 years. Being less than a decade younger, I would call it a miracle. I am not willing to bring oaths to Athens, so I will not talk about Prague, its beauties, and describe exceptional sites in Prague. But let me say a few words about the venue of this conference. Ora Hotel Pyramida is just at the edge of historical Prague. You can see its ramparts about 300 meters to the west from here, and within distance of 1 kilometer, you can find many places important to our history and to my story. Approximately 300 meters east is Strahov Monastery with its precious collection of arts and famous Baroque library. And just next door used to be a palace where Tycho Brahe and Johannes Kepler lived together more than 400 years ago. And if you continue and go farther, in 10 minutes you will get to Prague Castle or to Malastrana and Charles Bridge. And in the opposite direction, about 1 kilometer from here, you will find the oldest men's monastery in the Central Europe, Břevnov Monastery, which was established in the year 993. And just next to this monastery, some 966 years later, I was born and I spent my childhood. And another kilometer to the west, there is a Bílá Hora, the place where one of the first battles of 30-year war started. And at that time, within 90 minutes, it was decided that our country of Jan Hus and Protestants, will become Catholic country. But this is end of history and my story, detour, and I will go back to conference, to physics. Though we have not seen each other in person for many months, our research has continued and have not stopped. And experimental and theoretical research during this period has brought many interesting and important results that filled several missing stones in the mosaic of our knowledge, or maybe better to say ignorance of physics and nature in general. And I'm really looking forward to hear reports on current scientific achievements at this conference. Now, a few organizational words. I would like to introduce the members of the local organizing committee. Petr Bijovský, please stand up. Then Jaro Bielčík, he's not probably here. Jana Bielčíková, I did not see her as well. But I see Aleš Čeplý is here. Not yet, very good. So you see how large is our local organizing committee. Then Daniel Gazda is here, definitely, I saw him. Thank you, Daniel, for coming. Jarka Obertová, and Boris Tomášik, and Pavel Tlustý. So if you have some problems, contact me, contact secretaries, but you can also contact my colleagues, which you have seen just a few minutes ago or a few seconds ago. We should express our thanks for generous support also to our sponsors, both hosting institutions, Nuclear Physics Institute and Faculty of Nuclear Sciences and Physical Engineering of the Czech Technical University, then the programs TEA Strong 2020, the program CAS, CERN CZ, BNL CZ, and FAIR CZ. More practical announcements. Fresh information, including changes of the program, will be available in the lobby in front of the conference hall. Then accompanying persons and you, of course, are cordially invited to join us at the welcome party today at 19 or 7 o'clock. At the poster session tomorrow, which there will be some small refreshment, and public lecture tomorrow, then concert of chamber music and conference dinner on Thursday. And if you, participants or accompanying person, needs help, advice, please contact conference secretary or directly me, as I said. Contact us even if you have complaints. We will do our best to make your stay in Prague pleasant. And finally, I wish you a fruitful and pleasant stay at the HIP 2022 in Prague. Thank you. So being a chairman, I must tell you there will be no questions now. And I will give the floor to the first representative of the hosting institutions, namely Anna Macková from the Nuclear Physics Institute in Řeš. Please, Anna, take your floor.
So I would like to thanks a lot to Jirka Mareš, who is my very good friend and respectable scientist working really long time in our institute, as well as local committee members are good friends, and I know them for a long time. So, ladies and gentlemen, dear scientific colleagues, it's an honor and privilege to be here at the opening on the 14th International Conference on Hypernuclear and Strange Particle Physics, which is held in this charming place. This renowned and globally recognized international conference is the next in a series that started in Heidelberg, as it was mentioned by Jirka, in 1982. And this conference is organized by Nuclear Physics Institute of the Czech Academy of Sciences and Faculty of Nuclear Sciences and Physical Engineering of the Czech Technical University in Prague. So I am really impressed by the list of invited speakers and the program, and I am very proud that our institute can serve to the scientific community by organizing such a well-recognized event. Both organizing institutions are leading institutions in nuclear physics in the Czech Republic, serving nuclear physicists and the whole scientific community with unique instrumentation, erudition, expertise in a strong synergy. So on behalf of our institute, I would like to mention that our institute realizes research in properties of nuclear matter under the heavy ion collisions at high and intermediate energies, nuclear reactions important for astrophysics or nuclear energetics as well. The nuclear theory is oriented to nuclear structure, hypernuclei, interaction of elementary particles with nuclei, mesonic degrees of freedom in nuclei, and so on. A large complex of nuclear analytical methods based on charged particles and neutrons are also used in interdisciplinary research in collaboration with international and national institutions and with external specialists in chemistry, biology, dosimetry, ecology, medicine, archaeology, and much more. So the research and development of pharmaceuticals is performed as well in our institute. So in general, our institute offers a broad portfolio of nuclear instrumentation, technology, as well as high scientific competencies which are shared in European networks with leading institutions in the field via transnational access, supported by Horizon project, funding, and other European structural supports. We also, as you see here, take a part in world-leading experiments in CERN, FAIR, Spiral 2, BNL, ESS Scandinavia, and much more. So let me welcome you cordially in Prague, ancient heart of Europe, one of the most attractive and visited cities. It offers visitors really breathtaking historical atmosphere, presenting architecture masterpieces ranging from Roman era basilica to the Art Nouveau, functionalist and cubic houses of the 20th century. So in the end, let me wish fruitful, nice, pleasant event, successful event, and pleasant time in Prague. Thank you very much.
Thank you, Anna. I don't expect questions, but I allow you to ask if you wish. Okay, let's ask the second speaker or third speaker for welcome address, the Dean of the Faculty, Václav Čuba, please.
Good morning, ladies and gentlemen. It's great to see the conference hall full of scientists. I used the opportunity of sitting at this elevated place and counted. And there is about 70 of us present, which is great. Because the sad truth is that COVID pandemic may have given us the opportunity of finishing some papers we never did before, maybe set up some new experiments. But you cannot really do science without personal contact, without the discussions and brainstormings, because this is the only way how to spark new ideas, especially in physics. because out of all natural sciences, there are only few as demanding, as challenging, sometimes expensive, and at the same time fun as strange particle physics. So as a representative of one of the host institutions, Faculty of Nuclear Sciences and Physical Engineering, I am really happy to see all of you here. I wish you a successful conference. I wish you a pleasant stay, and please keep on pushing the boundaries of human knowledge. Thank you.
So I close the opening session, and I suggest about 5 minutes break now, and we will ask speakers of the first session to prepare their talks and prepare themselves, and I will ask also the chairperson, Laura Fabbietti, who will be chairing the first session, to take floor here, but few minutes, please. 5 minutes. In 5 minutes, we will meet here. Thank you.
I'm Laura Fabietti from the Technische Universität Munich, and it's a pleasure to be here in Prague. And it's a great honor to open the scientific session of this conference. HYPE is for sure my favorite conference. It's the conference where I feel at home, so I'm very glad to be here. But mostly I am glad and looking forward to the talk by Professor Àngels Ramos from Barcelona. Actually, I don't know where she found the courage to accept the challenge for these very challenging talks, which will give us, right, a revision of everything which happened between HYPE 2018 and HYPE 2022, which is 4 years of time where we had a lot of time to write a lot of papers. So, Àngels, thanks a lot. Thanks a lot for taking this challenge, and we are looking forward to listen to your talk. By the way, Àngels will talk for 30 minutes, and there will be no questions after her talk because we want to give her the full time to express herself. So please, Àngels, go ahead.
Okay. Thank you. Thank you very much for the presentation. And yes, this has been a very challenging effort, which I took with pleasure, and I learned a lot, because you will see that there is a lot of work that has been done during these 4 years. Okay, so let me start by reviewing the situation of the most basic ingredient that explains the structure of hypernuclei. And this is the elementary hyperon-nucleon and hyperon-hyperon interactions. As you know, because hyperons are short-lived particles, it's very difficult to make experiments, scattering experiments with them, and there is just a bunch of data, 35 data points, which are the points that are used by the interactions, the model builders, to build the interactions. And here you can see these data points in this, well, it's all over the place, but here we see how the model, the mesonet shift model fits the data, or models that are based on effective field theory. Okay, so let's move forward, and the information on the elementary interaction has really felt a boost, or has really experienced a boost because of these femtoscopy studies that are bringing new information on these interactions. And there has been a lot of activity by the ALICE collaboration and LHC. As you can see here, this collaboration is able to, they have been able to, by measuring the correlations of pairs of particles, they have been able to give us information on the proton-proton interaction, proton-lambda, lambda-lambda interaction, proton and cascade interaction here, etc. Okay? So by analyzing this data with different interaction models, you can learn about the characteristics of these interactions. Okay? And as you can see, for instance, there have been studies that have shown that the different interaction models can give you different predictions for these correlations. So by analyzing the correlations measured by ALICE at LHC, you can learn about these interactions. Okay, so there has been also some advances at JPARC by the JPARC E40 collaboration. They obtained differential cross-sections for sigma minus proton, and these differential cross-sections have already been tested against the interaction models, okay? Also, there are differential cross-sections for the elastic scattering, sigma minus proton, for the inelastic scattering, sigma minus proton to lambda neutron, or for the elastic scattering of sigma plus proton, okay? At CLASS, there has been some data also on lambda proton elastic scattering cross-sections at very high energies. And you can see here how the lower, well, the intermediate momentum region and the large momentum regions more or less they are joined together, these two regions, and also how several models that are in the market can more or less or not. I mean, all these models have to be refitted to the new data. Okay, so Another avenue that has been followed for the last year is the progress that has been done in lattice QCD simulations. In these calculations are essentially take the QCD Lagrangian built from quarks and gluons, which are the elementary blocks of the strong interactions. And from these elementary blocks, they derive the baryon-baryon interaction in all the strangeness sectors. So these calculations can give information, especially on the channels which the experiments are difficult to be performed, like in the higher strangeness part, okay? So there has been essentially two groups working on this lattice QCD. This is the whole QCD. So in these groups, okay? The whole QCD collaboration, essentially what they do is to derive potentials from the simulations. They derive potential that they can use in Schrodinger equations to derive phase shifts, etc., of the scattering of two baryons, okay, for the scattering of two baryons. There are also the results by Mark Illa and collaborations from the NP lattice QCD collaboration, and in this they obtain here, for instance, the energies for different sizes of the lattice, and these energies are then extrapolated to the infinite volume by the Lucier method. Interestingly, here I want to point out that there is a channel, the sigma nucleon channel in the triplet channel of the sigma nucleon interaction, in which these simulations, they see that there is some repulsion here. So by extrapolating this data to the infinite volume limit using Lucier method, they can obtain some results that would be here for the pion mass that is being used in the simulation, and interpolating that also to the pion mass, or extrapolating to the pion mass with different methods, they can obtain the binding energy of different baryon-baryon pairs as you see in the different sectors of strangeness. These two methods actually are essentially, they should give the same results, and this has been studied lately in these references here. Okay. You can also constrain the hypernuclear interactions, confronting them to hypernuclear data. And in these cases, you can take the elementary interaction that you obtain by fitting these interactions to the elastic or the femtoscopy or whatever, all these experiments. You take the very interaction, then you build up the medium effect in this interaction, so you construct your medium modified Z matrix, and with this Z matrix you perform some calculations in hypernuclei. And this has been done in this reference here, and then you see here how the separation of energy of a lambda as a function of the mass of the hypernucleus is reproduced. And here you see also the effect. The difference between the blue and the red curve is the effect of the three-body forces. If you use the effective interactions, the effective field theory interactions of the Heidenbauer et al. Group, and you put that into a nuclei, you can also see, especially for the interaction, that the next two leading order interactions, that you obtain a good reproduction of this binding energy of the lambda in several hypernuclei, in principle without the need of very strong three-body forces, because here the bands are essentially taking into account the uncertainties of the two-body interaction, okay? You can also study the mean field of the lambda in nuclear matter, in symmetric nuclear matter, and you see here that these effective field theory potentials give you that the lambda fields naturally has a potential depth of around 30 MeV, especially for the next two leading order interactions, and the sigma also feels some repulsion, which is something that it is preferred by the phenomenological model analyzing the sigma nucleus potential. So these very interactions connected through with these very interactions, you build an effective interactions, you take that to a hypernuclear or nuclear matter, and then you obtain results that are reproduce the observables, okay? And Another question is the effect of three-body forces that in some models they claim that they have to be important. Some other models don't seem so much importance of these three-body forces at the densities of normal nuclear matter densities of nuclei. And here you see how the energy, the potential of the lambda changes as a function of the density. And here at normal nuclear matter density, the red band contains also only two-body interactions. The gray band also implements the three-body force. And you see that the three-body force at normal nuclear matter density is not so strong. It doesn't give too much contribution, but it gives a stronger contribution as you increase the density. And this has consequences, as we will see when we analyze the physics of neutron stars. Okay? So, another way to check or constrain the hyperon-nucleon and hyperon-hyperon interactions is by doing ab initio no-core shell model calculations of hypernuclei. And here you have two different models. One is they are based on the use of different bases the technique is similar, but the basis that they are using is different. And these calculations are very important because they really help you in testing the very interactions that you have obtained from the scattering experiments or femtoscopy. Okay, so let's move on now to how we can test these interactions also in few-body hypernuclei. This is actually the benchmark. The few-body hypernuclei is the best benchmark for testing this interaction in order to understand also a few puzzles. The hypertriton separation energy, is it larger than before? The charge symmetry breaking in hypernuclei, which is surprisingly very large. Is there a lambda NN resonance or the lifetime of the hypertriton? These are open problems that are in this field of few-body hypernuclei, and I'm going to briefly mention each one of them in the following. For instance, the hypertriton, the binding energy of actually the separation energy of the lambda in the hypertriton that has been assumed to be of the order of 0.13 MeV, and has been challenged recently by the STAR collaboration, in which they claim that this separation energy could be as large as 0.41 MeV here, okay? And the question is whether this larger value of this separation energy can affect the models and how they reproduce the separation energies of heavier hypernuclei. A study has been made on this regard, a study in which the new value of the separation energy is used to constrain the relative weight of the singlet and triplet pieces of the lambda nucleon interaction. For instance, here you see that the effective field theory interaction that reproduced the old value of the separation energy of the lambda has these two, the singlet and the triplet scattering lengths are here, but in order to obtain a higher separation energy, you need to have a much larger singlet scattering length, as here, for instance. But you can compensate this increase of the singlet scattering length by a modification of the triplet scattering length, and even with these changes, still be able to fit the binding energies or the separation energies in other hypernuclei. So it is concluded here that an increased separation energy of the lambda in the hypertriton is compatible with a good description of light hypernuclei. And we are waiting for a new measurement at MAMI that will be coming soon, that through pion decay spectroscopy, that with statistical and systematic errors of the order of 20 keV. So this will also be an interesting experiment to confirm or refute this value for the separation energy of the lambda in the hypertriton. Let's move to the charge symmetry breaking problem. And this was already pointed out a few years ago, and it was due essentially to the very nice and precise measurement of the transition photon photon corresponding to this transition for the helium-4 lambda, and also the precise measurement of the energy of this 0 plus state in the 4 hydrogen lambda. Okay. So with this experimental information, it was established that the energy separation between the 0 plus states is about 0.233 MeV, and the energy separation of the 1 plus states is minus 0.083 MeV. There were many studies at that time. I'm just referring to the new ones, the ones that have been made in between 2018 and 2022. And for instance, there is this nice work in which they study this chiral symmetry breaking through, of course, through the mixing of the lambda sigma 0 through this mixing. That was already a mechanism that had been already established before. And they also include, apart from some mixing in the eta pi 0, also these contact terms. These contact terms are therefore fitted to these values, and they find for different cutoffs and for different model for different unknowns of the model that this breaking can be reproduced. Not only the breaking, but also this interaction is fitted to the breaking, to the binding energy of the hypertriton, and to the scattering observables. Okay. And there is the JPARC E63 experiment is going to measure, so it's going to contribute to this problem by measuring the 1 plus to 0 plus transition in hydrogen-4 lambda. Okay. Next, is there a lambda NN resonant state, and possibly also a sigma 0 neutron-neutron state? And this is an interesting question that was raised by the claim by this collaboration in 2013 that having seen this lambda NN resonant state. Okay, so there are some studies in which if this state exists, it will put severe constraints on the lambda N interaction. And these studies, for instance, this one here, so they show that if the lambda NN, so the lambda NN can exist as a resonance, okay? So it's above the threshold, but if it is fixed to exist as a bound state, the binding energy of other nuclei, other light nuclei that are here for several interactions would come too large as compared to the experimental values that are here. Okay, so probably if this exists, it seems that the preference would be something more like a resonance that as a real bound state. Okay. So, and this is there are some results that I hope we will see in this conference, in which obtained by this collaboration in JLab, that have been some enhancements in an area in which it would be compatible with the existence of this lambda NN resonance and also a pair of sigma NN states. Okay, so let's now move to the lifetime of the hypertriton. That the question is whether it's a short lifetime, like the lifetime that more or less that was measured by the heavy ion collision experiments, or it's more similar to this purple line here, that is the lifetime of a free lambda. Okay, this has been going on for many years in the field, and interestingly, in 2019. The ALICE collaboration has measured a lifetime that is no longer so low, but is closer to the lifetime of a free lambda. Theoretical studies have also been done in this regard, and this is the study of 2020. Is an initial no-core shell model calculation that included together with the lambda and N, it included also sigma N admixtures, and also the effect of final state interactions for the pi minus 3 helium in the decay of the hypertriton. Okay, so it has been correlated. So it was observed that there is a correlation between the binding energy, the separation energy of the lambda in the hypertriton, and also the lifetime of the hypertriton. But shorter lifetimes are compatible with the theoretical calculations. Okay, and with the accepted hyperonuclear interactions, etc. Okay, so we are waiting for new experiments that are planned in these different, by these different collaborations, and that will bring more light into this problem. Now I move to hypernuclear spectroscopy. I must admit that maybe there has not been a lot of activity here because this activity on hypernuclear spectroscopy was made already many years ago. And I want to mention here essentially one of these calculations in which these are distorted plane wave impulse approximation of several reactions, K minus, pi plus, K plus, gamma, K plus. And these type of calculations are essential to guide the experiments that are trying to obtain the different energy levels of hypernuclei, okay? And it will be interesting to have more people working in this type of problem. So we are waiting, so this type of, as I said, this type of calculations will guide the experiments, and in particular I want to mention the one that has been approved at JLab. This is measuring this hypernuclear spectroscopy on potassium-40 up to potassium-48. That will also show the dependence on the interaction on the asymmetry, the charge asymmetry of the target. And also there are some plans to do supra-precision lambda hypernuclei spectroscopy at JParc with the new beam line at JParc. Okay. Now, let me move now to the strange -2 sector. And in this sector, I want to mention the observation of a new lambda-lambda hypernucleus, which is the MINU event. It is represented here by the JParc E07 collaboration, okay? And here, this event could be interpreted as the sigma minus being stuck or absorbed by oxygen-16, going to these three different possibilities for the final stage. But the analysis showed that the most probable one is the middle one, and that allowed this collaboration to obtain a double lambda binding energy of 19, or the bond energy, so the interaction between these two lambdas essentially of the order of 1.86, which is a little bit higher than the accepted value. So this brings some new interesting discussions into the field, okay? So now I want to mention about the possibility that there exist cascade minus nuclear bound states, and this has some events have been already observed by the KEK E373 and the JParc E07 experiments. Here, these are I'm going to mention there are some Coulomb-assisted cascade minus 14, 1p nuclear bound states, and these are, for instance, this is the Ibuki event, and here, so the sigma minus is trapped into a 1p cascade minus state. Not the bound state, but one that is a little bit higher. Okay. And there are also some other experiments of sigma minus nuclear bound states that are essentially these two. And here, the binding energy of the sigma minus that is derived is much larger and is compatible with this sigma minus being into a 1s minus 1s sigma into a 1s state. Okay, so there are several in these results that come from the JParc E07 collaboration. Okay, these results are bringing a lot of information on the possible state in which the cascade minus can be absorbed. Okay, so there are also some theoretical studies on this, and for instance, this study in the 2021, they show that by changing the strength of the interaction potential of the the cascade minus interaction potential with the nucleus, by changing the strength, they could see that the experimental value of the energy of this Coulomb-assisted 1p nuclear state was compatible here with a strength Here is this value here is essentially a strength that is larger than 20 MeV, which is a little bit larger than was accepted until now. Okay. I want to say that there are also calculations, essentially mean field calculations, but using, for instance, this is a relativistic mean field model. And they also implement some residual interaction, and they feed their model parameters to reproduce these Kinka and Kiso and Ibuki events, okay? And also there are some calculations. In this case, it's not relativistic mean field, it's just a mean field by using a Sturm-Hartree-Fock type of calculations. Again, and these calculations are constrained to these new observations, okay? I want to mention that this type of calculations, the potential of the cascade minus in the center of the nucleus is not so strong. It's more moderate and of the order of 15 MeV. Okay, so now I move to lighter cascade nuclear systems, and in this I show you two calculations in which they claim it is a I mean, the light systems are very interesting because you take an interaction, a bare interaction, and then all the machinery of the nucleus is well known. You can use Faddeev equations, or if you have or Jakubowski or whatever, you can do calculations. So the complications of the many-body system, you can treat them, all these complications, almost exactly. Okay, and so by studying different potentials, in this case, they observe that this is results of the NNN cascade system in different isospin channels, and for two different interactions. And the two interactions are very different, but at least you can see that you find a bound state in the isospin 0 and J parity 1+. It appears to be bound. It dependent on the interaction, of course. The binding energy is very different, but at least it's quite robust. It's a quite robust result. And this result is corroborated also by other interactions in which, other calculations, sorry, in which they use other interactions, the chiral interactions, and they also find a bound state in the 1+, J parity 1+, isospin 0. Of course, this bound state is not the strongest, so they find other states in the four body system, which they may have even a stronger binding energy. So there is still some controversy on this system, so it would be interesting to measure them and also to do other calculations to check what are the differences. Okay, and now, okay, so other experiments that are planned in this strangers -2 sector is the measurement of atomic X-rays coming from the cascade, that cascade down in the creation of a cascade minus atomic systems like these ones that are planned by the J-Park E07 experiment. There are also experiments for producing light cascade nuclei here, and also planning to do some experiments of high-resolution spectroscopy of cascade hypernuclei. So this is going to be coming probably for the next HYPE conference, but I wanted to mention that here. Okay, now I move to the K-bar N and K-bar nucleus interaction. Here you have a review. You can see here the latest developments. And here I want to see that the K-bar N interaction has been studied for many years. Here the cross-section are displayed here. But the recent works, for instance, include a Lorentz invariance formulation of this chiral effective field theory at lowest order. What else? We find that this interaction has been extended to higher energies. That meant that the lowest order and next to leading order parameters have been fitted by these two groups. What else? They have higher partial waves have also been implemented in this reference, etc. Okay, so there is a lot of theoretical activity, maybe not so let's say, a little bit more moderate now because this was already a long time ago. That was a more interesting subject. And, but experimentally, what we have is this cross-section data here, but there has been some new experiments or new results. For instance, the use of the low energy kaons of Daphne has produced some new results by the Amadeus collaboration. Okay, for instance, this is the amplitude in isospin 1 for the K- neutron going to pi minus sigma, and also the measurement of some very recent measurement of some low energy cross-section of K minus P going to pi 0 lambda or pi 0 sigma 0 at very low momentum of the kaons, which is the key point of the kaons produced at Daphne, okay? And this is bringing 2 more points in these plots, 2 more points here, and these points have to be now fitted by new K-bar N interactions that have to really reproduce these points, okay? So there is some progress here. And now, also there is progress on the K-bar interactions. You can learn about the K-bar N interaction also from femtoscopy studies, and this has been done by Alice, collaboration at HCB, and here you see some results for the K minus P interaction in proton-proton collisions, and here you can see also results of the K minus proton interaction in lead-lead collisions. Okay, so let me just skip. So there are some also theoretical calculations about that, and interestingly is that from these interactions, you can really, from these experiments, you can obtain the scattering length of the K minus proton, and this has been done, and this is the result of the Alice collaboration. The error bars are still large, but I just want to mention that it's feasible to obtain the scattering length from the femtoscopy studies, and these values are close to the Siddhartha value obtained from the study of kaonic atoms. Kaonic atoms, they are very important kaonic atoms, especially I want to mention here the measurement of the K minus deuteron, X-ray of the K minus kaonic deuteron, kaonic deuterium, ground state that has been planned in Siddhartha 2, and as they are now taking data. So much is expected about these experiments to learn about the K minus neutron interaction. We have information on the K minus proton from scattering experiments, and now we want to know about the K minus neutron interaction. Okay. So, okay, some connection of heavy kaonic atoms with the kaonic deuterium here. I just don't have the time to mention that. There is some also studies on absorption of K minus by the Amadeus collaboration, and some theoretical studies that reproduce these results. There is also, again, the studies or experimental reanalysis for the K minus PP bound state, and the future also. In the future, they are planning to look for a K minus proton neutron or heavier clusters of kaons in light nuclei, and some studies have been done about that too. Okay, so now I should move to strangers in matter and neutron stars. I don't have really time for that. I just want to mention that, and Isaac Vidaña will talk about that in his talk, that the fact that you implement hyperons in your equation of state makes the mass of the stars to go down. So this is the hyperon puzzle, because hyperons are going to appear in the neutron stars, but then they reduce the maximum mass. I just want to mention that depending on the models, because the relativistic mean field models, you can play with the parameters, and then you can have hyperons and still reproduce a maximum mass of two solar masses. But I want to just comment that the connection between the three-body force that I mentioned before and this maximum mass of the neutron stars. If you, in this work, you can see how, in order for the hyperon to appear in a neutron star, the lambda chemical potential has to meet the neutron chemical potential. In a two-body calculation, that would be this dashed line. You would have hyperons in your neutron star. But if you implement three-body forces, it could be that because of the hyperon-nucleon-nucleon three-body force, the chemical potential of the lambda never meets the chemical potential of the neutron, then hyperons are not present, and then the equation of state does not soften, and then the mass of the neutron star stays large. Okay. So now I think I'm going to say anything about the hyperons at finite temperature. We will hear that in several talks in this conference, and also the medium properties of the particles can be studied in heavy ion collisions, like it has been done at Hades. And exotic hadrons, I think I have to finish here. But thank you very much
So,
for your...
thanks a lot, Angels. Anyway, your slides are online, and
You will see my
we
slides,
have.
yeah.
Thanks a lot. We really got
Thank you.
a flavor for what is happening this week, and thanks a lot for all your effort, Ran. So thanks again. So, I think now we are all set up to start, let's say, the single report, and it's a pleasure to have the first experimental talk by Simon Spiess from the HADES collaboration. Simon will talk about the results connected to the physics of hypernuclei, but also nuclei, right, and strange and in general from the HADES collaboration. You have 20 minutes, I give you 5.
Mm-hmm. Yeah, could I get my slides, please? Okay. Yeah, thank you very much. It is really a pleasure for me to be here. I'd like to thank also the organizers very much that I get the chance to present our results here from HADES, especially now with the focus on our heavy ion collisions we measure at HADES. There will also be talks on this conference to the elementary reactions which are measured. So let me start with a short introduction to the physics which we are doing with heavy ion collisions. So if we're talking about heavy ion collisions, usual question is where we are located in the phase diagram of strongly interacting matter. And now with HADES at this 18 accelerator at GSI, we are in the regime of few GeV collision energies per nucleon. And this for us as a result means that we are located at the high barrier chemical potential region at intermediate temperatures here. Yeah, down here at this tail, if compared, for example, to the higher energies at, for example, LHC or RIC maximum energies up here, where the biochemical potential is fading and temperatures come to a maximum. And what is really good to see here is that basically all currently running heavy ion collision experiments connect the region between, so almost the entire phase diagram is now explored. And at HADES, we are also aiming to extend this coverage here down to the even lower temperature and higher biochemical potential edge, which is a proposal for us by doing a beam energy scan below this 1 GeV energy. And why is this of importance for us? Simply because there are several models which predict that in merging neutron stars we create similar matter. And yeah, thereby can learn something about the relevant equation of state when we study these reactions. Now, the high biochemical potential in this region, of course, means for us that we are baryon dominated, and this can be seen in the rates of baryons to pions. So we are dominated by baryons. We have significantly more than mesons in contrast to high energies where we are meson dominated. And also another result of these high biochemical potential is that we have a lot of light nuclei, which is shown here in this energy excitation of helium-3 to proton, where one can see that it's steeply rising towards the low energies. So light nuclei are of great importance for us with this hardest point here, which is this black one. And yeah, now if we want to come to hypernuclei, of course we need another ingredient, so to say. We have the light nuclei already, but we also need strangeness or hyperons. And hyperons are rather limited at our energies simply because we have a production threshold for strangeness, and this is shown here in this reaction channels for the production of strangeness in free nucleon-nucleon collisions. And yeah, here are the threshold energies, and one can see to produce a hyperon we need in this isolated nucleon-nucleon collisions at least 2.55 GeV, which is exactly the energy we are measuring at, so our amount of hyperons is rather limited. This is also shown here on the right hand side, on the right plot, where we have energy excitation functions of lambda hyperons in case we are short mesons. Yeah, and here these circle points are the measurements by HADES in our 2 heavy ion beam times, gold-gold and silver-silver collisions. And yeah, one can see that we perfectly connect to the remaining available world data. In case of the lambdas, and in case of the KZO shorts, unfortunately, this energy region at few GeV is almost unexplored, and yeah, we are really looking forward to physics in this region, where also KZO short mesons will be measured, like for example at the upcoming ZIS-100 accelerator at FAIR. Now, as we have hyperons and light nuclei, of course we can bind them, we can form hypernuclei. And as we already learned in the previous talk, these hypernuclei are of great importance because from their properties one can deduce information on these hyperonucleon interactions, which are relevant for the stability of neutron stars. So to come to a short introduction to the HARDES experiment, this is an expanded view of our detector. And the main important information about this experiment is that we are a compact magnet spectrometer with these drift chambers, which are optimized for a low material budget. 2 are located in front of the magnetic field, 2 are located behind our magnetic field, and then finally we have our time of flight walls to measure velocities of particles. Yeah, and in total, this setup leads to a really large geometric acceptance with almost a full azimuthal angle and a large region of the polar angles being covered. Now, particle measurement at HARDES as a magnet spectrometer is usually done by the correlation between measured momentum versus the velocity of the particles. This is shown here in this plot on the right-hand side, which is from our silver beam time. And here one can again clearly see that we are baryon dominated. So we have here this region where protons and light nuclei are located, and they are significantly more abundant than here, the region where the pions and especially the kaons are located. So in this talk, I will present data both from our measurement gold-gold at 1.23 AGV. I will mark them with this green color, and I will also present data from our more recent silver-silver measurement at 1.58 GeV. This will be marked red. Yeah. Then to come to the measurement of single-charged particles, like for example protons or light nuclei. Yeah, the identification, of course, as I presented previously, is done by the momentum versus velocity correlations. This is the same for protons and light nuclei. For light nuclei, one has to take in addition to account that, for example, the deuteron and the helium-4 have the same mass over charge ratio. So they have to be separated in our experiment using specific energy loss in our drift chambers. Now, unfortunately, I have no results on the light nuclei to present today because they are still under investigation, but the protons I can already show. So here on the left-hand side, I've shown you the mid-rapidity transverse momentum distribution of the protons, which we're reconstructing from our silver beam time. And in the center, I show you the transverse momentum spectra for various rapidity intervals. And here one can already clearly see the strength of the HARDES experiment, which is this really huge acceptance. So we are basically able to measure from here protons in really backward rapidity direction, which are almost at rest in our laboratory system, up to here in forward direction, where the protons have high momenta in the laboratory system. And yeah, this is only possible due to our experimental setup, which covers all of these regions. On the right-hand side, I'm showing you the integrated rapidity distributions of protons, and again for 3 different centrality classes. And here one can see that at the most central collisions, we see an almost isotropic emission of protons around mid-rapidity. And then in the more peripheral centrality classes, one sees this deviation from that, which is due to the stopping of the nucleons in the collision zone, which simply ceases. And if I draw here the target and projectile rapidity, then one can see that we can cover with the experiment almost the entire region between target and projectile rapidity, unlike, for example, at LHC experiments where target and projectile rapidity are far away from the region which is accessible in measurements. Yeah, now to come to weak decays. By weak decays, of course, if we talking about hadrons containing strangeness, then the strangeness has to decay via the weak interaction. So almost every strange hadron which we are measuring is a weak decay. And With weak decays at our energies, we have the problem that our signals are just very rare. As I showed you in the beginning, on the energy excitation function, we are in this region where it is still steeply rising. So we can only expect to have strangeness in maybe 1 out of 10 of our most central events. And this means if we, for example, look at lambda decaying to a proton and a pi minus, then the actual signal is, of course, like in every 10th event, but protons and pi minus we have a lot, so we get a significant amount of combinatorial background, about a factor of 10,000 above the signals. And this is why we need a strong method to separate between the combinatorial background and the signals, and this is done via this off-vertex topology, which is simply a result from the long lifetime of these strange hadrons, and then develops these off-vertex decay topology parameters, which are shown here in purple for K0 short signals and in black for the combinatorial background. Now, at our energies, this is not enough because of this strong excess of the combinatorial background. In addition, we need to use an artificial neural network, which is trained on these distributions which I showed you in the beginning, and only with the additional separation power of this neural network, we are able to extract very pure signals. Now, to show you the reconstruction and the analysis of the lambda hyperons, here on the left side, I've shown you the invariant mass distribution, which is obtained after the selection method has been applied. And in the center, again, I'm showing the transverse momentum distributions of lambda hyperons for various rapidity intervals. And again, one can see that we have a really large phase space coverage with our hardest detector, even for these decaying particles. Now, our aim is to do lifetime measurements also for the hypernuclei, so we need some sort of test case to assess that our method which we are applying is actually working, and this test case are the lambdas. And if you remember my talk from the quark matter, then you might remember that we had some problems with the measurement of the lifetime of lambda hyperons. Fortunately, we were able to solve this in between. And with the corrected method, we can now actually measure a lifetime of lambda hyperons of 262 picoseconds, which is within errors exactly compatible with the PDG value. So we get out the exact correct lifetime of lambda hyperons. Now, also to show you the same for the K0 short mesons, again, we can see a clear significant signal in this pi plus, pi minus invariant mass spectrum. And what is here very special is if you look at the mid-rapidity transverse momentum distribution, then you can see we can measure here down to transverse momentum of 0 at mid-rapidity, and those are K0 short, which are even almost resting in the CMS system of the collision. So we can almost measure all K0 short mesons which are emitted from our fireball. And this is, of course, a great basis to perform later physics deductions on these data. Now, we also do a lifetime measurement of the K0 short mesons also to test this method. Here we get out 92 plus minus 1 picoseconds, so this is also in agreement with the PDG value, so also good result. Now to finally come to the hypernuclei, I start with a very short review of the properties of hypernuclei, because what I mainly want to show you here is that there are several decay channels for hypernuclei. For the hypertriton, at hardest we are currently measuring this two-body decay channel into helium-3 and pi minus, but there's also this three-body decay channel which we also attempt to measure, but unfortunately could not do yet. For the hyperhydrogen-4, there's a similar picture. We have this two-body decay channel and this three-body decay channel, but at the moment we are only measuring the two-body decay channel. Yeah, the reconstruction is done very similar to the reconstruction of lambda hyperons and K0 short mesons. And here I'm showing you the invariant mass spectra of in our silver beam time for the hypertriton on the left picture and for the hyperhydrogen-4 in the right picture. And you can see that we are able to extract very clear signals in this invariant mass spectra of the two-body decay channels. The three-body decay channel is more challenging for us because the additional particles significantly increases the combinatorial background, which of course is very problematic for us, but we are working on a procedure to be able to access this also. Now, one thing which is new, which I want to show you, is the measurement of hypernuclei from our gold-gold collisions, because we attempted this before, but unfortunately could not figure out a way to how to do this. But after we had this success with our silver-silver data, we reinvestigated our gold-gold data with this improved reconstruction method, and we are even able to reconstruct a slight hypertriton signal in our gold-gold collisions, which is shown here in the left, and a quite significant hyperhydrogen 4 signal, which is here shown on the right. And yeah, the very special thing about this is that never before hypernuclei were measured at lower energies in heavy ion collisions. So this was never possible. This is the very first measurement of that. And here, in case of the hyperhydrogen 4, the signals are even enough to perform a differential analysis. In silver-silver collisions, of course, we have enough statistics to perform differential analysis, so I want to present them to you here. Coming from the reconstructed hypertriton signal here on the left, we can separate it in even 4 of the rapidity intervals, which are shown here in the center, and the transverse mass spectra also shown here. And yeah, then we can integrate these spectra and thereby obtain a rapidity distribution. And this rapidity distribution is in that kind special that one can clearly see, even though the data points have rather large errors, it is very clear that we see here an emission of the hypertriton around mid-rapidity. Okay, thank you. Yeah, this does not exclude that there might be additional sources, for example, at target and projectile rapidity, but there is at least one source at mid-rapidity. Now, of course, as we heard in the previous talk, the lifetime is of great interest, especially for the hypertriton, because of the famous hypertriton lifetime puzzle. We do this measurement. Unfortunately, our measurement has rather large uncertainties. Still, if we put our measurement in context with previous measurements, like they were also shown in the previous talk, we have here this ALICE 2019 measurement, which had this lifetime, which is in accordance with the free lambda lifetime shown here in blue. And now our data also show that our lifetime is in accordance with this free lambda lifetime. However, the large uncertainties, of course, also allow for lower lifetimes here in this region between somewhere 200 and this 260 picoseconds. And we are, of course, looking forward to further data on this topic. Now, also to come for the hyperhydrogen 4, there's a similar picture, so we can again do a multi-differential analysis in 4 rapidity intervals, and we again, in the rapidity integrated spectrum, see that we have emission of the hyperhydrogen 4 around mid-rapidity. Yeah, as I already said before, it might still be possible that there are additional sources, but there's at least one source which is located at mid-rapidity. The hyperhydrogen 4 lifetime measurement is presented on this slide, and yeah, here we measure a lifetime which is significantly lower than the lifetime of free lambda hyperons. But if we compare this also to previous measurements, especially to this measurement from STAR from year 2021, which we'll most probably also hear a lot about in this conference, yeah, we can see that we are basically in perfect agreement with this measurement. And yeah, thanks to the larger statistics also, our uncertainties are significantly lower. So this, I really hope that these measurements will be confirmed then in the future by further experiments. Yeah, now to come to an interpretation of the data. So one of the very famous results from our gold-gold measurement was the observation that if we plot the yields of the strange hadron species which are produced here against the mean number of A part, then we observe a very uniform scaling with this A part to the power of 1.45 for all of these strange hadrons. And the astonishing part about that is, if we look at these threshold energies in these nucleon-nucleon production channels, then the K- and the phi, they have a significantly higher threshold than the K so short, K plus, and lambdas. However, this is not reflected in this measurement. Yeah, which somehow hints that, that initially in the collision strange anti-strange pairs are created, and then only afterwards they are distributed to the hadron species. And now in our silver-silver measurements, we were able to confirm this. So we have here still rather large systematic uncertainties for the K plus, K minus, and phi measurement. These measurements are still ongoing, so we are confident that we will be able to decrease these uncertainties. But also the currently available data show that we still observe a similar scaling for all of these hadron species, and even with a very similar slope of 1.46 in case of our silver-silver collisions. Now, something which is also new, we have done now the same analysis also for the hypernuclei, and this is shown here for the hyperhydrogen 4, which is this darker orange, and the hyperhydrogen 3, which is this lighter orange. And what is now really interesting is that the two hypernuclei species which we are measuring are scaling with a similar slope again. However, the slope is significantly larger than the slope of the remaining strange hadrons. So one could, for example, expect a hypernuclei to scale like the lambda because, of course, they contain a lambda. However, they seem to, in addition, profit from the availability of more nucleons in the more central collisions, which is a hint that maybe the hypernuclei might be produced via coalescence processes. Yeah, this already brings me to my summary. I hope I was able to show you that the HARDES experiment is capable of measuring the hyperons and strange mesons, hypernuclei in great detail. And yeah, at the moment we are heavily working on implementing a procedure to perform now comparisons of our results with nuclear transport models, and then to deduce also further information on the physics behind it. And a quick outlook for the hypernuclei measurement at GSI Fair is the SIS-100 accelerator, because if we plot this energy excitation functions of the hypertriton, which I adopted from this paper by Starr, then we can see that we have this strong rise at the low at the low collision energies due to the strong rise of the production of hyperons, and then this drop to the ceasing amount of baryons in the system. And here in this region where the SIS-100 and the CBM physics program is located, we are almost at this top. So yeah, we can expect a lot of hypernuclei measurements from SIS-100 CBM experiment in the future. Thank you very much, and also in the name of the HARDES collaboration, for your attention.
Thanks a lot for this very nice talk and for the impressive results. So, are there any questions? We have a little bit of time for questions. So, over there, Take, run there. And maybe we can put the slides back. In case.
Thank you very much for the very nice presentation. It is very interesting. So I have a question about your lifetime measurement for the hypertriton and the hydrogen for lambda. So your systematic error is larger than the statistical error. So what is the source of the systematic uncertainty? And also, how can you improve the systematic error?
Yeah, thank you very much. This is a good question. So, no, I cannot move in the slides now, but okay. Then I just have to tell it to you.
Try it again.
Now
Yeah.
it works, okay, perfect, thank you. Yeah, if we look here at this right plot where we have the decay curve of the hypertriton, then you can already see the high systematic uncertainties of these individual measurement points. And this is because we are using this artificial neural network for the reconstruction of these off-vertex decay topologies. And to have a more or less conservative approach, we wanted to deduce the systematic uncertainties based on the deviation between using the artificial neural network and not using the artificial neural network. Of course, not using the artificial neural network is very disadvantageous, because you get a significantly less amount of signals reconstructed, and of course the points start to fluctuate much more. And so the main source which drives the systematic uncertainty is at the moment this comparison to not using the artificial neural network. So I think from the lambda and K-so short measurement, we are at the moment quite confident that we do not get a problem by using the artificial neural network, so we might consider doing the systematic uncertainty estimation different in the future, and then of course the uncertainty would decrease.
Okay, Maximiliano?
Yeah, so you said from the lambda you use the same method, so you use the neural network also for the lambda?
Yeah, we use the same basic approach, but the approach is trained to the different particle.
Okay, but then it's still the neural network. So
Yeah.
in principle, you can also avoid doing this, because if the lambda comes out properly with the neural network, then this is an overestimation of your systematics.
Exactly, exactly.
It's very conservative at the moment.
Yes,
Can
at
improve.
the moment it's very conservative.
Other question or comments? Okay, other than that, thanks a lot. We move to the next speaker, whom I see approaching. So this will be Ivan Kiesel from the STAR collaboration, and we are looking forward to listen to the new results by the STAR collaboration. Can we have the slides? I will give you a notice before 5 minutes, okay?
Thank you.
Good morning. So in my presentation, I will give you results of our study of strange matter in STAR with express analysis. What is express analysis? To make such an almost online so-called express analysis, we have extended the functionality of the high-level trigger of STAR. In that way that after making the standard trigger on good events, high-level trigger will store part of data depending on the available disk space and computer resources to the disk, and then the reconstruction algorithms will read the data from the disk and then process them, making calibration, reconstruction, and physics analysis. And then the processed data will be stored in the form of so-called Pico DST for further analysis by other STAR groups. Depending on the available computer resources, as I told, and disk space, we processed on average about 30% of all BIMRSCAN2 data. And such a procedure take usually a few hours, maximum 1 day, to process all the data stored at the disk. And this type of express production analysis has been running since 2019. That means that all data taken in BIMRSCAN2 have been processed with about 30% of them, but all runs have been processed with express production and analysis. The algorithm which we have used for express analysis on high-level trigger, as well as in the STAR in general, these are algorithms for trick reconstruction and searching for short-lived particles. These algorithms were initially developed for the CBM experiment, and then within the so-called FAIR Phase 0 program, we adapted these algorithms for the STAR experiment, for STAR analysis in general, but also to test the algorithms from the point of view of the future CBM experiment. When we get first data, then we have to be sure that the algorithm will work. There are two main algorithms which we developed for CBM and using STAR. This is so-called CA track finder, full automaton-based track finder. And applying to the STAR experiment, we demonstrated that use of the CA provides about 25% more D0 and about 20% more W, just replacing or upgrading the standard reconstruction procedure, which was initially, before that, used in STAR. And also the KF particle finder, I will give more details on the next slides, provides a factor of 2 more signal particles comparing to the standard STAR approach. What is shown on the slide, that the left, this is the application of the KF particle finder to simulated data of CBM experiment, and the right, the same algorithm without any changes applied to real data of around 2016 in STAR, and we see that the signal comes immediately. Okay. In this presentation, I will focus on physics analysis, and this means that on KF particle package. KF particle package, this is the package for searching for short-lived particles, and is based on application of the Kalman filter mathematics. That means that together with the state vector, which is parameters of the particles, we use also covariance matrix, not only at the tracking stage, but also at physics analysis. That means all the information which we get during tracking, we use it further for physics analysis reconstruction of short-lived particles. To be fast, I mean, the Kalman filter is a complicated mathematics, and to be fast, the algorithms are vectorized, parallelized, et cetera, from the computer science. The algorithms, the interfaces to algorithms are relatively simple. You can see at the left, this is easy to understand. And the algorithms are kind of 3D, written in a 3D way. That means that they are geometry independent and currently are used at different level of activity at CBM, LS star, and Phoenix experiments. We also at the bottom right, we also have a part of the algorithm of the framework which is implemented, so-called missing mass method, when we have a daughter particle is neutral, not registered, not reconstructed, and detect not reconstructed, but the mother particle should be detected like sigma, pi minus, and neutron. Okay. KF particle package, this is more functionality, mathematics, etc. While for the online analysis, we have developed on the top of that so-called KF particle finder package. That means that within this algorithm, we have implemented reconstruction of almost up to 200 different decays, so that we can run the algorithm online, and all these decays will be reconstructed in one go. That means that the algorithm is relatively fast. In CBM, for central collisions, it takes 10 milliseconds per collision. And you can take this package as a template, run in your experiment. You can change, adapt the procedure for your needs. Coming to BIMRESCAN2, so express analysis. So here we show that on an example of mesons, that the calibration, reconstruction, and the analysis of mesons is very, very good. So like shown, for instance, for P0, we have 50 sigma significance at the top left. Other particles also have very good sigma to background ratio and significance. And at the right, you see also background-free identification of charge cones with by full topological reconstruction. When we have all 4 tracks reconstructed, then we can apply searching for K plus, K minus, and then we can compare what is the quality, et cetera, calibration, etc. So for us, mesons are used as probes for the full reconstruction chains. This is an example of missing mass method application. So that's, the picture is relatively clear. So the second peak, this is due to misidentification muons and pions, but all other is very good. And the missing mass method gives us many opportunities for further physics analysis and application also in hypernucleus as well. Yes, so these are hyperons. So we see all particles with high sigma to background and ratio and significance. And this is also due to upgrade of the inner part of TPC, so-called ITPC, and also improved Silver automaton track finder. This has increased the efficiency of reconstruction of these particles. And important for us also to study that we have now possibility to study in low PT region these particles. Coming to fixed target express production, BIMRESCAN2. especially at low energies, when we increase the interaction rates, we observe pile-up. And so you see at the right, this red point, this is a target. And then this yellow circle, this is a beam pipe. And then we see also this white ring, this is support structures. And at the left, at 2 centimeters, you see this structure of beam pipe, which is also shown at the bottom here at this distribution. So at this histogram, you see reconstruction of helium-4 lambda without and with special cleaning procedure which we have developed, and this increased the quality of significantly reduced background and the increased quality of reconstructed hypernuclei, especially in three body channels. What is shown here, this is analysis of hypernuclei at 3 GeV with fixed target, and in this case we had relatively high interaction rate. That means that in order to process all the data on HLT, we applied an extra additional trigger, which is requiring helium, and in order to enhance hypernuclei. So this means that what we see in 2021 data with fixed target 3 GeV, we see helium-5 lambda with significance 9 sigma. And this means that with the collected statistics, we have enough data to make analysis of yields, lifetimes, and spectra of these hypernuclei. So, in order to work further, we have processed also the data 2018, 19, and 20. 2021 fixed target, and also in collider mode at 7 GeV to have hypernuclei, and we see that helium-5 lambda we see with significance 11.6. This gives us possibility, so we have actually for H4 lambda, we have, where is it? So, helium-4 lambda, we have almost 1,000 hypernuclei. That means that we can make analysis with Dalitz plots, for instance, in this case. What is, we applied side bend method to analyze the background, which is smooth, you see at the left, at the right, and then we subtracted this background from the signal region at the middle. What we see that at the bottom we have at the top you see a complex structure in the signal which can be explained as a possible spin effect, and also at the bottom middle there is a hint on resonances to body lithium-4. When we make projections, the same is visible at the bottom, center at the bottom. You see that background is different behavior of background and the signal. So we still see the same hints. For helium-5 lambda, similar behavior, similar structure as helium-4 lambda with lithium-5. The same for projections. So here we have only 190 signal hypernuclei or events, so we need more statistics to make more precise analysis. This is for H3 lambda. With offline production, we expect higher statistics. This is 3 body channels. And in our case of the express production, this channel was suppressed because of the helium trigger. The same for projections. And coming to binding energies, so we observed that binding energy is increasing up to helium-5 lambda. And when comparing binding energies per nucleon for different nuclei and hypernuclei, so we observed that hypernuclei, they behave similar. The statistical errors are smaller than the markers, so relatively small. And binding energy, our conclusion or assumption currently, this is the binding energy of hypernuclei together with hints on the two-body resonance decays can be an indication that lambda behaves similarly to other nucleons, neutrons, protons in hypernuclei. And coming to the summary, so in the express production data stream, we see all signals starting from mesons and up to hypernuclei using a particle finder on high-level trigger. And we observe helium-5 with significance of 11.6 sigma. Dalitz plots of three-body hypernuclei channels show complex structure, which possibly is a spin effect. Hints that significant part of three-body decays happen via nuclear resonances. Hypernuclei binding energy per nucleon is increasing with A up to helium-5 lambda. There are indications that lambda behaves similar to other nucleons, neutrons, and protons in hypernuclei, and decay models are needed for efficiency estimation of three-body channels and branching ratios. Thank you.
Thanks a lot, Ivan. Really impressive. So, questions or comments? While people warm up, I will start with a question. So, you mentioned the evidence of a decay into lithium pion. Maybe you can, I didn't quite grasp how you evidenced that. It was on a Dalitz plot. Maybe can you repeat that?
Yes, so
Yeah,
what we see here, that one of the possible explanations is that, so what is shown here, that one of the possible decays of helium-4 lambda is through lithium-4 resonance.
I see, true. I see, because you see the resonance, so if you project over x-axis, I see.
Yes.
This I see here, because, okay, wow.
This is one of the possible explanations.
Explanations, I see.
Or assumption.
Here there is a question.
Yeah, and just to comment about this three-body decay, actually you are showing that the three-body decay is actually a two-chain, two-body decay. That you have the first, the pion emissions, and the second decay from the resonances.
One of possible kind of.
And this actually have been already seen in the three-body study in the previous experiments.
Okay.
So actually this proves it again.
Okay, thank you for the comment. Sure, it has already been seen, but this, I mean, what it shows is that it opens up the possibility of looking this differentially for many nuclei. So Avram, there.
So for further analysis, we need the standard production first, and then some theoretical models to apply and to have more checks.
Of course, when you go to lambda helium-5 in particular, the importance of non-mesonic decays becomes increasingly important. So without pi minus, can you say something about trying to determine those things which are very interesting theoretically, the non-mesonic decays?
So what this was, we have only limited analysis during the online this express production. So the full analysis we will do just after the final calibration standard production. This is what I can say.
Okay. Horst? There? Yeah, yes.
You have been mentioning the decay through resonances. Can you elaborate a bit more on that topic? I think that is a very interesting issue.
Yes, we have to do the final calibration and production, and then we will do the more precise analysis. Currently, this is what we have now. Otherwise, what I can say, this will be just our hypothesis, not more. So this is the last our numerical results, how to say. So for other hypotheses, we have to check many things, especially as I told you that there is a pile-up here, so we have to be a little bit more accurate working with this 3GeV fixed target data. So we just move pile-up at this level to see much more clear signal, but effect of the pile-up should be also kind of investigated.
But you can't say yet which type of resonances are that. Okay, so that's left to further.
I think we
work.
have to wait a bit.
Yes, we have to wait,
But the
otherwise,
data are there and the answer will come.
Not
so.
just speculating, I'm sorry.
Okay, other questions or comment? Okay, if not, thanks a lot for this really great result. And then we will enjoy the coffee break and we reconvene at 11. But Jirji, you want to say something?
Sorry, we still have some time, so I have a few announcements to you. First one is there is a list of participants at the reception desk, and not everybody signed there, so please do it because our providers of support needs this list of participants. So please go there and sign during the coffee break, for instance, or during the lunchtime. Then, as for public lecture, you probably notice that there is a message that it's free online registration. So I ask you to register because it's good, again, for organizers to know how many people we can count with, because there will be some reception, some refreshment. Thank you. And okay, and last message. What speakers see here, they can see it also here. And not always you point there. You are staying this way, and there is a camera. There is a camera. This white instrument is a camera. So online participants see you from this side or this side, but not that side. So this is for the other speakers to this conference. Thank you very much. And so now we have coffee break for more than half an hour, but you haven't seen each other for a long time, so I think you have a lot of time to speak with others. So we will meet at 11 o'clock here.
Yeah, wow. Three-dimensional faces again. Huh? At last. Okay, welcome to the second session of this conference. In this session, we will have talks on the A=3 system. We have heard about that before. And we will start with two online presentations. The first by Yu Ma from RIKEN and from JParc, and he will talk on this new planned experiment, JParc E73. So please start your talk. You have 20 minutes, so 15 plus 5.
now the problem is how to implement this experiment. As you can see that I0 as the final product behaves to gamma response in media. So this I0 is not experiment friendly at all. So our solution to this challenge is to employ a treat, so-called gamma repackaging method, as you will see details in the next slide. So if we look at the I0 decaying dynamics, we will realize immediately that even though the scattering of I0 should not decay back to that, but if the I0 is supposed to 3, sigma 0, positive 3, sigma minus corresponds to distribution right here. And what we have done to achieve such a good simulation is to combine the Avalanche reaction from the published data for this K minus pi 0 reactions together with modern low function calculations as kind of input for Fermi motion. Combine these two information together, we see a very good agreement has been achieved without any remaining puzzles. And we also confirm that not only for the random distribution but also for time distribution, both the data and one-column simulation achieve very good consistency. And this further enhances our confidence for the future data analysis for our trial case. We have reported this results about, half year ago in the GPARC Hack Committee in order to convince them to give us the green light for a second stage, so-called physics data taking. And our result at that moment was that it's around 190 picoseconds plus minus 8 picoseconds as statistical error and systematic error. It's also comparable magnitude as to other kind of tuning, and we were actually doing in the last few months is working with the paper craft that trying to simulate it. So to avoid confusing with maybe slightly different numbers from this conference and future publications, please allow me to keep the systematics for publication, which you will see very soon, I believe. Now we see the results from the production cross-section measurement of our triton with the strings exchange reaction performed at GPARC. And you see, of course, compare with the case of the hydrogen 4 on the production cross-section, the triton case is much more challenging both because of the opposite formation capability and also the decay fraction ratio is also quite different, so that you see a much more challenging solution knowledge ratio, but nevertheless
Yeah, thank you very much for this very interesting talk. I'm using the right microphone or not? I'm not sure. Are there questions to this talk? No questions? Everybody is happy? Yes, that seems to be the case. So we wait for the final results, which will, with the systematic error, of course, very soon. And thank you again for this talk, for this contribution. And we come to the next online talk. I hope this works, the technique now. No, not yet, but this is probably, yeah, now we see your slides. Now it's okay. Perfect. So the next talk is again on hypernuclei lifetime, now from the STAR collaboration by Yue Ma Hang Leung. I hope I spelled that correctly out. And he will talk on recent studies on hypernuclear lifetimes from STAR. Again, 20 minutes plus 5. So please start your talk.
Okay, thank you. So first of all, thank you to the organizers for giving me this opportunity to speak in this conference. And I apologize for not joining in person. So today I will discuss some recent studies on hypernuclear lifetimes from the STAR experiment. I'll start with a quick introduction and then I'll mainly focus on new results coming from the recent BCN2 program. I'll also talk a little bit about anti-hypernuclear measurements as well as branching virtual measurements, and then I'll finish this talk with a summary and outlook. Okay, so as a super quick introduction, one of the main motivations of studying hypernuclei is because it is one of the only forms for us to study the hybridizing interaction, and this interaction is particularly important in the description of the original phase of hybridized objects. So, hypernuclear studies dates back to the 1950s, and traditionally, reactors, exchange reactors, or gamma experiments have been used to study hypernuclei. And it was only until this decade or so that we started to use carrier collisions to study hypernuclei. And one of the main, I think, advantages of carrier collisions is that both light hypernuclei as well as anti-light hypernuclei can be produced in rather copious amounts in carrier collisions. So this actually gives us potential for very high precision measurements. So the focus of this talk is on the lifetime of particularly this is the hypertype, as already mentioned by Maria Ma in the previous talk. The right-hand side is a compilation of previous measurements of the hypertype. You can see that the majority of them lie below that. And this is somewhat surprising because the hypertype is a loosely bound object, and we can
cleaning hinges on this old foil and producing tracks that can be reconstructed using an electricity technique. In order to reconstruct using a detector, we utilize the sonic channels, where you can see the channels we utilize on the left-hand side and bottom corner. You can see a few examples here as well. Using our 3G data, we see clear signal in hypercontinent, H4 lambda, as well small bump on the left-hand side of the main peak. And we further quantified this contamination to be less than 1% effects on our life measurements. Okay, so I want to kind of go over the systematic uncertainties that are being calculated here on the slide. And I only mentioned here that the two, I think, more important sources comes from the analysis task and the input distributions. For the analysis task, they arise because we place topological variable cuts on our candidate in order to enhance its significance, and because our description of such topological variables in our simulation are not perfect, they will incur some non-negligible uncertainties on lifetime events. As for the kinematic distributions, because we need to weight our simulation such that we reflect the true kinematic distributions in the real data, and because our knowledge in the true kinematic distributions are not perfect, that will also infer some uncertainties in the efficiency estimation, which leads to uncertainties in the lifetime calculations. Okay, so this brings me to my results on the energy strategy program. So the red points here represents the new results coming from the energy strategy. Hydrocarbon is on the left-hand side, H4 lambda, H4 lambda is on the right-hand side, and then compared to previous measurements as well as preliminary results of evaluations, that's shown as black markers. If we look at the hydrocarbon, we see that our measurement is a little bit shorter than the 3 hour lifetime, which is shown as the solid gray line here. The global value is indicated by this blue band here on the left-hand side, and is around 80% of the 3 hour lifetime. And this is consistent with recent evaluations incorporating time state interactions as shown as the purple dash line here at the top. As for the A equals 4 hydrogen gas system, here we note that the average, global average of H4 lambda is slightly shorter than the H4 lambda lifetime, around 2-second level. And this can be explained by evoking the isotope rule, which suggests that the pi-zero period should be suppressed compared to the pi-max period by approximately a factor of 2. I'll summarize this slide by saying that the published hydrocarbon H4 lambda results actually has an improved precision compared to previous published data, and hopefully that can bring stronger constraints to field calculations. Okay, so besides low energy conditions, we've also observed hyper-gas signal in our top red energies. And for this particular analysis, we can see the data set used shown here on the right-hand side of the document. They mainly consist of 400 GeV heavy ion emission data sets, and we observe significant hydrocarbon as well as anti-hydrogen signal using these data sets. And in fact, besides the hydrocarbon, we've also observed H4 lambda as well as anti-H4 lambda using these 400 GeV data sets. And in fact, this is the first observation of anti-H4 lambda with an equivalent Gaussian certificate of around 5 cents. So following a similar strategy as outlined for the energy schedule results, we can correct the efficiency, and here we report the lifetimes of H4 lambda and anti-H4 lambda separately, which is shown on the right-hand side block. We see that within the larger subdomains, the anti-H4 lambda lifetime is consistent with that of H4 lambda. Okay, so finally, I'd like to spend a minute or two on this branch ratio element, which I think is quite intimately related to lifetime calculations. So the relative branch ratio R3 is defined as the branch ratio of the two body Okay, so this brings me to my summary. I presented some new hydrogen measurements, hydrogen lifetime measurements, and starting with these indicator. For the hydrogen and H4 lambda, the published results are more precise than the previous published results, and the average hydrogen lifetime is around 80% of the freelance lifetime. This is consistent with theoretical calculations incorporating higher time state dimensions. I've also shown the first observation of NPH4 lambda using our Kiwi data, and you see that I extracted NPH4 lambda lifetimes consistent to match with H4 lambda. Finally, I've also shown new measurements which involve some new methods to extract free body hydrogen elements through template fitting, and this with different was also hydrogen lifetime calculations. So our main software saying that what we analyzed in terms of different T-scan tools that we the tip of the iceberg, as already mentioned by Professor Kiesel in the previous talk, there's actually a lot of data coming from these scan tools waiting to be analyzed, and I think we expect more precise and exciting results in the near future. Okay, thank you for listening.
Yes. Thank you very much for this nice talk and these new data from STAR. Are there now questions? Yes, Tage.
So thank you very much for the nice presentation, and thank you very much for showing the very nice results. So I have a question about the contamination for your hypertriton lifetime measurement from the heavier hypernuclei. So you considered the decay from the helium-4 lambda, pi minus helium-3, and missing proton. And so with your fixed target measurement, so you can also produce heavier hypernuclei. And did you consider the contamination from the heavier hypernuclei than the helium-4 lambda?
Yes, that's true. I mean, this is just an example. For example, I think H4 lambda also produces a similar contamination, and this is also estimated. And for heavier hypernuclei, this is also considered, but this is, I think, smaller compared to this particular helium-4 lambda correlated background, which I think is the most dominant already from our studies.
Okay, thank you very much.
There was a question over there first, and then Horst.
Thanks a lot, excellent talk. I have a question about the three-body decay of hypertriton, this new way that you deal now with the contamination, because you have also out a measurement of the lifetime in the past that used this three-body decay channel, and I'm wondering, is that measurement still valid now that we have this kind of treatment of this correlation? Because if I look at the paper, the signal extraction is very different. Even though the shape of the background, I don't expect it changes significantly between 200 GV and 3 GV gold data.
Yeah, I also am aware that previous measurements uses a difference, and it places a very tight cut on the proton ionized cameras in order to reduce the contamination, which is different from what is presented here. I don't think there's, well, at least to me, not any immediate reason for me to invalidate the previous measurement, but I think this is like a good comment, and certainly something that we're looking into.
Thanks a lot.
Yeah, then Horst, please.
I mean, you mentioned these calculations, including the pion final state interactions. can you say how much the contribution of the final state interaction is for the lifetime?
You mean this calculation, right?
Yeah, it's a question to the theoretician actually, but you might know it.
I believe it's around 10% or so, but maybe the experts can comment on this.
Okay. So 15%, as Avram is telling me, okay. But then it might be of interest to do lifetime measurements also for more heavy nuclei, because that might then change the final state interaction and filter out those particular components. Is there any plan to go to heavier hypernuclear lifetime measurements? That means, say, in the mass 10 region or so.
Yeah, I couldn't fully catch that, but I think that I guess the highest, heaviest nuclei that we can reach is given 500, and that's already shown by Professor Kiesel, and I think we do have plans to linearize the lifetimes from this.
Yeah, it would be interesting to see how that evolves with the mass.
Yes.
Thank you very much.
Yes, Avram?
Not everything that is interesting theoretically is feasible experimentally. If you go to carbon-12, we know that the pion final state interaction, where Zulogio, he calculated it among the first, is less than 10%. And most of the data, most of the lifetime is controlled by non-mesonic decay. So it requires completely different techniques. And I think we should leave it at the few body problems and don't start to study that thing, which is quite frustrating.
Good. Maybe allow me one question. You had these different systematic errors which you discussed, and you assumed probably in your final calculation that they are uncorrelated. Did you look for correlations among these systematic uncertainties?
So this is, I think that's a good question. So these 5 sources that is listed here, in fact, yeah, you're right, we assume that they are uncorrelated. However, analysis has this particular source, we actually, within this, this bracket, there are actually different types of topological paths that we placed. And it is found that, in fact, there are some correlations. For example, the DCA between the pion, the systematics that could be correlated to the DCA of helium, for example, prism stuff, for example. And indeed, we did scan through different combinations in order to understand the correlations between those uncertainties regarding the topological paths to arrive with this final value here.
Good. I think with that we close this contribution. Thank you very much for this nice and interesting talk. And now we switch again to technique here. Hope it works. And we will have a talk by Maximiliano Puccio or Puccio? Puccio, okay. Again now on hypernuclear synthesis analysis by Alice.
Thanks a lot for the invitation and for the introduction. So I really want to talk today about a topic that is dear to my heart, that is like anti-hypernucleosynthesis processes at the LHC, and now we study them with the ALICE experiment. Let me a little bit introduce the topic. So the LHC, okay, people look at it for Higgs boson, Z boson, electroweak, new physics beyond the standard model. But to me, what it really is an antimatter factory. So here you see a couple of plots that try to illustrate these things. You see the antiproton over proton ratio as a function of the centrality in lead-lead collision. So here you see antiproton over proton as a function of PT in central collision and then in semi-central collision. And essentially you see that this ratio is very close to unity. At the LHC, we produce the same amount of matter and antimatter. And if we look even at heavier nuclei, so we go to anti-helium-3 and helium-3, at the LHC we can arrive up to the alpha, but beyond starts to be difficult. You see that this kind of behavior is also there. We still see that we have a ratio that is very close to unity, even if it's a little bit slightly lower, and we know that there is a kind of relation that holds in all kinds of models, statistical hadronization model and coalescence model that are introduced later, that essentially tell us that for a nucleus, we should have like the same ratio of protons to the power of the mass number. So this kind of relationship, we verified it at the LHC up to mass number equal 3, and we even did specific studies that to reduce systematic uncertainty here by calibrating our detector material and studying also the cross-section of antimatter with our detector. So essentially, you see, we have the same amount of antimatter and matter, but still we don't have a lot of these particles. You see, we get 40 protons in a central lead-lead collision, but if we go to hypertritons, we get only one hypertriton every 10,000 events. So hypertritons are much more rare, and this you saw also in the talk of the previous speaker is due to the fact that at the LHC energies, the production of heavier nuclei is essentially suppressed. But why do we look at this? So to me, there are mainly three motivations. Okay, the first one is what we also saw in the previous talk, to study a little bit the properties of hypernuclei, and so to study a little bit the interaction among nuclei and hyperons. And in this case, ALICE really gives most precise measurement of the properties of hypertriton. But there is also a second motivation that I will also focus a little bit more today, that is like solving a nuclear physics problem. So how we get a TeV collision of two nuclei to produce loosely bound objects such as hypertriton that has a B lambda that is of the order of 100 keV. So, and can we use this kind of measurement production to understand something about the properties of these objects? I believe we can, and I will also make this point later. And then there is a third reason that I will not discuss today. So actually, these kind of measurements are quite interesting to study, like what are the consequences for flux of cosmic ray antinuclei that are very interesting for dark matter searches. Of course, there is not so much time today, but if you are interested, just come to me or Laura in the coffee breaks and we will tell you about that. So let's start with something that I feel that people are quite interested in here. Lifetime and binding energy of hypertriton. So in heavy ion collision, okay, you already saw from the previous speakers, we essentially detect hypertriton to the charge decay, to the charge mesonic decays. In the case of ALICE, since we see the same kind of background, dangerous background that was shown by the previous speaker in the three-body decay, we focus on the two-body decay channel, so helium-3 pion. We track the pion, we track the helium-3, we reconstruct the decay vertex, and then we essentially do all the combinatorics and train a machine learning discriminator. In our case, it's not a neural network like it was done in others, but we use actually the XGBoost library, so boost decision trees, and we train this discriminator using both data for the background, for the sideband background, and Monte Carlo for the signal, and this boosts our significance by up to 50%. So I will not go too much into the details of the analysis because Stefania has a talk in a few days, so I invite you all to listen to that talk for all the details about the analysis. I will now go directly to the result. So this is the usual collection plot where we show. Actually, I have to update. Now the paper is published from STAR, so we can put the new reference. This red point is still the preliminary result from the ALICE collaboration. I'm a bit disappointed that we didn't manage to get the paper out for this conference, but I promise it's in the editorial board of our collaboration, so it should be out in a few weeks. And you see that essentially, using the 2018 LED dataset and these new machine learning models, we get a measurement that is as precise as the world average. And we can definitely exclude large deviation from the free lambda lifetime. So now with this kind of precision, we can really go and test also different models with different hypertriton structure. Here you see the comparison with different data. We can only, of course, for the time being, we can only exclude this very old model. But still, I think, as was said also from the previous speaker, to really have a look at model on the structure, we have also to have a look at the other properties of hypertriton, and one of these is the B lambda. So here you see, again, the different measurements of B lambda and the result from the ALICE collaboration. So for the time being, in this preliminary result, we have uncertainties of the order of 100 keV, even though our measurement is essentially compatible with 0. So actually, this measurement is quite precise, but still we are very much limited by our systematic uncertainties. And Stefania will also discuss about this in 2 days. And one thing that one can really see is that these very old measurements are still quite very nice uncertainty, even though they have quite smaller data samples. And something that we are currently developing in ALICE to both improve this measurement and improve the three-body decay measurement is this kinematic closure technique, where we track not only the daughters of the hypertriton, but the hypertriton itself. This actually will be possible with the detector that we have currently installed, and we will take data this year, so stay tuned, because with that we have actually something that is equivalent to a megahertz readout rate bubble chamber. So we can really go and check with precision what is the hypertriton binding energy, but also studying all the different decay channels of hypertriton. Let's move to the antinucleosynthesis processes and what are the implications for hypertritons. So as you might know, there are two big classes of models in heavy ion collision that try to describe the production of nuclei. The first one, the first class is the one of the statistical hadronization model, or if you talk with people, they usually say also thermal models. Essentially, it's okay. This plot, you saw it so many times today. These are the prediction from the thermal model of the yield as a function of the collision energy of the nuclei. And you see that, unfortunately, the LHC sits in the point where actually the yield of hypernuclei is not the maximum, while our friends in STAR and beam energy scanning in others, they sit in a much nicer position. That said, in this model, the key parameters that determine at the LHC the abundances of the particles is the chemical phase-out temperature. And what is very nice is that since nuclei have a large mass, they are quite actually sensitive to the chemical freeze-out temperature. These models are mainly used in lead-lead collision, but I will also show you that they try to extend it to smaller collision systems, like PP and P-lead collisions. The other class of models is actually the coalescence model that are kind of more intuitive, if you want, in the sense that you have like your collision region where you have a lot of hadrons going around. And among these hadrons, you have nucleons, like proton and a neutron, that if they are close in phase space, they have a certain probability to form a deuterons. This is a very naive picture of what the coalescence model does. What is very important, though, in this kind of model is that there is an interplay between the region of the collision, so the size of the collision of the collision system, and the size of the object being produced, so the size of the deuteron or the size of the hypertriton. So you can imagine that since hypertriton, we know that it's very wide state, coalescence is very sensitive to this fact. So let's have a look at the first test of this model. The first way you can test them is by looking at the deuteron over proton ratio as a function of multiplicity. Here you see all the data from the ALICE collaboration in different collision systems going from proton-proton, these colored points. Then there is the blue points that are p-lead collision, and the black points are lead-lead. You see essentially the deuteron over proton is going smooth from small systems to large systems. And this kinds of behavior is actually suggesting us that maybe there is a single nucleosynthesis process that can allow us to describe the production of antinuclei in collisions at the LHC, regardless the fact that we are colliding protons or lead nuclei. The bad thing, though, is that if you look here, you have this green line of the coalescence describe perfectly the data, but also this band from the thermal model is not is describing qualitatively the data. So we really are not able here to distinguish between the two. However, if we also have a look at another observable, that is a proton over pion ratio, in this case, we see different curves from the thermal model that have very different parameters from the ones that are used in the first slide, in the first plot. And essentially what we see here is that the thermal model is not able to describe our data in the proton over pion and deuteron over pion with the same set of parameters. So let's say in this case, we think that the thermal model still has to improve a little bit the description of our data. But if we want to investigate more like the coalescence and in general the antinucleosynthesis model, we should have a look at another parameter that is the so-called coalescence parameter. Here you see the definition. There is essentially the ratio of the invariant spectrum of the nucleus divided by the invariant spectrum of the proton to the mass number. So in the case of the deuteron is deuteron spectrum divided by the square of the proton spectrum. And what it tells us is essentially what is the coalescence probability. So the probability that when you have two nucleons produced in the system, they find each other and they form the nucleus. So essentially, the larger is this parameter, the larger is the coalescence probability. But okay, already from here, I tell you the simple picture that to guide a little bit the eye in this case. So in small systems, so you have to imagine all the nucleons are produced together. They are very close in space, and all that matter is if they are aligned in momentum space. So if they are very close. And since, okay, you have one dimension less, you don't have to care about space, but you have only to care about momentum, we expect that we have a larger coalescence probability. Well, in lead-lead collision, we have a very huge collision system. We have the protons and neutrons, even if they are aligned in momentum space, they might have been produced very far from each other. So they don't meet, they don't have the possibility of interacting, and so you expect that you have a smaller coalescence probability. So why I'm telling you this? So when we go and look at something like the hypertriton, this is a very huge state. So it's order of 510 Fermi. So it's larger than a copper nucleus, it's larger than a proton. So when we produce this in a collision of proton-proton, the probability of having like this very small collision system that gets projected on top of the hypertriton wave function is extremely small. Essentially, we can get in the theory this coalescence parameter by relating the wave function with the size of our collision, and what we get is not only then an understanding of what is the production of nuclei in proton-proton collision, but we can also go and understand what is the wave function of the hypertriton. In this case, you see, for instance, the B3 for hypertriton is a function of the radius of the collision. So large radius is lead-lead collisions, where we have some measurement from the ALICE experiment, and the small radius around 1 Fermi is proton-proton collision. And you see in this case, the statistical hadronization prediction is up there, while in the case of coalescence, we have this dependence even between between the Gaussian wave function and the numerical wave function provided by Hildebrand and collaborators. We see even a difference in this case. But of course, before going to the unknown, so we don't know the hypertriton wave function, we should calibrate our theory on something we know, like the deuteron. So in this case, you see the B2 as a function of momentum, and you see the prediction of the of the coalescence model, assuming different wave functions. So what we see here is that more realistic wave functions, like Kähler effective field theory of the Ulten wave function, they actually factor 2 off with respect to our data. So we have to say that still coalescence is still an incomplete model, at least the coalescence we are using here to compare to the data. There are already some new development, but what is very nice is that we can really use a standard candles like deuterons and helium-3 to gauge our theory, and then when our theory is really calibrated, we can then use it to explain our hypertriton data and then understand what is the hypertriton wave function. But let's keep ahead 1 second and have a look at the hypertriton result that we have in PP and P-LED collisions, so in small collision system. Here you see what are the prediction of the hypertriton over lambda ratio as a function of multiplicity for thermal models that are these black curves, and coalescence model. You see that in the small collision system, we have a large difference between these two. Okay, so what is really interesting is, okay, in this case, the coalescence assumes an hypertriton radius that is of the order of 10 Fermi. But the fact that we have such a large difference between the two models is very helpful, because even though we know that coalescence have a little bit of an issue of explaining things precisely in the case of deuteron within a factor of 2, in this case, the difference between the model is such that we can even ignore that. So when we put on top of the plot our measurements in P-LED collision, the red point, and in PP collisions, we see that actually the measurement shows a good agreement with the two-body coalescence. But what we really care is that we have a tension with the statistical hadronization model, and that essentially we really exclude some of the configuration of the statistical hadronization model. So now what remains to be understood is to which extent we can trust these predictions, in the sense that we know that we have to calibrate our coalescence on other particles to understand and then really have some constraint to the hypertriton wave function itself. But this is not only, it, in the sense that now statistical hadronization is also entering the game of studying in details what happens if we put the wave function in the statistical hadronization model prediction. And there was a recent talk, was 1 week ago, by Bernd Müller at SQM in his summary slides. He showed that he could actually insert in the thermal model a piece of calculation that takes into account the relation between the volume of the collision and the wave function, and essentially get the same kind of suppression. Still, even though this is a different model, it's statistical hadronization, we still need this sensitivity to the wave function to really describe this kind of trend. This brings me to the summary and outlook. So I think that we are really in the high precision era for hypernuclei in heavy ion collision, okay, not only at the LHC, but also at RHIC. And I would like to show you a few projections for the upcoming Run 3 heavy ion run that starts this year in November. So essentially, what you see here is that for what concerns hypertriton, we will measure hypertriton with the same precision we actually measure currently deuterons. So expect even better measurements for what concerns both B lambda and the lifetime, even though you will see in the paper that there is not much to improve on the lifetime side. For what concerns hyperhydrogen for lambda, I think also in that case we will have the same precision in that case that we have for hypertriton right now. These predictions are not updated with the finding of star that we have actually a feed down of a state, so it actually will get even better than this. So stay tuned for some measurements in heavy ion, but also in proton-proton collision, where we can really do a lot. Especially we can have this kind, so in this plot, the S3 as a function of multiplicity, and this is the expected performance in terms of statistical precision on the hypertriton measurement in run 3. You see that these uncertainties are of the order of % in PP collision. This means that when we want to go and test like different wave function scenarios in run 3, we will be certainly limited by theory. So this is really an invitation. If you have ideas, if you really are interested into this, please come and do calculation from us, improve the theory from us, because we will be certainly limited by the theory precision when we will compare to theory in run 3. But not only hypertriton measurement, we can also have a look at the lambda nucleon-nucleon interaction by looking at the lambda deuteron correlation functions. I will not go too much into the details. There is a talk by Bhavani in these days. I invite you to have a look there. So this is a projection of what is the kind of precision we have we expect in this kind of measurement that really gives us like an insight on the three-body forces. But it's also very interesting because if we go and measure the deuteron-proton-pion decay of hypertriton in proton-proton collision, if we have such kind of interaction, this is actually a kind of correlated background that is very difficult to deal with because it will create a kind of bumpy structure below our invariant mass. So summarizing, so really I think ALICE proved to be a precision experiment for the determination of hypertriton properties, and I think that starting from this year, this will extend to A=4 hypernuclei, so stay tuned for that. And what I wanted really to emphasize in this talk is that I think there are also new ways into the study of hypernuclei structure, and the study of the production in small collision system might be one of that. And in this respect, for sure, new data will be coming. What remains to be seen is also if the new theoretical development will be also at the level of precision required to really infer information in this way. So thanks a lot for the information.
Thank you very much for this additional aspect on the hypertriton. Are there questions? We have time for one or two short questions. Yes.
When you talk about the calibrating the theory for hypertriton, what does that exactly mean? Do you assume, because the hyperon has a different mass than the proton or neutron, and so effectively it may come from a different part of the whole fireball than the protons and neutrons come. So I wonder, is this included into the calibration, or the calibration means just that you assume the same source for all three baryons?
So this is very nice. We had also a discussion with Laura about this yesterday. So there is a paper from ALICE where we show that actually the source for proton-proton and proton lambdas, if you consider also lambdas, is actually the same when you check it with the correlation function. Of course, this might be also a current limit in our experimental uncertainty that we see them compatible, but they are already quite precise. So one thing in this respect that one can explore is that currently we have only one-dimensional radii. So for the source, we only check at one-dimensional femtoscopy for that, and this can be expanded with the new data sets that we get in run 3 and have a look at three-dimensional radii and also having a look at different particles and so on. So this might be also one direction where the experiment can also help to improve. But one thing that also we see is that, for instance, what is missing in this kind of calculation right now is that it's not an event by event calculation. Some correlations you have in certain events, they might even come from like jet events, or when you have like protons and neutrons that are created inside the same jet, and this creates a kind of correlation that is actually averaged out when we just have a look at the average radius in the event. So this is also actually, there is a paper from Kakel-Ries and collaborator where they explore also this, and then they also can explain quite well the deuteron data.
Yeah, more questions?
Well, I am not an experimentalist, but it just strikes me, I would like to know, how do you actually determine temperature?
Yeah, so that's a very good question. The first thing one has to ask is which temperature. So in every ion we usually have 3 temperatures, but the one that I'm referring here is the chemical freeze-out temperature, that is actually a fit parameter of the theory. So you measure all the yields of different particles, and then you just fit your hadron resonance gas model to the data, and you get the chemical freeze-out temperature.
Yeah. If I may just very quickly, does it mean that on the level of or the scale of strong interaction, you are expecting equilibrium condition? Because when you don't have equilibrium, you can't do temperature.
Yeah. No, yes. The short answer is yes. So the level of goodness of the fit of the statistical hadronization model fits in lead data suggests that indeed we reach equilibration for the hadronization of light flavor particles. We don't see it, for instance, if you consider charm, you have to, this is out of equilibrium and you have to add it on top of it.
Thank you.
Yeah, you're welcome.
Well, maybe I can make a remark. This question whether these heavy ion reactions are equilibrated or not is a question since 30 decades, you know? Not 30, 3 decades or longer going on, because the point is we know that the system is not in equilibrium. There's flow, there are other things going on in these reactions, and this is, I think, still at the end an open question, because if you form a fragment, you have to get rid somehow of the energy. It has to collapse to a wave function, and if these free nucleons which form a hypertriton are flowing around, you have to get rid of their energy somehow. And this is an old question which is, I think, still discussed in all these heavy ion reactions, and it's finally not solved. So even if it looks like equilibrium, it doesn't mean that there is an equilibrium. Yes?
Okay, thank you very much for a nice talk, and I have a question about the uncertainty of the hypertriton deduced from the correlation function, page 22. From the correlation function of the deuteron lambda. In the case of the deuteron lambda, there have been at least 2 predictions by Mrotinsky-Sloan and Heidenbauer. The correlation function of deuteron lambda is, for the doublet case, the spin half case, the correlation function is dominated by the binding energy. Of course, therefore, it will be, or the scattering length or the binding energy. Therefore, I think that the precision is very much, but it also contains the J equals 3/2 state. Then the uncertainty may arise from there. And did you check the Mrotinsky-Sloan paper and the Heidenbauer paper about that uncertainty to extract the hypertriton binding energy from the correlation function?
You mean to extract the binding energy of hypertriton from the proton-lambda correlation function?
Yes.
So no, this actually we didn't have a look into that, and I refer you to the femtoscopy talks from Alice, because I think that is actually treated better. I'm not a femtoscopy expert. Maybe Laura wants to.
So your point is that this correlation function contains 3 half and 1 half, which is completely true. In the paper about the correlation function lambda d by Adenbauer, what he shows is that if you measure the correlation function in different systems, so with different sizes, scanning PP, PLED, LED collisions, you can distinguish between the models. So obviously you always measure the, let's say, weighted sum of 3½ and 1/2, but you are able to distinguish among the models by measuring several colliding systems, basically. Only one measurement won't be able actually to help you very much. But anyway, we cannot determine binding energy from this correlation. We can just let's say, see which model is best. Yeah, but it's a verification.
Yes. No more questions? Then I would like to thank the speaker again for this very nice. And now we come to theory by Daniel Gassler, and he will talk about the lifetime of the Hypertriton.
Good morning to everyone. And first of all, I would like to thank for the opportunity to show some of our results here. And yeah, I'm going to talk about the lifetime of the Hypertriton. And first of all, I would like to give many thanks to my collaborators, especially to Axel Perez-Obiol and Avraham Gal and Eli Friedman, who are also here, who are particularly involved in this project. And so let me again begin with the motivation. And we have heard it many times in the previous presentations, but I will repeat some things. So what we know about Hypertriton is that it's the lightest bound hypernucleus with spin parity 1/2 plus. To a certain extent, it can be understood as a bound state of lambda hyperon, proton and neutron with a very tiny separation energy, which is also quite rapidly changing in recent years. So here I'm using the world average. And this tiny separation energy also implies very large distance or very large size of the hypernucleus. It is about 10 Fermi. And as such weakly bound system, it's a very dilute system, and it is expected to have a lifetime within few percent of the free lambda hyperon lifetime, which is to 99.7% governed by non-leptonic decay of the lambda. However, what we see in the data is that actually the current world average of the measured Hypertriton half-life is about 20% shorter than the free lambda half-life. And this was recently strengthened by recent experiments like from HypeHigh experiment in 2013 and by the previous STAR measurement in 2018. Which were giving even considerably shorter half-lives for the Hypertriton, which were even shorter than this 20%. Before the Alice came into play, the world average was around 30% shorter, but now Alice seems like the Alice collaboration and also the updated STAR measurement seems that we actually get half-lives which are more compatible with the free lambda half-life. So it's actually not clear if we still have the puzzle or the puzzle somehow is resolved by uncertainties, but still we get something like 20% to explain. And a similar spread was also seen in the previous experiments, and this figure, basically this picture summarizes the experimental efforts dating back to the 60s when people started measuring the things, and here you can see how the world average starts evolving when the Alice started reporting typically lifetimes compatible with the free lambda decay. And on the theoretical side, people also attacked the system for 60 years, basically since the times when the first experiments have been performed, and the spread in the predicted Hypertriton lifetime values was mostly compatible with the idea of very weakly bound lambda hyperon, so it basically should decay at the same rate as a free lambda or even slightly shorter. I think the first signal that things can be very different was computed by Avraham Gal and Garcilaso in 2019, and also recently in 2020 paper again, Fabian Hildebrandt and Hans Hammer updated the calculation with a simpler model, and they again end up with a half-life which is similar to the free lambda half-life decay. So what was our aim to actually, why did we compute it again? And so first of all, we wanted to revisit the hypertriton half-life computation while employing hypertriton and helium-3 wave functions, which were obtained using state-of-the-art nuclear and hypernuclear interaction models, or Hamiltonians, which were derived from chiral effective field theory. As a next, we also wanted to include and study what is the effect of pion final state interactions and both S and P waves. And we also considered what can be the effect of a sigma hyperon or sigma NN admixtures in the lambda in a hypertriton, which are present due to the strong interaction lambda nucleon sigma nucleon coupling. And we also wanted to study the relationship of the hypertriton lifetime and the hypertriton lambda separation energy, since this observable is also not very precisely known, and there is a debate in last years. And last but not least, we also wanted to say something about uncertainties and try to quantify theoretical uncertainties, and especially those we can quantify. So to describe briefly the method we use is to compute a hypertriton half-life is actually quite complicated due to the many hypertriton decay channels. And what is dominant in hypertriton, as I mentioned, are the mesonic decay modes due to the decay of lambda into pion and nucleon, and you can end up with two-body decay channels like pi minus to helium-3, and then the further the additional breakup channels where you break up helium-3 into deuteron, proton, or even disintegrate the helium-3 completely into proton, proton, and neutron. And then you also have the charge opposite decay channels, and everything contributes to the half-life of the hypertriton. And on top of that, there are also non-mesonic decay modes, which are dominant in heavier hypernuclei, but here in hypertriton, they don't play such a role. But we were not able to compute all this reaction from first principles, but we have used kind of shortcut or trick, and I will show you that it's actually, or it was already mentioned, that it's possible to deduce the hypertriton half-life from actually only the two-body pi minus decay rate, so only computing this first reaction, and then you can relate it to the full hypertriton half-life. So how to do it is to first of all compute the two-body decay mode. We can do it because we have methods and tools which allows us to do so, and then we also use the experimental branching ratio, which has been mentioned in previous slides, to add contributions from all pi minus decay modes by using this branching ratio. So you include all pi minus decay modes, and then you also add all the neutral pion decay modes using the empirical delta isospin 1/2 rule. And so in the end, you end up with the total decay rate of the hypertriton. On top of that, we have also added one small 1.5% contribution, which comes from the non-mesonic decay modes, and even added a tiny contribution which comes from pionic absorption on two nucleons, which was estimated from pion optical potentials. And so in order to compute the two-body decay rate, you start with a transition operator of free lambda hyperon, and then you sandwich it in between hypernuclear and nuclear wave functions together with pionic waves, and you end up with expression like this, where you have the It contains contributions from parity violating and parity conserving amplitudes, which are accompanied by the hypernuclear form factors. And the form factors are nothing else than the sandwiches of the wave functions and the transition operators. So in our case, for the pionic wave functions, we use both plane waves, just to be as clean as possible, but we have also considered distorted waves due to the final state interactions. And helium-3 and hypertriton ground state wave functions, we employed the Ab initio-Korshal model to compute them. So just to briefly say what Ab initio-Korshal model is, it's basically a quasi-exact method to solve the nuclear many-body problem. You start with a realistic Hamiltonian or Hamiltonian composed of realistic nucleon-nucleon, hypernucleon interactions, and then you diagonalize this Hamiltonian in a finite A particle harmonic oscillator basis, where you basically expand your wave function in terms of harmonic oscillator wave functions. And basically it's quasi-exact method because the only parameters which are entering the solution are basically the model space truncation, because you include only wave functions, harmonic oscillator wave functions with a certain energy, and also the harmonic oscillator frequency. But in principle, the method is systematically improvable. As you increase the model space, you should converge to exact results, which will be also independent of the harmonic oscillator frequency. And so for the input potentials, we've used, to cover the nuclear part, we have used this particular interaction, nucleon-nucleon and 3-nucleon interaction. It's actually a whole family of potentials, but I will talk about it later in connection with uncertainties. And for the hypernucleon potential, we have used still the chiral leading order potential from Heidenbauer, Polinder, and others, which includes also the explicit lambda nucleon, sigma nucleon mixing. So we deal with a couple channel problem to actually compute a hypertriton. And just to show you the performance of Korshal model when you compute helium-3 wave functions, in this figure you see the dependence of the total energy as a function of the model space truncation for several different harmonic oscillator frequencies. So you see it's like the Korshal model for three nucleons works very well with quite moderate model space sizes. You get very good convergence, where basically the energy is independent of the frequency, and we can actually get 10 to minus 3 MeV accuracy about model space truncation of Nmax 30. And the interaction is also fine. It's optimized with respect to helium-3 binding energy, so we get perfect agreement with the experimental value or up to some uncertainties. In the case of hypertriton, it's a little bit more difficult. The Korshal model typically has convergence problems when the system is weakly bound, and we see it also in the hypertriton. But mostly thanks to the computational advances, we are able to run calculations in very large model spaces and basically get the same convergence for the energy. So this figure again shows the ground state total energy of the hypertriton, but now as a function of what we call effective length scale of the harmonic oscillator basis. It's nothing more than just reparametrization of the Nmax and of the truncation and frequency of the harmonic oscillator basis. But the advantage of using these variables instead of the old ones is that you actually have a theory, or you have some underlying. You can actually compute the corrections which are coming from the there is an analytical expression how you can actually extrapolate the Korshal model calculations to get results in finite model spaces. But in case of energy, you don't really. And the effective length scale is one of the parameters, and there is also an ultraviolet scale, which also translates from the model space truncation and frequency. And so you basically do calculations at different ultraviolet scale cutoffs, and you observe basic convergence with the ultraviolet scale, and then you extrapolate in the infrared region, and this is what it shows. And this is basically the UV convergence. And what do we see? That for UV cutoffs around 1 GeV, we get a pretty converged result for the hypertriton energy. But for the case of hypertriton energy, we also get converged results up to keV when we use the largest model spaces, which we can do. And so if we take these two wave functions and also the pionic wave functions and compute first two-body pi minus decay rate, and this is how it behaves. It behaves, so here you see the two-body decay rate, again, as a function of this effective length scale of the harmonic oscillator basis. You see that the convergence pattern is quite different. It converges slower than the energy, but it's because it depends on the operator. And it's the decay operator is a different operator than the energy, so we can expect a different convergence pattern. But and in this case, we actually had to, or we needed to extrapolate, so it was good to have some analytical underpinning and understanding of the method. And again, we did the analysis for different ultraviolet cutoffs, and we see the same, that for cutoffs around 1 GeV, we can quite reliably extrapolate the two-body decay rate into infinite model space. And yeah, this is written here, it's for 1 GeV. And we perform the extrapolation, and this is, let's say, leading order formula for the correction, but we have used just this simple formula here. We didn't go to higher orders for the corrections. So this was the two-body decay rate. And as a next step, what we wanted to study are the pionic final state interactions. So for this, we also need to understand the pi minus nucleus interaction, because what appears here is that pi minus nucleus interaction affects or has an effect of the outgoing pion emitted from when the helium-3 is created. And we have quite good understanding of pi minus nucleus interactions from optical potentials, which are constrained by fits to pi minus atom level shifts and widths from neon to uranium, and they reproduce also the 1s level shifts and width of pi minus atoms of helium-3. But in this work, we actually needed to, because then you basically get the interaction, but at a threshold energy. But we needed to extrapolate into the kinematical regime, which is relevant for the hypertriton. So we supplemented these pionic optical potentials by also pion-nucleon and pion-nucleus scattering data, and extrapolated to different transferred momentum, which is relevant in the hypertriton decay. And so solving, then we obtain pionic distorted waves, and we can replace the pion plane waves by distorted waves. And what we have found, as Avraham already mentioned, is that due to quite intricate interplay of S and P waves part of the optical potential, the pi minus final third interaction is actually it's strongly attractive, and it is found to increase the two-body decay rate by 15%. And yeah, the details of this are in the paper. So the next point which we studied was actually the sigma nucleon admixtures in the hypertriton. So to depart from the simple picture of lambda plus deuteron. Oops. It's actually in front of me. Yeah. So how does the sigma hyperon appears actually in hypertriton is that we know that or the interactions which we use is designed such that it contains this strong interaction lambda nucleon, sigma nucleon transitions, which in turn couple the lambda nucleon, and sigma nucleon hypernuclear sectors. So your hypertriton wave function is actually a combination of all these different charge channels. And despite the sigma nucleon channels, they contribute only about 0.5% to the norm of the wave functions. They actually have quite a large effect on the hypertriton decay, because you basically open new sigma hyperon two-body decay channels, which are available in hypertriton. And if you write down the amplitudes, then in the end you actually realize that the amplitudes interfere with the original lambda nucleon or lambda hypernuclear amplitudes. So you have a small number, you have a tiny number, but you multiply by a large number, and in the end, the effect of the sigma nucleon, sigma hyperon admixtures is that the two-body decay rate is found to be reduced by 10%. So it goes against the effect of the pionic fine-state interaction. And what we have also studied is that is the relationship of the two-body decay rate, or the dependence of the two-body decay rate on the binding energy of the lambda. And basically, binding energy or lambda separation energy in hypertriton is also quite uncertain. But in our case, we didn't have any parameters in the interaction which we could tune, or we didn't want to do it. But what we have noticed is that using that there is a correlation between the computed binding energy and the two-body decay rate for these different ultraviolet cutoffs. Basically, increasing or decreasing the ultraviolet cutoff of the harmonic oscillator basis, you are throwing away some parts of the interaction, so it changes your binding energy, or it modifies the interaction by itself. But it still provides you well-converged calculations, which you can actually safely extrapolate towards infinite model spaces. And this we have used here, that this correlation actually seems robust. So decreasing the cutoff into smaller than 1 GeV. By this, we decrease the binding energy of the hypertriton, and in the end, it also and it then increases the decay rate, increases the two-body decay rate. And once we have the two-body decay rate, we compute the hypertriton half-life, and we have found actually quite interesting correlations. That in this table, you can see the first column is the ultraviolet scale of the harmonic oscillator basis, which we use to tune the separation energy, and for the lowest cutoffs we get a separation energy about lambda separation energy about 70 keV, but then as we converge and increase the cutoff, we get to basically converged value is somewhere around 160 keV, and this is how the two-body decay rate behaves. So it's smaller binding, it's quite it's sensitive to the changes of the binding energy, and as you increase the binding energy of the lambda, then you also increase the decay. You increase the decay rate of the two-body decay rate, and then you decrease the half-life of the hypertriton. The more bound the system, the longer half-life is going to be. And for example, this first value, it basically makes us consistent with the previous calculations by Kamada et al., which used older Nijmegen potentials, and the Nijmegen potentials produce binding energies of something like 70 keV. And in this way, we could recover their two-body decay rate, and then moving up to lower cutoffs for binding energies around 130, 160 keV, we can actually show that it agrees with the high pi lifetime measurement. And then if we are a little bit, if we extrapolate widely to large binding energies reported by a star, then we end up with quite short lifetimes. And these actually turn out to be compatible with the star measurements, and especially their value for the branching ratio, and then the values basically coincide. So based on just these calculations, we can't exclude any value of the binding energy or the relationship between binding energy and the hypertriton half-life. It's like what we see is that you have a strong dependence of the half-life on the binding energy, and in this case we were able to basically make the measurements consistent within their own with some value of the hypertriton binding energy. And what we have studied as a last, and it's still kind of ongoing project, is to say something about theoretical uncertainties. And I would like to say that we have all the uncertainties under control, but this is not true. And we definitely can't control all the uncertainties which go even into the computation of the two-body decay rate. And so we have focused only on theoretical hypernuclear structure uncertainties in the two-body decay rate. So these are basically uncertainties in the wave functions, or uncertainties in the helium-3 wave function and hypertriton wave function, and how these propagate into the two-body decay rate. So we can divide also these hypernuclear structure uncertainties into method uncertainties and model uncertainties. By method uncertainties, I mean basically the solver you use to solve the Schrödinger equation. But this seems to be completely under control for three-body nuclei and hypernuclei, and we see that the methods are more precise than actually the input Hamiltonians. But then we also have a model uncertainties, especially the hypernucleon interaction, which is constrained by poor database of scattering data, which on top of it suffer from large uncertainties. And they are going to be very uncertain. And the only diagnostic tool we basically have is to study the cutoff dependence, but this is not say, correct measure of uncertainties. And there are also uncertainties in the nucleon-nucleon and three-nucleon interaction, and they are much more advanced compared to the the uncertainties are known much better compared to hypernuclear interactions, because they can use a rich database of flow energy observables and study all kinds of uncertainties. And basically the application of such thing, or it was the aim of the development for this particular family of nuclear interactions which we use, is the N2LO-SIM family. And this family of potentials was that parameters of these interactions were fitted to reproduce simultaneously pionucleon, nucleon-nucleon, and also three-nucleon low energy observables. And as I mentioned, it's a family of 42 Hamiltonians, where the experimental uncertainties propagate into the low energy constants directly into the low energy constants of the chiral FT Lagrangian. And just to mention that these all Hamiltonians, they give equally good description of the fit data. And for example, the helium-3 and hydrogen-3 binding energies or separation energies, they have been in the data set which was used to constrain the interaction. So you basically don't have any uncertainties in these variables, but the prediction for helium-4 actually gives you 1.5 MeV uncertainty. So when we plug this into calculation of the two-body decay rate, the results you can see here, where we plot the binding or the two-body decay rate as a function of the binding energy of the lambda. And this is what you get when you plug in all these 42 different Hamiltonians. So all these 42 nucleon or three-nucleon Hamiltonians, and then you get the spread in lambda separation energies, which is something like 80 keV. And you also get quite considerable spread in the two-body decay rates. So the sensitivity is more what we have expected. And on top of it, there is also the uncertainty which is see in the cutoff of the hypernucleon interaction, because in all these previous calculations we have fixed the regulator cutoff of the hypernucleon interaction to be 600 MeV. But actually you get quite a strong dependence on the cutoff as well. So the blue points, these are these different nuclear Hamiltonians with a fixed hypernucleon interaction. But then we just computed these endpoints here, and then we fixed the nuclear Hamiltonian, but changed the regulator cutoff in the hypernuclear. So altogether the spread is quite huge, and you get a spread of more than 100 keV in the binding energy, and also something like 40 or 50% in the two-body decay rate, which then all propagates into the half-life. So I think I'm completely running out of time, so I will just flash the conclusions. Yeah.
Yes. Thanks very much for this interesting topic. Yes, please, over there. Yeah.
Thank you. Hi, Daniel. Thank you for the nice talk. I have actually two questions. The very quick question is that in the slide 11, you show you use an exponential And that for the extrapolation of the decay width, is there any good reason that one should expect such converge of the decay width?
Yeah, when you switch this effective length scale and the lambda UV cutoffs, then you can actually derive analytically how the correction looks like. So this exponential is leading order of some expansion, and you can find it in the papers of Kai Wendt when he was in Sweden with Christian Forsen. I can send it to you.
Okay, thank you.
We have been working on this much more now, and we'll also have a paper.
Thank you. And the other question on slide 15, that your result strongly depends on the ultraviolet cutoff that you used. And on the other hand, it should also depend on the interactions. For example, the hypernuclear interaction that you used. There we know that the strong difference between the prediction of the leading and next to leading order potentials. Can you somehow say about how your result changed if you use the next to leading order interactions, for example?
Yeah, this I don't know. We would need to use the next to leading order interactions, but I think all the dependence is hidden in the strong dependence of the two-body decay rate on the binding energy, because you can come up with very simple parameterization of the two-body decay rate as a function of binding energy. So it behaves something like a square root of the binding energy, and then this trend seems very universal. It basically doesn't matter much how you change the binding energy, but once you change the binding energy, then automatically the width is changing as well. So if the N to NLO, well, it depends.
Thank you. Yeah.
Good. I want to stop the discussion now. We are here face to, only if it's an urgent question. Yes. But we are here again face to face, so we have time for discussion in the breaks.
I'm sorry, yeah. Okay, sorry, this is not a question to you, but I have a very important question to STAR and ALICE collaborations, because I want to ask both of them, do you want to withdraw the previous data result, or do you want to keep both of the new one and the old one? As the final result of the experiment, if you find the old one, previous data with shorter lifetime are not good as the new one, then you should declare that you want to withdraw the old one. If not, because you showed in the page 3, yeah? Daniel, could you show page 3? This is the average, yeah. This shows in the MINDS database. This is just average of all of this data. But I think we had better make it clear. We should withdraw some of them.
This is an important point, yes, also for the database. But as an experimentalist, I must say we should take experimental uncertainty seriously. And I don't see that there's a really 2 sigma deviation or beyond 2 sigma. And also if there are a few cases far away by 2 sigmas, that's normal if you have 10 data points. So for an experimentalist, this is not a problem. But of course, you are right. These data which we have in the database are disjunct, so there's no overlap also among the data points.
So I want to ask both of the 2 collaborations to make it clear. Yeah.
Okay, with that, I would like to thank you again for this nice presentation. And we come to the last talk by Li Guangtang on the E12-17003 experiment. Now we have to learn 3 numbers for an experiment, not only 1.
All right. So nice to see everybody in a real lifetime, and really appreciate the organizers. All right, so this actually is trying to report the result from this experiment from JLab. And we so far had 2 publications. And the second one, the talk is based on the second one, just came out recently, a few months ago. I don't want to go over too much, so you already heard enough. So I just want to emphasize that the HyperFine result played significant role to us to propose the experiment, because we really think that the lambda proton experiment, at least we have some data. But so far, we don't have lambda neutron scattering data at all. So we basically assuming the lambda proton, lambda neutron scattering is pretty much identical. Taking, don't consider the difference. However, the charge symmetry breaking you already seen. There are at least 3-4 times larger than nucleon-nucleon interaction. So that's promote us to see if we can take a look whether the lambda then system exists, and probably these may provide us experimental data that help us to extract the investigate the lambda neutron interactions. The JLab experiment, when we proposed it, we considered the advantage because E'(K) gave us a direct missing mass spectrum. It will be easier to identify the missing mass, binding energy, measure the natural width, and it can give us a decent precision. And also at that time, there's already 4 approved experiments using tritium target, because that is really an experimental problem. So we take such advantages. But there is a disadvantage at that time for this particular experiment, because the whole system in Hall A is not optimized for K-ion production, and the Q² is very high, very low virtual photon flux. 3 momentum transfers to lambda is high, so the lambda disassociated with the system, the probability is very high, so we anticipate a very small yield. At that time, also, there's no cross-section information available, so we don't know what type of statistic we can get. And JLab is ending such tritium experiment. We have a very limited beam time, so we can only propose up to that little bit time. So that's basically, and also standard equipment, we don't have outstanding particle identification system. So we fight for whatever we have. And that's the only opportunity we can have. So in Hall A, we use a 2 spectrometer. And so 2 spectrometer, left arm, right arm. The left arm, we detect the scattered electron. And the right arm, we detect the kaons. And this spectrometer has very long path length, 26 meters, so the kaon survival rate is very low, only 12%. We have to use a pretty high beam energy in order to give kaon enough boost, 1.8. We keep the kaon at 1.8 GeV in order to have a sufficient survival rate. So we planned 2 kinematics, hydrogen kinematics and tritium kinematics, one for precise calibration for the absolute missing mass, the other one for production. So I will explain this a little bit. In the hydrogen, this is the missing mass. The line represents the reconstructed missing mass in the correlation of a scattered electron momentum and a K+ momentum. So-called hydrogen kinematics, we intend to put both, to let both lambda and sigma 0 appeared in the missing mass spectrum. So therefore, we can use the non-missing mass to precisely calibrate the absolute missing mass. And then in the tritium kinematics, to produce the lambda neutron-neutron system, then we try to have a highest the possible kinematic acceptance. In such a case, the sigma threshold, sigma neutron-neutron threshold is in the corner. So the sigma quasi-free is almost completely moved away. So it chopped away. In the free lambda production, if we switch to hydrogen target, so here is the free lambda, and then the free sigma 0 is completely gone. So because the acceptance is quite limited, right? So we have to use both of them. So I quickly go through, because I don't want to extend this too long. So we have a different analysis strategies, for example, using six-slit holes on each spectrometer to optimize the angle reconstruction, multifoil thin carbon target to get a Z reconstruction optimization matrix. So you can see here that this is the Z reconstruction, and we can see the two high peak is the tritium target cell wall. In between is the gas region, so we cut plus minus 10 centimeter. So the resolution is about 4 millimeter. On the right-hand side is the time coincidence between the two arms. So we got about 300 picoseconds resolution. So we can identify, for the real coincidence kaon, we can separate the kaon out of a pion and a proton. But you can see pion and proton still there because the incomplete the particle identification. We can separate the real, but the accidental coincidence is mainly from the pion and the proton. The kaon accidental is gone. So the accidental contributor to the missing mass is mainly from the misidentified pion and the proton. Now, we also have to understand that it's a large scattering angle at 13.2 degrees. So when we try to optimize the momentum matrix, the scattering uncertainty, the angle scattering uncertainty will contribute actually to the momentum matrix optimization. So we have actually did the resolution, simulation, the contribution from beam energy, momentum, scattering angle, everything folded in together. So we can see that the achievable resolution as a function of a mass. So there we can actually anticipate at A equals 3 what type of resolution we anticipate. And in order to really help to optimize the momentum matrix, we have to select the heavy target, heavy system that actually does not being affected by angular uncertainty at all. So sensitive only beam energy and momentum. So we cut the events from the target cell on the wall. That's aluminum. So to get some data like a magnesium 27, so we use this part of the data cooperate together with the free lambda and sigma 0. Then free lambda and sigma 0 provide precise quench of the absolute beam energy. Then the event selected from the magnesium 27 is heavy, so it doesn't sensitive to the angle to help us to ensure the momentum. We will be confident what type of resolution from the momentum matrix, optimize the momentum matrix. So this is basically showing the magnesium, what type of magnesium 27 we got, the S lambda, P lambda, D lambda. So there are at least three sharp peaks. So from the ground state, we anticipate, if this is a ground state, so this is what type of resolution we're supposed to have. So that actually agreed with the simulation very well. Then this is showing the kinematic calibration. You can see that in the hydrogen kinematics, we see free lambda, free sigma zeros, and with their non-mass, it also agree with the simulated energy missing mass resolution. Then the same hydrogen also taken in the tritium wrong condition, and this also verify our calibration. So this lambda is right on the lambda mass, so the calibration showing the calibration is precise. Then this is the lambda neutron spectrum. This is the overall spectrum. I'm sorry, yeah, this is the in the tritium data. The tritium data analyzed in terms of assuming hydrogen target. So therefore, the actual tritium events is wrong kinematics. But if there is a hydrogen contamination, you will see a free lambda. So these actually verify the tritium target when it was made. There is a 3% hydrogen contamination in it. All right. So from this, we actually, the red line here is we are having a simulation using the helium-3 spectral function. We have the SIMC Monte Carlo showing the spatial distribution. So that is a lambda, and there's some sigma quasi-free, both of them in wrong kinematics, and only the free lambda has with radiative tail. So this is about a 3% contamination. And then the same thing, and if we analyze the hydrogen data in the wrong tritium kinematics, then we can see the hydrogen is broadened, and we know the contaminated hydrogen in the tritium set of data, where exactly it's supposed to be and how the line shape should be. So we extract this function. Then we can take a look at the lambda and then spectrum. So from this general spectrum, there are 5 different contributions. Number one, there's accidental, and this accidental background is mainly from the misidentified pions, protons. So we extract this precisely by selecting the events from accidental peak. We select 40 of them and analyze and scale it down. So we can extract this function precisely. And this is the lambda previous slides. We already know the line shape. We know exactly where it's supposed to be, how the line shape should be. We also extract how many events should be, 158 counts. So therefore, we know this function. And there is some helium-3 contamination, about 3%. So we also had a simulation about that. And this part, number 4, this is the lambda quasi-free. And using the SIMC simulation, using helium-3 spectral function, simulated the quasi-free. On top of it, there's a slightly little bit sigma 0, sigma minus nucleon quasi-free left over. All right, so this is the general feature of the overall spectroscopy. And here I plotted 2 vertical lines. That's the 2 sigma threshold, 3-body threshold. And there's supposed to be another one, sigma minus deuterium, is in between these 2 dashed lines. So that's basically the general feature. So from this glance, you may see that there's no strong suggestion of a strong enhancement suggesting a 3-body system, either bound or unbound or whatever. But however, if you look at the detail, all the simulation, assuming the simulation at least gave us a decent understanding of a general feature, we do see in the threshold, there are a little bit enhancement over there. And this enhancement, and plus there are also enhancement near the sigma threshold. And this, we actually had 3 independent analyses, 3 analyses using different method or whatever. And then we actually can, events by event, try to compare them. So these features actually quite consistent between 3 totally independent analyses. So they're actually showing us there might be something, right? So let's say this is a possibility, right? So we cannot provide solid conclusion, but there is a possibility because of such consistency. So let's consider with all these non-functions fitting there, we just try to see if there is a possibility we fit it. So if we fit, this looks like the binding energy is not bound, it's unbound. So it appeared there's a small enhancement, about 0.2 MeV or so, and with a width 1.26 MeV. And here we only provided the statistical uncertainty. The systematic uncertainty is about half MeV also. So this might be, if this actually is, we cannot 100% identify, right? Because the significance is quite low. The significance is affected by, number one, the total number of counts. Secondly, is the high background. So both of them contribute. The significance is only a little bit over 2. So that's why it's not insufficient to provide definite identification. But so therefore, from so far this experimental result, at least we say it might be possible. If it is possible, then the binding energy could be around 0.2 MeV, and then that gave, excluding the resolution, the natural width is about 0.35, somewhere in that region, right? So, but in the sigma region, you know that the sigma quasi-free is completely removed over here. So that actually explored some extra events quite obvious is over the quasi-free. So one of them is below the lowest threshold, which is sigma 0 neutron. So it looks like 3 MeV below the sigma neutron threshold. And the second one, which is, if it does exist, the second one could be a sigma NN. We don't know which one, what type it is. It looks like a 13 MeV away from the first one, right? So, here we can, of course, from this experiment, from the missing mass point of view, we cannot identify whether this is a sigma minus or sigma 0 neutron. We cannot determine. We can only suggest, because based on the 2 threshold, the sigma 0 neutron is the lowest threshold. Then if this one is even below the lowest threshold, the possibility, there is a possibility, this actually is a sigma 0 neutron. And this is actually quite interesting because the prediction of existence was made long time ago, but so far none experiment have ever seen bound sigma NN type 3-body sigma hypernuclei. If this is actually real, at least there's the first paper published already had some cross-section. This is a photo production cross-section. That lead us to the in future, in case we are able to redo this experiment again, we can plan more realistically how much beam time we need to significantly reduce the statistical uncertainty by reducing the background, improving the significance, to hope we can, we've been able to redo this experiment again with much better precision and more solid, right? So that's all I want to say. Thank you so much.
Thank you very much. Yeah, it's my fault that we are overrunning here. Are there one question? Yes.
Yeah, thank you very much for your interesting talk. So I want to ask you about the possibility to propose to take the deuteron target data with this reaction. So as you mentioned about the sigma NN system, so maybe you explained a lot of things, but recently in JPark we proposed to measure the sigma N cusp two-body system, but the final state is corresponding to sigma 0p. And it's have a long history, and it's clear enhancement have already measured. But in case of this reaction, the final state should be sigma 0n, not sigma 0p. But in this final state, there is no observation. So then if you can measure something, so there may be, and also the interest discussion have already done by the Professor Heidenbauer. So then, so I wanna, so if you have a plan with the deuteron target data, maybe we can, it's really interesting for us. So then, so if you have some comments, so please give us.
So you're saying that whether we should also consider using the deuterium as a target?
Yes, yes. So
Yeah,
then maybe so you can also discuss the two-body system sigma N. So then there may be some clear enhancement in while it's an inclusive spectrum.
Yeah, in the deuterium case actually. It depends what type of physics we're aiming. You know, for example, in this case, we're looking for three-body system, and we are trying from the three-body system whether we can extract the two-body interaction. But if we are using two-body target, of course, you try to directly producing that, then there is a problem that what is the final state interaction can cause you. For example, in the deuterium threshold, whether there's a cusp effect. And there are some issues, but
so we
did, you know, there was experiment done, lambda using deuterium. We had such experiment in 1996. We didn't see anything.
Sorry.
Okay, anyway,
I have,
we can
that is a discussion I think for lunch or dinner. There's enough time. I would like to thank all the speakers of that session. And the lunch is taking place in the same place where you had breakfast. And we will meet again then at 2:30 here for the next session.
our first afternoon session in this very nice conference, and I think everybody here in this room are happy to see so many in person this time, and the first time I think for 3 years or so. And the session is concentrating on double lambda and cascade nuclei, so it's cascade physics, essentially what we will hear in the next 2 hours. And as you see, our first speaker is online and ready to present his contribution on information on double hypernuclei with nuclear emulsion detectors. Kazuma, please go ahead.
Okay, let me summarize our event in this conference. So today I introduce an experimental result of double hypernuclei for using the nuclear emulsion. And also we can see a little bit some characteristics of the double hypernucleus and the hypernucleus. So I introduce current knowledge. And also a little bit recently progress of our analysis method. And finally, I summarize my talk. So, topic with the hypernuclear is essay and also the mass number from 6 to 17, the lambda hypernucleus spectroscopy. And the hypernucleus, especially Xi minus hyperon captured in oxygen and nitrogen and carbon case. And also we measure the Xi N interaction with X-ray from Xi atoms. This subject can be introduced by Dr. Fujita. And also, if possible, we can see the P-wave interaction, that is a lambda hyperon in P orbit. So up to now, we detected the double hypernucleus 30 years ago, experiment 4, and 20 years ago, 10, and present experiment 33, so total 47 double hypernucleus, including the candidate 1, 3, 6. So this is a table of the recent experimental result. Some this one is published event. Also this one. So this is a list of the double lambda hypernucleus. So the Nagara event is uniquely identified. Then this data is strongly, how to say, strongly gives a strongly constraint for this result, Hida and Mikage also. But in E07 experiment, 2 events, just only 2 events, but a little bit free from these data. And I can see the mass number dependence of B lambda lambda. So this is a mass number and B lambda lambda. So almost linear dependence we can see for B lambda lambda. And very recently published one is D001 has 2 interpretations, lithium-8 and beryllium-8. So by this linear dependence, this event likely the beryllium-10, but of course this lithium-8 case is not rejected. And next one is Xi hypernucleus. Xi minus hyperon capture the nitrogen 14. So around here we can see the 2p state, and around this is a uniquely identified Irrawaddy event. So this event constrains the 1s state. For example, that
Kinka case, this one and this one is some one of the spin doublet. So this is a theoretical calculation. This result is support this interpretation. This result is already published in the Progress Theoretical Experimental Physics. So now our result obtained by hybrid method. Hybrid method is emulsion sandwiched by some electric detectors. So its acceptance is very limited, about 30%. If we can free from such kind of the information, that means we scan the whole volume of emulsion. That time we can expect more 10 times statistics. So about 1,000 double hypernucleus can be obtained. So anyway, but total 33 by experimental 07, but just only the less than 10 event was interpreted. So other one is a very, very confused vertex, or we cannot identify by the unknown charge of decay daughters. So now we are developing the analysis method with the X-ray microscopy. So ordinal 3D, we are watching the emulsion for the optical microscope by this direction, but we expose the X-ray. So this kind of the image can be obtained for 0 degree. So this is a alpha decay chain of 228. This one is alpha tracks. So we can shift the angles, something like this. That time we obtained this kind of the 3D image, stereo image we can obtain. Then we can watch the vertex point in different directions. Then that means the very possible, the very precise measurement. In the case of the optical microscope, this is a Uzai hypernuclear candidate. From this point, one single hypernucleus and another one single hypernucleus, but the vertex point is very crowded. So we cannot identify the stopping point here or here or here. Then decay mode of the Xi hypernucleus candidate is uniquely identified, but the binding energy Xi minus hyperon is -4 to 1 MeV. It depends on the vertex point. So we watch this event by X-ray microscope. So this one grain was separated. This grain is formed by silver. So we can identify the capture point here. Then, Then we can measure very rather small error rather than this one. And we challenge to the charge identification of the decay daughters. This is the highest magnified objective lens image for optical microscope. This is the alpha decay and something like this. So the same event we watched by X-ray microscope, then recognize the silver grains constructing the tracks. This grains density corresponds to the energy loss. So this is a hydrogen and this is a helium-4. So we measure the grain density from the 10 to 80 microns. So this is the data of hydrogen is just only 3 tracks, and helium is 10 tracks. Right hand is a developed method by optical microscope. This method applied for the identification of the nuclei of Kinkai event. Kinkai event is a Xi hypernucleus. So we calibrated by 200 alpha tracks with measurement of track widths. After obtaining the track widths, we calculate the track volume. This axis is a track volume ratio to alpha tracks. So this is a targeted tracks of Kinkai event. So we can easily recognize this track 3 is charged 2, not about 95%. So on the other hand, if we use an X-ray microscope, this is a hydrogen and this is a helium-4. By just only the 3 tracks, we can see some good separation. Then we will challenge to this kind of the separation with X-ray at spring 8. And the proposal already submitted. And after hydrogen and helium, we will challenge the lithium, beryllium, boron separation. And now overall scanning, we have now 4 microscopes, so ultra high speed. And if we apply this 4 microscopes, then we can finish the scanning about 4 years. But near future, we'll 10 microscope, 6 microscope will obtained, newly obtained. And also, to detect the double hypernucleus in overall scanning, it is necessary to the very smart scanning. So this trial was done in Riken. So strategy is anyway, due to very little samples of double hypernuclei, then first many images of hypernuclei were produced by simulation of GEANT4, something like this. So then we will make a Martian-like image by use this technology, and we apply the mask RCNN. Then we will pick up the double hypernucleus. At first, we applied the detection of the alpha decay. Then we obtained the 80% efficiency with 20% purity. And now this method is applied for the detection of the hypertriton to resolve the binding energy and lifetime. So anyway, after that, we'll apply this strategy to double hypernucleus detection. Then we are able to estimate the 1,000 double hypernucleus and 1 million right single hypernucleus. So this is a summary of my talk. Anyway, we obtained 33 samples of double hypernuclei in recent experiment. And now, the nuclear interaction is attractive and level scheme can be seen. So near future, we expect 1,000 double hypernucleus and 1 million single hypernucleus. And also, we will confirm the A dependence of B lambda lambda of double hypernucleus, and big Xi at the production of double hypernuclei would be obtained. And we will confirm the level scheme of the carbon 15 Xi hypernucleus, and also we want to detect the carbon Xi minus system, Xi minus oxygen system, and also in the future we will dope the boron 10 in the emulsion. Then we will attack the Xi minus and boron 10 system. And also we have a sigma minus top event in the about 1000. And finally, we would like to target the S equal minus 3 physics. Thank you very much.
Thank you. Thank you very much. Contribution is open for question. Avram Gall has a question.
Professor Nakazawa, thank you very much for this interesting talk. But as experimentalist, how do you explain that this exciting 1s cascade minus states are found only in nitrogen 14 of all light emulsion nuclei? We know that there are substantial amount of carbon 12 and oxygen 16. How do you explain it?
Yeah, today I didn't talk about that, but anyway, our data is mainly obtained mainly nitrogen, but carbon is 2, and also oxygen captured almost nothing. So that means I think the decay daughters is a alpha cluster case for nitrogen. Case is easily possible. That is the reason I think for the amount of the nitrogen capture is a large amount rather than carbon or oxygen.
Thank you. I disagree, but thank you.
So, are there further questions? Over there.
Thanks a lot for the nice talk. I have a question, a technical question on how you convert your Germ4 simulation into the image that then you analyze with these conditional generative adversarial networks.
This one?
So, yeah. What kind of sample of data you give to the adversarial part of the network to discriminate between generated and real data?
Anyway, we are now challenged for the double hypernucleus, but now we are this kind of the alpha decay and also hypertriton image. And sorry, what do you?
Yeah, no. The question is, what if because imagine the adversarial part of the network has to distinguish between the generated part and real data. So essentially, you want your network to produce data that are effectively indistinguishable with respect to real images. But the thing is, I imagine your sample of real images is quite small. So how large is this sample of real images that you give in the training to the GAN?
Yeah. Anyway, we tried first alpha decay. This alpha decay, huge amount of event we have. Then we produce the alpha decay event and some translated image, and we compare the real image.
Okay, thanks a lot.
Okay.
Yeah. So thank the speaker again. We have to stop here. And thank you very much for your talk. And we go on with the presentation of Emiko Hiyama. Emiko, are you online?
Yes, can you hear me?
Okay.
So, and also now I try to have a full screen. Can you see the screen also?
Yes, we see
Okay.
your screen and we see your picture. Okay. Emiko,
Yes.
20 minutes including discussion. And
Okay.
please go ahead.
Okay, let's start. Okay, so First of all, I would just thank the organizer to give me a chance to talk in this conference. Unfortunately, I cannot attend this conference on site. So today I will talk about cascade hypernucleus. Okay, and then study of the cascade and interaction is one of the important issues in hypernuclear physics. So as mentioned by Professor Nakazawa, that he observed the many cascade hypernuclear event like this. This is the Nakazawa-san's slide, and this event is carbon and 15 cascade hypernucleus. You can see that, and then now cascade and interaction is defined by this equation. Now we have a question, and by observation of this nitrogen 14 plus cascade hypernucleus, now we understand that this cascade and interaction defined by this equation itself is attractive. So, and in the future at the JPAL facility, they are planning to produce this cascade hypernucleus, namely boron 11 plus cascade minus hypernucleus by K minus K plus reaction using the carbon target. And then by motivated by this observation in the future, now theoretically based on this observation of the nitrogen 14 plus cascade hypernucleus, now it is important to predict the level structure of this boron 11 plus cascade system. So now theoretical, this calculation will be introduced by Tanimura-san at the end of this session. Okay, so then after observation of this boron 11 plus cascade hypernucleus, now next we want to know and we want to understand this V cell first. So namely, spin isospin averaged terms. So I already pointed out this an experiment very important by this equation, this paper, namely using the rhenium 7 target by K minus K plus reaction, and so this cascade hypernucleus should be produced. So because the reason is why, and core nucleus and helium-6 is known to be hollow nucleus, then valence neutrons are located far away from this alpha particle, then valence these neutrons are located in p orbit, whereas this cascade particle is located in the 0s orbit. Then distance between this cascade and neutron is much larger than interaction range of the cascade and neutron. Then this alpha cascade potential, in which only Wiesel terms works playing a dominant role in the binding energy of this system. So then I also showed that energy spectra of this hypernucleus. So the cascade interaction that I use as these three kinds of cascade and interaction, namely the Nyman modality and extended softcore 04 and Hall potential, which is based on lattice QCD potential. And then this potential is composed of these four terms, namely that this potential are composed only central part only. So then this table is a property of the spin isospin component of these three potential. So this is the isospin 0 and spin 1 of the cascade and two-body interaction. And in the case of ESC04, and especially in the isospin 0 and spin 1 case, is strongly attractive to have a bound state. And on the other hand, and other three components are weakly repulsive attractive. And then in the case of Nyman modality, all components are weakly attractive. And in the case of Hall potential, especially the isospin 0 and spin 0 is strongly attractive. And others are weakly attractive or repulsive. So in this way, spin isospin component of these three potential are very different with each other. However, we found the spin and isospin average property defined by this equation is similar with each other. So next, I show you the result of this A-7 cascade hypernucleus. So this blue line is the lowest threshold, and this red line is our result. So you can see that this we can see that we have one bound state and like this, and the binding energy is similar with each other with respect to the lowest threshold. And the most important thing is the decay width. And if we use the EST04 potential, then the gamma is just around 3 MeV, and the Nyman modality is 0.27 MeV, and then this one is very small and decay width. So in this way, decay width is strongly dependent on the employed cascade and interaction. So from this calculation, now so we can see that A equals 7 is dominated to the binding energy of the cascade hypernuclear with A equals 7 is dominated by the alpha cascade potential, namely this V0. So then, and recently, Fujioka-san planned to produce this cascade hypernuclear using lithium-7 target by K-K plus reaction, and finally he tried to obtain this double lambda hypernuclear. So now we are looking forward to having this data in the future. So after having this data, so what is the next for the experiment? So again, V0 is defined by this equation, okay? So then we have a question among them, which partial contribution and makes attractive for this V0? In the case of cascade interaction, we have this 4 component like this. So then we have in this case, we have a question. We have a two-body bound state of the cascade interaction. In this case, we have no idea. But on the other hand, in the case NN case, also they have also 4 components. Among them, T equals 0 and spin 1 case is strongly attractive to have a bound state as a deuteron. So what's about cascade interaction? We have no idea. So again, I just show you the Hall potential. So also I put on the phase shift analysis of the Hall potential. So from this phase shift analysis, and you can see that the T equals 0 and the spin 0 case is very strong attractive, but another 3 components are weakly attractive or repulsive. How did you get this kind of information experimentally? So to investigate the cascade and interaction experimentally, it might be possible to perform this kind of experiment using the deuteron target by K-K plus reaction. But in this case, we have a cascade and neutron two-body system, but the K-K plus reaction, and we have the T equal total I spin 1, spin 0, or spin 1 case. So that it would be difficult to obtain information on the cascade interaction total as spin 1, spin equals 0 or 1, because there might be no bound state for this system. So therefore, now I suggest to you following, just so we can put on alpha particle for the cascade and two-body system, or 2 alpha particle to this cascade interaction. Then, due to the attraction of the alpha cascade over alpha N interaction, maybe this cascade N two-body system might have a bound state. So among this system, let's discuss on this system. Okay, so then core nucleus helium-5, the ground state is a resonance state. Then we can add it to cascade particle to this system. So then, due to the spin-spin interaction of the cascade neutron, and maybe we would have this spin doublet state, 1 minus or 2 minus state. And then among them, and 2 minus state is maybe an S minus 1, and S minus 1 state of the cascade interaction is dominant. On the other hand, in the case of 1 minus state, and in this case, S equals 0, spin 0 of the cascade N system is dominated. So now what about level structure of the cascade, alpha cascade and system using the Hall potential? Okay, so this is my result. Okay, in the case of total isospin 1 of this 3-body system, and we have this green line threshold. And unfortunately, if I use Hall potential, then the state should be above this green line threshold. Therefore, we have no bound state, because So this is also phase shift analysis again. Then here, this phase shift is a T equal 1 and spin 1 case, and this is also T equals 1 and spin 0. These two state attraction are not enough to make a bound state of this one. And also, I show you the chiral EFT cascade interaction and proposed by Heidenbauer, and just so you can see that T equal 1 and spin 1 phase shift like this. And this phase shift is also more attractive than this Hall potential. So then if I use this information based on the chiral EFT potential, then you can see we have a bound state in 2 minus state. So then I summarize by K minus K plus reaction using lithium 6. In this case, we enhance total as spin 1 case. But in this case, Hall potential does not have any bound state, but in chiral EFT potential has a bound state. So in this way, bound state is dependent on cascade and potential employed. So therefore, from this fact, maybe lithium 6 target is not so good target. So on the other hand, if we use a K minus K0 reaction using lithium 6, now total isospin equal T equal 0. Okay, in this case, if we use the Hall potential, we have 1 minus state is bound state. So if we have a bound state of this 3-body state, we can obtain information on the T equals 0 and spin 0 cascade interaction. Okay. However, also currently, K minus K0 reaction would be difficult experiment. So therefore, also it might be risky to use the lithium 6 target. But on the other hand, maybe to obtain information on the two-body partial wave contribution, it might be useful to employ the boron 10 target, K minus K plus reaction. Also in this case, total isospin 1 case is enhanced. Okay, and the core nucleus is beryllium 9, and this is ground state. Okay, and this is bound state. And if cascade particle is added to this state, and due to the spin-spin interaction of the neutron cascade, and also we have this doublet state for the type and total as spin 1 case. And this 2 minus 1 is just this spin 1 case is dominated, but in the case 1 minus state and antiparallel spin 0 is dominated. So then what about spin structure of this A equal 10 system? Okay, this is my result, but this is very preliminary. Okay, and you can see I already calculate isospin total isospin 1 and also T equal isospin 0 case. And in this case, 2 minus state is a ground state and 1 minus state is excited state. On the other hand, in the case of T equals 0, 1 minus state is a ground state and 2 minus state is excited state. Why? Okay, I just show you the phase shift by Hall potential again. Okay, and you can see that in the case of total isospin 1 case here, and this black line and spin total isospin 1 and spin 1 case is slightly attractive, but in this case is also the repulsive. So therefore, any 2 minus state should be lower than 1 minus state. It's reasonable. And on the other hand, in this case, is a T equals 0 and spin 0 is attractive. Therefore, 1 minus state should be ground state. So in this way, if the level structure of the A equal 10 cascade hypernuclei is observed by experimentally, then we could obtain information on the partial wave contribution of the cascade interaction. So now in this way, any level ordering is so important. So I hope that in the future, experimentally, they observe this in a level structure of the A equal 10 cascade hypernucleus. Okay, and this is a conclusion. Okay, since observation of the nitrogen 14 plus cascade hypernucleus, it is important to obtain information on the cascade interaction. In this talk, I introduced a study of the A equals 6 and 10 cascade hypernucleus to obtain information on the partial wave contribution of the cascade and two-body interaction. Currently, a production experiment of the A equals 7 and 12 cascade hypernucleus at JPARC are planned. So since the bound state of the 8.6 cascade hypernuclei dependent on the cascade potential employed, then it would be risky to perform an experiment using rhenium-6 target. However, maybe I suggest to perform experiment using the boron-10 target at JPAC facility to see the spin partial wave contribution of the cascade interaction next. So thank you for the attention.
Thank you, Emiko. Are there questions, comments? Okay.
Okay, thank you, Emiko, for a very nice presentation. I just have a question. How do you estimate or how do you calculate widths in your calculations?
Okay. So in my calculation, then I use the G-matrix calculation. And in this case, we have an imaginary part. So then, just so I diagonal Hamiltonian, the energy is so real part and imaginary part. So imaginary part is correspond to the decay width. So in this way, I obtained the imaginary part.
Are there further questions? If not, then I would have Emiko. There's also always the discussion about the rank 2 tensor interaction. Do you have any idea how to fix that?
So sorry, the tensor interaction you mean? I cannot catch your voice. Sorry, tensor interaction or?
No, the tensor interaction, the rank 2 tensor interaction.
Tensor interaction, you mean? Okay, I see. In the case of tensor interaction, for the cascade and interaction might be important because there is a pion between the cascade interaction. However, now in the Hall potential, unfortunately, they does not provide me the tensor interaction. So then in the future, I hope the Hall potential provide me tensor interaction. My tensor interaction might be important. So therefore, this would be the next future my project. Sorry, I cannot answer anything, but so I would tell that would be important.
Yeah. Avram, please go ahead.
Emiko, thank you very much for this exciting talk. But I have a question. You suggested to do experiment on boron-10. So in a core of 9 nucleons, you have cascade minus bound by a little bit over 8 MeV, correct?
Sorry, here, this one?
Yeah, the 8 MeV is what Xi minus is bound in beryllium 9.
This one?
Yeah, what is the core? Beryllium 9, so cascade minus is bound by 8 MeV. So now I come to a question. So if you go then to cascade minus in nitrogen 14, which is what excites all of us, you would obtain several MeVs more. It would be completely inconsistent with what Nakazawa-san advertised. Don't you feel that there is some problem here?
Okay, thank you very much. So this is also what I'm thought. Okay, this is I would tell very preliminary calculation. Okay, so then now so far I didn't apply this Hall potential to the nitrogen 14 cascade hypernucleus. So therefore, what about the Hall potential? What kind of binding energy we could have binding energy for the nitrogen 14 cascade hypernuclear. Also, I would check that the consistency with the nitrogen 40 cascade and this one. But now I cannot tell about it because this is a very preliminary result. So therefore, this result, the binding energy might be changing. So therefore, could you wait for some time because this result. Now, last week I obtained this result. So therefore, I should analyze more about this binding energy.
Very interesting discussion, but we have to stop here. Thank you, Emiko, again, and good night to Sendai.
Thank you very much.
So now we are having 3 talks here locally. The first one is, there's already Hans-Josef approaching.
You're not Horst Lendke. Where's the chairman?
That's an S missing, so that is 1 sigma. So, Hans-Josef, please go ahead and tell us about SCRM force for all known cascade hypernuclei.
Okay, yeah. Do I have to stand here for the mic? I guess so, huh? For the microphone, yeah. Thank you very much. In these times, the problem of cascade hypernucleons is very challenging, very interesting. The reason is that we do have some new data, but we don't have enough new data to fix, to draw the unique conclusions or to fix the interaction uniquely. And this is the reason that there are recently several theoretical works, and they all come to using the same data, or nearly the same data, but come to completely different conclusions. And I will tell you about one attempt here that is in terms of the Skirm-Hartree-Fock model applied to cascade minus hypernuclei. Okay, the overview, some brief introduction of the model, and then talk briefly about. Sorry.
You should push the right button.
Yes, that's right. This is too small. Then briefly talk about the data, and then show our results. So just for a very visualization of the brief visualization of the Skirm-Hartree-Fock approach is a typical example. It's a self-consistent mean field model. So the individual, this example is for lambda hypernucleus. It's just the same for cascade, apart from the fact that there is an electromagnetic interaction in addition. So the different single particles levels of the individual particles, neutrons, protons, lambdas, they are sitting here in mean fields that are generated self-consistently from the using the densities here, calculated from the single particle state. So it's a self-consistent approach, a traditional approach that has been used really a lot in the pure nuclear physics, in ordinary nuclei, and therefore we have a lot of nucleon Skirm forces available that we can use here in our attempt to solve the problem. You usually use this one here, the Lyoung 4 force, which is very reliable for ordinary nuclei. But also others can be used, and the results are fairly independent on them. Then our problem here is to optimize, to fit the Skirm parameters of the lambda hyperon force. In our case, it's a neutron of the nucleon hyperon course. In our case, it's a nucleon cascade. This is some more details of the model. So it's an energy density functional approach. We need to specify energy densities for the nucleonic part, involving the kinetic densities, the space normal densities, and the spin orbit densities here. And then we have to add a part here regarding the hyperon. In this case, would be the cascade. It depends also on the hyperonic densities here. Now, in our analysis, it will be very important to consider non-spherical nuclei. So we need, on top of this, we need to consider deformation of the nuclei. This has already been done very early in the initial papers of Wattereng. So we're using a 2D model, axially deformed core, a nuclear core that is axially deformed by imposing an additional constraint on the total quadrupole moment. There are experimental data available on this, and we have to fit to this data for the core nucleus. Okay, this is just very briefly showing the nucleonic Skirm energy density functional. There are usually the two-body terms, and there are kinetic terms, then there are F-surface terms, and there are three-body terms, or many-body terms, let's say, above, beyond two-body, and there's also spin orbit. And we will have, soon I will show you the energy density function for the cascade, which has an equivalent structure. Now, minimizing the total energy of the system, then we arrive at some Schrödinger equation in which we have the input, the things to solve are the mean fields for the different species here. and these mean fields are derived from the energy density here. So we have in particular a hyperon mean field that is obtained from the hyperonic energy density. We have also a spin orbit mean field that is, in this analysis, we keep it still to 0 because in the lambda sector it's very small, and anyway we have too many parameters for the moment. So then it's a mean field approach, and therefore it is not really ideal for very light nuclei because there are several there are finite size effects. But as long as we are only interested in these removal energies of the hyperon, in this case would be calculated from these two nuclei, and these two nuclei share the same nuclear core, and I take the difference then. So there is the idea is that any mistake in the calculation of the nuclear core density will cancel out here in taking this difference, if there's not really a big problem in the model. And one consequence would be, in fact, that the results are fairly independent of the nucleon-nucleon Skirm force that I'm using. In fact, this is in practice this is a case. Anyway, we use this. This is a formalism we are using now towards data here. We have heard already in the previous talk something about the data, in particular about this new carbon cascade hypernucleus. Also has been, I think this has also been mentioned. This has not been mentioned here. There are data on this one, and this is something that is often forgotten, let's say. Okay, I will speak about this now in detail in the future. So we have to, in the following. And so we have to fit the data of these nuclei here. And we fit them by adjusting the parameters of our Skirm force. I will show them in a minute. So that will lead us to a Skirm force, we call it SLX, and then some number in the nucleon cascade sector. So a brief repetition of the data. We have already heard that here several times, I think, anyway. First of all, regarding the 15 carbon cascade hypernucleus, there are these relatively new data, starting with the Kiso event. Kiso event, there were two possible interpretations. Either it's a S, the cascade in the S state or in the P state. That the latter hypothesis is recently confirmed by two other data here. So we think now that this is the correct data here. It's about the cascade is bound by about roughly 1 MeV in a P state in this 14 nitrogen core. So that is this nucleus. Then we have the famous. More recently, we have these candidates for S state. Just we heard about this. First of all, there is a Irrawaddy event with this binding energy, and then there is another event with two interpretations here, about 8 or about 5 MeV. However, only one of the, at most one of these numbers can be the real ground state of the nitrogen plus cascade S system. In the following analysis, it will become clear that if we want to fit the other event candidates for the beryllium and boron hypernuclei, only this fairly strongly bound Kinka event would be the true ground state. So in the following, I will assume this. We have two states here. One is the S state, which is bound by above 8 MeV, and then there's a P state bound by above 1 MeV in the 14 nitrogen core. So we will try to fit these two data here. Now, next, then there is the infamous results for the beryllium cascade hypernucleus. Okay, everybody knows in that analysis they derive this. They don't get bound removal energy, but they only say that the most compatible mean field used for the cascade used in that analysis has a depth of about 14 MeV. This is the relevant plot here again. So here we have this histogram, and there are different attempts to fit the data here from 12 to 20 here. So from the naked eye, one would say here maybe the good one is between 12 and 14, 16, but let's say 20 would be excluded by this data here. So about 14, that is what they say. And then on this, based on this analysis, there were some theoretical calculations here in the past that come to the conclusion that the compatible removal energy of the cascade in a state would be of the order of 5 MeV. 5. But this is not the data. The data is only this year. Okay. So what we therefore what we really need in the near future is a good measurement of these numbers here of the removal energy. And in fact, that was attempted already, but they are not really good conclusions. The only thing is preliminary here, this conference proceedings, and there are several possibilities of the analysis here, 1 peak analysis, 2 peak analysis, and even 3. Also, it takes a lot of fantasy to see peaks here. Anyway, the 1 peak analysis would be compatible with the Kiso p-state value. This 2-state analysis would be compatible with nothing for the moment, and this is anyway excluded. So this is now very preliminary result, the only thing we have. Okay, then last but not least, I mean, this is what there are old emulsion data regarding the formation of 13 boron cascade hypernucleus. They are often nowadays they are often forgotten. We have in the previous 2 talks we have heard nothing about them, but there are two. One reason is that the results are ambiguous. So, but there are possibilities that both of these results correspond to a bound cascade with exactly the same number. This is, of course, just a coincidence. But okay, we cannot exclude that this is reality. So the problem is that these results are ambiguous. So apart from the 0.82 result, it's also possible that actually both nuclei are unbound here. Cannot be excluded. So we don't know this. If there are no bound states here, so if this would be true, then okay, then we have the nitrogen and the beryllium events, and we can easily fit them with most of the models that we have, get some consistent prescriptions. It's more difficult to fit all 3 together. So to include in the fit, this result here is not straightforward, and I will explain to you now. So we will try to fit these data as well. We will assume that these are good data. Now here I specify the energy density function for the nucleon cascade sector. First of all, we disregard here the energy part totally. There are some reasons that it is not a bad approximation. I have not, maybe at the end I can say, but this is not a problem. So then we have the energy density function in this form. We have the usual 2-body force, and we have the kind beyond 2-body force, let's say 3-body force. This parameter is also here. If there would be really a true pure 3-body force, then this would be 2, but this is another parameter in the game. Then we have a surface term here. That is, well, it has no experimental implications. This is an effective mass term because this parameter occurs also in the effective mass of the cascade here. And finally, we have some spin orbit term here. So this is kind of minimal model because already at this stage here we neglect any isospin dependence as well. But already we have too many parameters. That's our problem here. So so what we do in practice here? First of all, we disregard the change of the effective mass. There are also good reasons to do that from Bruckner calculations. Probably it's a good approximation. We also neglect the spin orbit term because we know in the lambda sector this is very small. So okay, might not be true in this sector, but okay, this is. We need to reduce the parameters. There's nothing we can do. This 3-body or multi-body force, let's say, we use some trial values, the standard value 2, and we also use another value 7 or 6, that is often used in nucleon Sturm forces, just to have a comparison. The surface term is very important because it determines the shape of the mean field, and we know we need to compare that with the Vos-Saxon mean field in the beryllium hypernucleus. So this is important to keep that, and in fact we use some trial values here, typical values in the equivalent lambda Sturm force. We have the typical best values are about 20 to 30 here in these units. So this is some natural natural size. And then, okay, then we have two parameters left, the volume parameters we have left, and we use them, as I said, to fit them to these two, the S state and the P state of 15 carbon. Okay, and then that's all. I show the results. So here are the different parameters, either 2 or 7.6, and then varying the surface term here. Then these are the resulting values for A0 and alpha 0 and alpha 3. In order to know the relative magnitude, you could multiply this by about 0.1 because there's another density factor there to make the calculation. So we can say this is about maybe, it can be 20 to 2, the importance of these non-two-body terms can be about 30% or maybe even more of the two-body force here. Okay. Anyway, then these are the predictions fitting the nitrogen, 50 nitrogen. These are predictions for either the boron in S state, boron in P state, and the beryllium in S state. Remember, we don't have the data here, we only have the mean field. Here, however, I just showed you, we have these potential data that the value was 0.82. And you see here, we can get, actually we could even fit it this well. We get certainly very close to this potential P states in boron. So we can reproduce this value. However, the point here is that in our SCRM calculation, this is a strongly deformed nucleus. Without deformation, without deformation, this is not bound anymore. So we need absolutely deformation in the theoretical treatment of this nucleus because the core carbon-12 is experimentally strongly deformed. Okay, this we don't know. Anyway, so this is the data we can very well reproduce, and this here, this is the beryllium, and this is the for beryllium we have only let's say pseudo data we have is the Woods-Saxon fit of the E885 experiments there, and I draw here the Woods-Saxon for the three values 14, 16, and 18, and these are our fits here of the results of the SCRM model for this nucleus, depending on the three-body parameter here, 2 or 7.6, and then of course depending on the surface term. Sorry? Good, very good. Okay, fine. Depending on the surface term. Of course, the surface term strongly influences the shape of the mean field here. So I cannot just compare the depths I get here with the Woods-Saxon depths because they have completely different shape. Look at this one. It's a minimum at higher density. So there's for sure in a macroscopic calculation we can never reproduce the mean field. We can have the Woods-Saxon shape. We can only have let's say overall qualitative comparison. And I would say here that in overall for all these parameters here the comparison is not bad. Certainly we do not go down to 20 and we do not go up to 10. So I would say this is in agreement with the derived. Of course, the shape depends on the A2 parameters. Okay, so there's a fair agreement with the 12 beryllium hypernucleus. Now regarding the boron, I just told you, since the core of the 12 carbon nuclear core is strongly deformed. This is the experimental beta 2 the quadrupole deformation calculated from the quadrupole moments here of the nucleus, and the experimental value is this one here. So in our SCRM model, we must make sure that we create a core nucleus with this deformation, and the result is shown here. And this result here shows the mean fields and also the densities. This is the dashed line is a spherical calculation, and the solid line here is a deformed calculation, is an oblate calculation like a donut. So this is in the z equals 0 plane, and we can see that in the z equals 0 plane, this donut is much more extended than the spherical core. And if you look here, this is a difference of several MeV at a certain radius in the radial coordinate in the z equals 0 plane. And since the wave function here, the wave function of the P state is concentrated to a good part here in this area, the result is that the energy of the p state is lowered here in practice by order of 1 MeV. This in the table before I have shown you that, comparing the deformed and the non-deformed calculation. Using the same interaction parameters for the nucleon cascade, we get a difference of up to 1 MeV in the binding energy. And this is essential because in this way I fit the data. If I would use the undeformed model for the 12 carbon, I could not fit the data. Okay, I'm finished. Here's the summary. We can fit the 3 nuclei together with a very minimal Skirm force, basically 2 parameters. No? That's all. Then, in order to do that, however, we need to assume that the KINCA 808 MeV event is the true ground state of the carbon 15 hypernucleus, because only in this way I can fit also the boron. If I use any other result here, 7 or 6 MeV is not enough to have the boron fit in the Skirm approach always. Okay. As I showed you, beryllium, the Woods-Saxon mean field is fairly well reproduced by our calculation, and here's the reason that the boron is p state in boron is bound is its deformation. It would be unbound without deformation. Comparing with other models, this we will in the following we will have a very detailed discussion, in particular of the boron, I think, because that is, they made a big point of that. In their models, they can fit the carbon and boron, but as we heard already this morning, the price to pay is a very strong binding of the Woods-Saxon, because as far as I understood, there's no deformation of this nucleus, but we will hear about this later. And there's another one here, recent publication, they fit only the p state of carbon. The S state comes out relatively loosely bound, and this is also very low, and therefore they cannot fit the boron. The same is true for recent publication of Yamasan and others here. IMF plus some residual spin-spin interaction. They fit again they fit the carbon. In this case, they can also fit 2 states of the carbon. Woods-Saxon is again in agreement with the beryllium data, but also they cannot fit the boron, obviously, because also there's no deformation. Yeah, that's it. So some last conclusions. You may read them. The very important conclusion is we need more data. We need more data in order to fix our parameters in any theoretical model that we are using here. Thank you very much.
Okay, thank you very much, Joseph.
You're welcome.
Let's have one question. If there is any. There is one.
Thank you very much for your talk, but you were talking so fast.
I don't hear you. Maybe your microphone is not on.
Can you hear me now?
A little better.
Okay, I will start. Now it's better. Okay. I just wonder, why do you call your model Skirm force? Because from the original Skirm force, which is a density-dependent mean field model, practically nothing was left.
So why do I call what?
Why do you call it Skirm force? Because the original Skirm force was defined for mean field, which is real mean field. It had not mean field in very light nuclei.
I cannot hear you. Sorry.
So what's wrong? Can you help me?
Cannot understand.
Unfortunately, it's hard to understand.
Okay. How about that?
That position is a very good one.
Okay. My question is, why you call your model Skirm force? Because from the original Skirm force, practically nothing was left in your model.
The original Skirm force was the nucleon Skirm force. I mean, it's various.
In mean field.
Eh?
It's a mean field,
Yes.
density-dependent interaction.
Yes.
And I can't understand your perception of the mean field in light nuclei.
Yes. This is a mean field, right? This is
Well,
cascade mean field, yes. Yes.
and how about mean field in lead 208?
In that 2.8, yeah, I didn't. I could calculate that. I think, yeah, with our parameters, it goes close to 30, if I'm not mistaken. But I'm not sure. Before I say that.
Shift that discussion.
Or maybe less.
Yes, let us leave it.
I can extend this. Of course, I can immediately calculate heavy nuclei, but we don't have data for the cascade. Of course, yeah.
Right.
Yeah.
But I think we should discuss the whole concept of scalar force and light nuclei. Let us do it later.
Yeah.
Let's stop here and thank Hans-Josef again for his presentation. Let's go to the next.
So I apologize for not being Eli Friedman. He stayed at home, and we are coordinated in this talk. But I'd like first to start by very strong opposition to perhaps the main point made by the previous speaker. Carbon-12 is not a deformed nucleus, certainly not in its ground state. We have evidence, long time evidence from experiments made in Brookhaven for measuring the lambda levels in carbon-12, what we call lambda carbon-13. And the shell model analysis without any deformation gave very good agreement. That's a Milner-type shell model calculation. It was published many, many years ago. So I don't think that introducing deformation in carbon-12, which is not based on any microscopic model, deserves to be considered. We introduce deformations in heavier nuclei when we can't do microscopic calculation and we need to do some kind of mean field, but not where we have microscopic calculations. Another point of objection is that there is no data really on what is called cascade-borne 12, namely E05 or previous experiment of K minus K plus on carbon-12 did not deliver any bound state. There is no experimental paper that reported bound states there. There are some proceedings where these things were made, but nothing, and so those pseudo data should not be analyzed. So having said that, I'm going now to present you with the work of Eli Friedman and myself, and what we did is we analyzed particular set of very clearly defined cascade minus state, which we call lambda twin, cascade minus twin nuclei, and these are obtained, the abstract of our paper appears here. You capture cascade minus in a nucleus ZA, and you observe two lambda hypernuclei without any ambiguity. There are no unobserved neutrons, etc. So let me now proceed. So first, I'll give you a brief overview from earlier counter experiments and also from recent femtoscopy. These are the data that the previous speaker showed from E885BNL and E224KK, and they show you the the endpoint spectra of K minus incoming, K plus outgoing on carbon-12, and trying to fit them with Woods-Axon potential. And I would say that the depth V cascade is of order 15 MeV, and that's really what the conclusion of the first speaker was. So these are old experiments, but no bound state. Another type of experiment was done in trying to search in the AGS for lambda lambda H4. Lambda lambda H4 is a controversial object. The published paper tried to argue that it was seen. Later, there was suggestions that what was seen is not lambda lambda H4, and today most of theorists think that the two lambdas start to be bound in nuclei with A equal 5, namely lambda lambda H5 or lambda lambda helium 5. Nevertheless, you can study this experiment, gives you a quasi-free spectrum of the Xi minus obtained by this K minus K plus reaction on beryllium-9, the initial state before cascades and breakup occurs. And a recent analysis by Harada and Hirobayashi gives you a potential strength of 17 plus minus 6. So it allows even for somewhat higher things. Now I come to show you things that were actually shown by a Miko Hiyama talk earlier, two theoretical models. One of them is ESC 08, Nijmegen, one of their potentials, and the other is HAL QCD. And you see that the main attraction in these things occurs in different partial waves. Nevertheless, the potential depth that reported by Inu et al., Okono, for other type of potentials are quite shallow, are less than 10 MeV. So here we have our first theoretical problem. Emiko said that she could get cascade minus bound in Xi in boron 10, in actually beryllium-9 by 8 MeV, and that by itself would violate already these statements of the potential depth that how do I press for the light? Here, okay, thank you. So this would be in contradiction to this value. So we have problem here. Okay, let's continue now and show you the results of a recent femtoscopy study that appeared of P Xi minus correlations, and you see that this supports nicely the HAL QCD potential. This is now this curve here, and the HAL QCD thing has very strong interaction in the I equals 0 and S equals 0 channel. Okay, so you see that various models of various reactions give us quite different suggestions. I wouldn't say even prediction for the strength of the Xi-N interaction and its spin and isospin dependence. So what I want now to focus on is Strange's minus 2 production at KK and J-Park on diamond target. That's basically leading to emulsion. You place light emulsion nuclei there, carbon, nitrogen, and oxygen. And the cascade minus stops in these light emulsion nuclei and gets captured and cascades electromagnetically in atomic states until it gets captured. And it gets captured strongly by this two-body reaction, Xi minus P going to lambda lambda, So you observe 2 lambda. The 2 lambdas can belong to one double hypernucleus or 2 separate lambda, single lambda hypernuclei. So the most famous type of experiment is the Nagara event, about which there's no controversy. The capture here is on vertex A in the picture, and it corresponds to capture from a 3D state. Conceptually, the cascade can go down also to the 2p atomic state, but the strong interaction, the conversion, kills it, and there's very little that can be done. So all we know is consistent with capture on 3D state, and the kinematics or the binding energy of lambda-lambda helium-6 can be obtained just from the kinematics observed by this experiment. Then there is a weak decay, and then there are unobserved neutrons, but they do not play a role in the determination of the binding energy. Unlike this, there are several events in lambda-lambda hypernuclei that do not allow unambiguous interpretation. For example, what is denoted here by the Mikaj versus Nagara. This thing, the Mikaj thing, is captured in carbon-12. It gives you perhaps lambda-lambda helium-6, lithium-6, but also a neutron. And the introduction of neutron leads to large uncertainty. So it could be interpreted also as lambda-lambda beryllium-11 or lambda-lambda beryllium-12. In all these cases, the theoretical uncertainty, because of the presence of unobserved neutrons, conjectural neutrons, is so large that all these events are basically consistent with good few-body calculations that Emiko Oyama published. Also Milner and I did shell model, but those are not microscopic calculations. So there's not much use from these states. We have only 3 established states in lambda-lambda hypernuclei, and they agree with the Nagara event with lambda-lambda helium-6 we know now. So now this is for lambda-lambda. What happens with cascade minus capture, not to single lambda-lambda hypernucleus, but with 2 twin lambda hypernucleus, single lambda hypernucleus? A good event in our thinking is this Ibuki event, which is Xi minus on nitrogen 14, giving you lambda helium-5 and lambda beryllium-10, and the kinematics is unique, and you derive some binding energy for the Xi minus. On the other hand, there are also events like Kinka, was mentioned earlier, and that involves unobserved neutron, and moreover, it assumes that the cascade minus there is even down to the 1s orbit. I forgot to say that Ibuki is already involves capture of cascade minus from the 1p orbit. So you might ask, how come it goes to the 1p when I say that normal capture occurs from the 3D state? Okay, so what I'll concentrate on is on the good states, on the states that we think are unambiguous, not the ones that require unobserved neutrons for their interpretation. It doesn't mean that some of those suggestions are wrong, but either they have large uncertainty or they allow for more than one possibility. So all these states, you see there is a remarkable agreement between 5 states on carbon-12 and on nitrogen-14, and moreover, they all agree with cascade minus being absorbed in the 1p or the 2p atomic orbit, and you need that because there is a kind of requirement in the third row under the table that L cascade must be the L proton in order to have two lambdas in the one S state. So they all correspond to 1 MeV, and what we did next is calculate the position of the atomic states in carbon as a function of the strength B naught of an optical potential, T rho, which goes like B0 rho R, and we scan over the strength real B0. And what we get is that you see the states that go strongly from atomic to dive to become nuclear, and the correspondence there is that the 2p, capital 2p, becomes 1p, which is a nuclear state, and we fix by that the strength of the optical potential, and that corresponds to depth of an optical potential of 24 MeV. Now the trouble is that some of my states here in this table that I said is a good table, good selection of events, is from nitrogen-14, and the binding energies are 1 MeV. But what I get here, the lowest line here, is that when I calculate the position of this 1p state in nitrogen-14 with this strength parameter indicated from carbon-12, I get 2 MeV. I don't get the 1 MeV roughly. So what happens here? So here comes the surprise. Nitrogen-14, when you couple nitrogen-14, which has spin non-zero, but 1 plus, and you couple cascade minus in the 1p, L is different from 0, you have a triplet of levels. So I kind of copied from a calculation that Milner and I and Dover did many years ago for lambda carbon-13, for lambda states in the p shell, and we have this triplet of states, and I took a parameter for the quadrupole interaction, which is smaller than what is in lambda, because we anticipate the cascade nucleus interaction to be weaker. And lo and behold, I can get the upper state there. Can't press it. I get this state around 1 MeV. Why don't we observe these states? I don't know. It depends on quantum numbers, and I don't know. 5 minutes. What do I do now to get rid of this? No, to get rid of the... No. Okay. So in this way, we can see that nitrogen-14 is a special case for the 1p, and it doesn't contradict what I derived from carbon-12, a potential depth of something like over 20 MeV, which is exceptional in this case. Now, let's introduce density dependence of the cascade potential. Instead of taking B0 to be independent of the density, we make it density dependent. And the simplest thing is to introduce Pauli correlations. In fact, we use a formula that in the slang of some theorists is called WRW. First W is Waas, W-A-A-S. He was a student of Wolfram Weise, sits there in the 90s. And then Monkey Row for the R, and Wolfram Weise for the W. And what this gentleman noticed is for hadron-nucleus interaction, a la Erickson potential for pions, if you want to generalize it for kaons or for any other hadrons, you need to consider straight after the correlation, nuclear correlation terms, after the mean field, after the T rho optical potential, and that goes like rho to the 4/3, but it might be strong in the center of the nucleus. So you have this denominator in the upper formula, which gives you renormalization. When we do it, the 24 MeV reduces to 22 MeV, not much of a difference. But what it would mean is also that it affects our interpretation for what we might deduce for three-body interaction, because there's no single row to the 4/3 term. Its effect spills over also to higher densities. Now, if we do a similar thing for lambda, we can get a potential depth of 30 MeV, so we are consistent with that. If we ask what the 1s binding in carbon-12 and nitrogen-14, they are considerably larger than what Nakazawa showed us from the emulsion events, and about which I asked him, why do you have these things only in nitrogen? We expect the binding energies to be considerably larger than in the 1s, but we also say that the 1s level will not be reached. So now I have specific remarks on these Sturm-Hartree-Fock calculations that were presented. If I take a term that involves a row motivated by cascade and two-body interaction, a term goes like rho square that is motivated by cascade and n. Both of these terms with coefficients marked here A0 and A3 are present in the Sturm-Hartree-Fock calculation. And then I fit them, these two terms, just to the Kinkai event in nitrogen-14, the 1s, which I don't believe in, and to the 1.13 MeV state, Kiso and Ibuki, which also depends what spin value it is. Then I have the table displayed below. The Sturm-Hartree-Fock thing that does not have the Pauli effect gives you an overall potential depth of 13.7 MeV, but that actually is not the two-body strength of the potential, the 13. But it's a result of a much larger two-body strength, 34 MeV. What happens here? 34 MeV and 20 MeV. If we introduce now in the optical potential method Pauli, it doesn't have large effect, but again, the two-body strength of the interaction is much larger than expected. So that does not mean that you should believe in two-body interaction that is so strong for cascade. And in my view, it means that the Kinkai event is not reliable, is not a real case. So after I confused you so much with which events I believe in and which I don't believe in, let me try to summarize. All the 5 events which are unique, they give you potential strength of 24 MeV. The Pauli correlation will give you 22 MeV. I cannot do a decent three-body derivation of a potential term cascade NN because these are only 1p state. And to have a good derivation, I need states in both 1p and 1s because the two-body and the three-body affect differently these states. Now, here are other predictions that we have. They all differ from each other. And then I come to this question, why all the E07 assigned 1s cascade minus events, Kinkai and others, are in nitrogen-14? I need just one good 1s cascade minus event in carbon-12 to proceed from this on. And I will not speak about implications to dense neutron star matter. These are secondary to what lambda witnesses because both the interaction of cascade is weaker. It appears well after the lambda appears. It is important perhaps if you have too many lambdas and they just go to cascade nucleon instead of in free space the other way around. So that's it. Thank you.
Thank you very much, Abraham. So we have time for one quick, precise, short question. is 1 year old.
So you say you at present you can't believe in the either 7 deeply bound states, and so why the Irawaji event, another one, is
Why?
Irawaji event is the another one, another deep bound state. You don't rely on.
I have perfect explanation for the 6.27 MeV plus minus 0.21 MeV, if I recall, in terms of something completely different, but I won't tell it here because I need to finish the calculations with Eli Friedman on this. So in few months, you'll see it published.
I see, okay.
So I believe that the cascade minus cannot get down to 1s. We did cascade calculations, atomic cascade calculations.
But that's not decided. That's not experimentally confirmed.
That's correct. It's not experimental.
So
but
it's still unknown.
yeah, but I have completely different explanation for the irada, for the for the thing that is more. By the way, the Kinka experimental uncertainty is quite large, and 2 sigma there almost overlaps with the states that you mentioned, irada way that is so narrow.
So it's a very interesting, enlightening discussion, but Angels, I suppose we have to go on. Well, if you promise very quick and short, and Abraham promises to give a short answer.
Yeah, Hans showed that if you include the formation, you gain 1 MeV of attraction for this 1p state. So imagine that in a way, your potential of 24 is because you don't have the formation, okay? So if you had, in order to gain, okay, let me see. If you would allow a binding of 0 MeV, so if you would allow 1 MeV less binding in your approach, what would be the size of the depth of your potential, let's say?
The previous speaker said that actually this 1p state can be bound by 1 MeV only because of the formation. And if it doesn't have the formation, they disappear. They are not bound. Now, my experience with hadron states in carbon-12 is that the shell model works perfectly. We get agreement for excitation energies, for gamma transitions, and so the Milnor type. So I don't see any reason to put there.
Okay.
So thank you very much, Abraham. And let's go on now to an experimental talk, I suppose. So it's Takeshi Yamamoto, and you have 25 minutes in total.
Okay, thank you, Chair. I'm Takeshi Yamamoto from JEA. First of all, I would thank organizer for giving me this opportunity to talk about our experiment, X-ray spectroscopy on Guzai minus atom at JPAC. Okay, these are contents of my talk. After introduction, I will talk about our measurement, our first try in JPAC EO7, and then just finished JPAC EO3. And finally, I will talk about the future measurement. Okay, this is introduction. We are aiming for the world first measurement of X-ray from Guzai minus atom. From this measurement, we can obtain information of the Guzai nuclear optical potential. This Guzai-N interaction may have large baryon mixing effect because of the small mass difference between sigma Guzai-N and lambda-lambda. So X-ray data may help to understand this kind of mixing effect. And also, the mass number dependence of this interaction may help to understand the role of Guzai minus in the neutron stars. Okay, our X-ray measurement aim for the, at first, establishment of experimental method to get this X-ray data at first, and then we want to go to systematic measurement to cover the wide mass range of target. Okay, this figure shows a level scheme of iron Guzai atom. when the Guzai particle approached close to the nuclear surface, as shown in this figure, the atomic level energy will be shifted by the strong interaction. And at the same time, the level has reduced due to the nuclear absorption effect. By measuring this X-ray, we can obtain energy shift and reduce, and this have information of the real and imaginary terms of the Guzai nuclear optical potential. In addition, by measuring upper transition here, we can obtain also the absorption strength for this middle state from the X-ray yield ratio between this upper and lower X-ray. So our target X-ray transition is this two in our measurement. And this kind of method was already applied for the negatively charged particle like the K minus and sigma minus or so on. So this time, we will apply this method to the Guzai minus particle by taking advantage of the high intensity K-on beams at J-Park. Okay, X-ray data may give us various information on the Guzai nuclear interaction, and this situation is similar with sigma minus atom data case. Okay, this plot shows the existing data point for the sigma minus atoms. The more than 20 data points are available for the shifter and the reduce. And from this analysis, we can obtain the potential as shown in the bottom figure. And this data make constraint for the potential, especially for the nuclear surface region here. Okay, let's go to strangest -2 sector. So far, we don't have Guzai atom data. So we are now on the starting point for this Guzai atom. So here I listed our target for measurement. So our first measurement is J-Park EO7, where we studied carbon and bromine and silver. And our next measurement, J-Park EO3, was done for the iron atom. And in future measurement, here we will study carbon again. So in my talk, I will talk about these three measurements. And for the heavier atom, the PANDA collaboration have a plan to measure about the lead atom in 2027 or later. But anyway, so far, now we are just at the first step towards the final goal of covering all mass number region. Okay, here I want to mention about another physics motivation related to the emulsion data. So this is event display of the famous Nagara event in emulsion. And Helm 6 double lambda decay chain was written here. So from they reported B lambda value of 6.91 MeV from the analysis of production and decay point kinematics. But in the production point, the stopped Guzai forms Guzai atom. So before the reaction, so this B lambda value will depend on the binding energy of Guzai atom. So actually this uncertainty for this B Guzai binding energy of atom is have contribution for the error of this B lambda. Okay, bottom figure shows the level scheme of Guzai carbon atom. So in theoretical prediction, the last orbit before the reaction is mainly 3D. So for this 0.13 MeV was used for this B lambda calculation. But if the absorption point is not 3D but 2P case, the binding energy will shift with 100 kV. And furthermore, if this state have energy shift, maybe the effect is more serious. So in my opinion, we should check it experimentally from the X-ray measurement to support the analysis of emulsion. So we want to measure this important big xi value for the carbon atom and also as a nuclei studied by the emulsion. Okay, I want to go to our first try in JPAC EO7. So detail was already discussed by Professor Nakazawa-san in this session. And also X-ray detection part will be talked by Fujita-san in Saze. So I want to just show you the overview. So this experiment was already finished by the 2070s. This is cartoon image of experimental setup. We produce the Xi minus from the K minus K plus reaction and stop it inside the emulsion plate. So the purpose of this measurement is search for double lambda hypernuclei and Xi hypernuclei. So recently we reported some special events like Mino event and Ibuki event. So for the X-ray measurement, we installed germanium detectors in front of emulsion plate, and emulsion consists of these elements. So basically, these Xi atom should be produced. But we have a chance for the heavier silver and bromine because the Xi capture probability is high for the high nuclear target case. In addition, we have a chance to observe carbon atomic data in the event which the X-ray emit from target and go directly to the germanium detector. Okay, so the analysis part will be covered by Fujita-san, so I show you just an overview, but the features of this measurement for the heavy atom case, the signal to noise ratio is expected to be good because we can tag Xi stop inside emulsion by the emulsion analysis. But yield ratio is bad because of the low stopping probability or decay probability, and also the low abundance of the target nuclei inside the nuclear plate, emulsion plate. And also, germanium detector setup is not optimal. Okay, so I want to just show the X-ray energy spectrum. The upper and lower X-ray is a spectrum without and with Xi stop selection using emulsion information. So this green region is our region of interest for the bromine and the silver. But unfortunately, no clear peak structure was observed, and we will give just upper limit for branching ratio. So now we are submitting a paper for the analysis of these heavy atoms. Okay, let's go to carbon atom data, which is important for the Nagara event analysis. But unfortunately, for this measurement, we cannot use emulsion information. So signal to noise ratio in X-ray spectrum is bad. And also the yield is limited. So middle figure shows the X-ray energy spectrum. Blue shows the all Xi production event. And basically, we cannot identify the Xi stop, but kinematically, we can select the low momentum Xi production, so which is might be have high stopping probability inside the target. But unfortunately, for also this carbon atom, no significant peak was observed. Okay, this plot shows the upper limit for the branching ratio as a function of the width of 2p state. This dotted line shows the theoretical projection for the branching ratio using the lattice QCD potential, which has a weak imaginary strength. So we cannot observe the peak structure, but around 1 keV width case, we achieve the almost same level we achieve same level upper limit. So we want to retry this measurement in future experiment with improved sensitivity with a factor of 3 or so. Okay, let me go to another measurement, JPAC E03. Interaction is the same, but we select iron as a target because of this is suitable for the X-ray measurement. This is because one technical reason, namely enough high density gains the stopping probability, and also physics reason, namely the suitable absorption strength. We expect the 4 kV width with this 3 MeV, the imaginary potential case, but if we use recent lattice QCD potential, which shows a much smaller imaginary strength, in this case, we have much higher probability to observe the X-ray because in case of the natural width is smaller than our detector resolution. Okay, this is the experimental setup. We performed a reaction X-ray coincidence measurement. Xi minus production identified by the magnetic spectrometers, beamline spectrometer, and Kramer spectrometers. In addition, X-rays were detected by germanium detector array. So in our original proposal, we plan to use a hyperbole J for this array, which was used for hypernuclear gamma ray spectroscopy. But the accelerator power is not enough high so far, so we decided to take 10% statistics data with the present accelerator condition. And for this first phase data taking, we used the other germanium detector array, hyperbole X prime. So I want to concentrate on this first phase data taking. We use this hyperbole X prime system for first phase because this array is optimal for low beam intensity. So this figure shows the configuration of the hyperbole X prime. We used the so-called Clover type segmented crystal germanium detector with a visual suppressor. And we mounted 4 detector units like this to cover up and down side of the target because of the horizontally wide beam and the horizontally wide target. So this table shows a comparison between hyperbole X prime and hyperbole J. So hyperbole X is weak in the high rate capability because of the slow amplifier and also serious radiation damage. But this array has much better energy resolution of 2.5 kV. This has great merit in the case of a very narrow 1 kV width case. We expect better sensitivity with this hyperbole X array for the low momentum beam, low beam intensity expected in the first phase data taking. Okay, this is a photo of the array. This is constructed in the beamline on 2020, and this array also has a target holder, trigger counters, and calibration sources, and also cooling system for germanium detector. Okay, this is a data taking summary. This plot shows an integrated number of K-on beams on the target. We started data taking in December 2020, and during this period, we have the 2 times long accelerator downtime, but finally, in the April 2021, we achieved a 95 giga-K-on target with about 20 days beam time, which corresponds to almost full statistics for the first phase data taking. Okay, analysis for this first phase data is now ongoing. So details will be discussed by Ishikawa-kun in Wednesday. So I want to show you just the X-ray spectrum, but this spectrum is very, very preliminary because the event selection, background reduction, and calibration is not optimized yet. So this is a X-ray energy spectrum. There are some the peak structure from the normal nuclear gamma ray, and these 3 regions correspond to the Xi atom region. So for these region, there are events, but not clearly peak observed at this moment. So we are now on the way of analysis, but roughly speaking, the intensity of X-ray seems to be low than our expectation. So anyway, we will continue the analysis and we will report it in near future. Okay, finally, I want to talk about future measurement. In near future, high-resolution Guzai hypernuclear spectroscopy will be performed with this SS spectrometer. So thanks to the good resolution of this system, we expect this kind of mass spectrum for the Guzai hypernucleus. And we will perform systematic measurement, namely at first start from light nuclei, like carbon and lithium, then go to the other mass number target. Okay, then this relationship between the hypernuclear spectroscopy and X-ray measurement is kind of complementary. In my opinion, both is important for the understanding of the interaction. So in this experiment, the reaction and the momentum is common with X-ray measurement. So we have chance for X-ray measurement in parallel, while the acceptance of this system is rather low, rather small for the X-ray measurement. Okay, first target of the STS experiment is carbon. So the key point of this experiment is use of active fiber target system shown here. This system will be used for the energy loss correction, and this AFT consists of 3 millimeter scintillator fiber, and each fiber will be read out by MPPC devices. So this AFT has a merit also for the X-ray measurement, because we can tag the stop inside the target. So maybe we can realize a good signal to noise ratio as an emulsion experiment. But yield is expected to low because of the low density of the target and also smaller acceptance of S2S spectrometer system.
3 minutes.
Oh, thank you. Okay, this slide shows the demonstration of AFT analysis. This figure shows a simulated event display. Upper part shows the event display for the signal, namely Xi minus stop in fiber. So after K minus K plus reaction, Xi minus particle will stop before after the 4 centimeter or something flight. Then the absorption occur with the rather higher energy deposit inside fiber. On the other hand, the bottom shows a background event, namely Xi minus decay before stop. Actually, this decay is the main background source. More than 90% of produced Xi minus was decay before the stop. So this decay rejection is important issue for X-ray measurement. So in this decay case, by using the information of flight path and decay, the energy deposit, we expect about 95% background reduction, which may much improve signal to noise ratio for X-ray measurement. Okay, second try for carbon atom measurement. For this measurement, we will install germanium detector along the AFT system. And actually, this configuration is almost similar with the previous EO3 experiment. And the left figure shows the expected spectrum, assuming the parallel data taken in the E70 physics beam time. Thanks to the AFT analysis, and we will obtain the good signal to noise ratio compared with previous E07 measurement. Then we have a chance to observe X-ray as shown in this expected spectrum. So now we are submitting the proposal for this measurement, and also we are preparing for this important measurement. Okay, this is last slide, timeline of the X-ray spectroscopy of Xi minus atom at JPAC. in 2070s, we studied for the carbon, bromine, and silver atom in the JPAC-E7 experiment. And we just finished the data taking of EO3 first phase for the iron atom. And now we are here. During JPAC long shutdown period, we are working to exchange magnetic spectrometer from Kramer to the SS. And then, the beginning of 2023, we planning to take the X-ray data for carbon atom in the E70 experiment. Okay, this is summary. We are aiming for the world's first measurement of X-ray from the Guzai atom at JPAC. So we tested experimental technique in the previous E07 experiment, and we studied carbon, bromine, and silver atoms. And we just finished the first phase data taking of E03, which will be iron atom will be studied. And then we have planned for the future measurement with XS spectrometer. We will retry to measure this carbon X-ray measurement. That's all. Thank you for your attention.
Thank you very much. So there's time for one or two questions over there.
Thank you very much for the nice presentation. So I have naive questions. So you made several trials to measure the X-rays, but looks like that you didn't see any signals. So, but before the measurement, I suppose that you had some estimations or do some Monte Carlo simulations, but you didn't observe the peaks. Are there any physics behind it? Or is there any problem of your estimation or experimental setup? And I have another question. So you also showed the Monte Carlo simulation for carbon-12 atom measurement in future. And is that the Monte Carlo simulation, how much reliable is that the Monte Carlo simulation?
Yeah, that's a problem point. Now at present, we don't know the X-ray intensity, accurately. This is depend on the so-called the cascade process of the atom. So now we assume that some 10% or so X-ray intensity per Guzai stop, but this depends on the cascade process, and we have no experimental experimental data for that part. So that part is unknown. But of course, our detector analysis has some problem. It's of course possible. So yes, in this 1 year we check this kind of mistake we really have or not. But at this moment we cannot find this kind of technical problem.
But you have to understand why you do not see the signals with the existing data, don't you?
Sorry?
So, because my worry is that, you try the other measurement in future, but maybe you may have a chance not to observe the signals again. And if you repeat those, and what can you learn?
I see your concern. Okay, yes, first we should, this, the iron atom case that we expect enough, before measurement, enough number of counts is expected. So this part, yes, we expect enough, but the result is not the case. So we should, this is, I think this is first kind of evidence for we need to check the cascade process. So, yes, later we should discuss the specialist for this cascade process. I'm sorry, so at this moment I can't find the reason.
That is a good concluding remark for the moment. Thank you very much. We still have another presentation. And this time it's online. And it's Yusuke Tanimura, energy spectra of carbon-15 cascade and beryllium-12 cascade, and the cascade N two-body adaptation. So,
hello, do you hear me? Hello? Do you hear me?
what is?
Hello?
We do hear you, I guess.
It's
Full screen, you mean?
Hello?
Maybe you use full screen.
Okay.
Yes, now it's full screen.
Okay. First of all, I'd like to thank the organizers for giving me an opportunity to give a talk in this conference. My name is Yusuke Tanimura from Tohoku University. And my talk is about an interpretation to the recent experimental data for carbon-15 Xi nucleus and Xi and two-body interaction. These are my collaborators, and this work has been already published in PRC. So as discussed in the previous talks in this session, there are some recent experimental data for the energy spectrum of this carbon-15 Xi nucleus. This figure shows the observed spectrum. The vertical axis is the binding energy of Xi minus particle. And there are some events that is named Kiso, Ibuki, Kinka, etc. And especially this one. This one called Irrawaddy is a new event. So these data provide information, important information on the S-2 sector of the baryon force. So the purpose of this work is to give an interpretation to this new data, including this new Irrawaddy event. Especially, we introduce spin-dependent Xi-N interaction, and we try to estimate the strength of this spin-dependent interaction by interpreting this Irrawaddy and one of the candidates of Kinka event as the ground state spin doublet state. Either we consider two possibilities, this Irrawaddy and the upper candidate of Kinka is the spin doublet, or the lower candidate of Kinka makes the spin doublet. And we also try to predict using this interaction that we have made estimation. We try to predict also the spectrum of beryllium-12 Xi, that is, which is to be measured in future experiment. So to do this, we do the following calculations. First, we do relativistic mean field calculation, RMF calculation, to get a simple estimate of the structure of this system. We get to get the single particle levels. We get single particle energies and single particle wave functions in these nuclei. And then we introduce an Xi residual interaction, and we do some very simple shell model-like calculation to get the energy spectrum of carbon-12 Xi nucleus. So in the calculation, we assume that the carbon-12 is an inert core, and we consider interaction between Xi particle and the valence neutron and proton. So the RMF theory, it is an meson exchange model. The baryons interact by exchanging the mesons. And for the coupling constants between nucleon and mesons, we take the existing parameter set that is called PK1. And the coupling constants between Xi and mesons are fitted to reproduce the spectrum of the observed spectrum of carbon-12 Xi nucleus. So by doing RMF calculation, we get some mean field for Xi particle and single particle levels. We fit the depth of the mean field so that the S-half state of Xi particle is around 6 MeV, around here, where Irrawaddy and Kinka events are located. And at the same time, the P state energies are fitted to adjust it around minus 1 MeV, around here. So as I mentioned earlier, we consider two possibilities. First, Irrawaddy and the upper candidate of Kinka makes a spin doublet. In this case, we fit the S-half energy around here between Irrawaddy and the upper Kinka. And the other possibility is that the lower candidate of Kinka event is one of the spin doublet states. And the S-half energy is fitted to around here, this between Irrawaddy and lower Kinka event. So then we determine this RMF parameter set like this, and then on top of that, we consider a spin isospin dependent residual interaction between Xi and nucleon, like this. And this is the spin of the Xi particle, and this is the spin of the nucleons, and these are isospin operators. And for this nucleus, the carbon-12 Xi nucleus, we consider the carbon-12 as an inert core, and we consider only the interaction between Xi particle and the pair of proton and neutron, valence proton and neutron in nitrogen-14 core, nitrogen-14. And the energy spectrum, energy shift due to this residual interaction is estimated by first order perturbation theory. So this is what we do. And these strength parameters of this S-wave interaction, they are estimated based on the Hall QCD and Xi S-wave potential. But we found that this S-wave potential is too weak to reproduce the energy splitting between Kinka and Irrawaddy events about 1 MeV. So in addition to S-wave, we decided to consider also P-wave interaction, spin-spin interaction. And we do the same thing. We estimate the energy spectrum by using the first order perturbation, using this interaction in addition to S-wave interaction. So this is what we get. This is our main result. This shows the energy spectra of this carbon-12, carbon-15 Xi nucleus as functions of this P-wave interaction strength, V sigma P. And the left panel shows the energy spectra where we interpret the upper candidate of Kinka and Irrawaddy event makes a ground state spin doublet. And in this case, we find that both positive and negative strength of this P-wave interaction, interaction reproduces the observed energies of Kinka and Irrawaddy event. Then on the on the negative side, it is around minus 150 MeV times femtometer to the fifth. And on the positive side, it is around 100 MeV times femtometer to the fifth. And this right figure shows the other possibility. We interpret the lower one of Kinka and Irrawaddy as a ground state doublet. In this case also, minus 150 and plus 100 gives a reasonable agreement with the observed energies of these Irrawaddy and lower Kinka events. Yeah, this is our main result. And we have also tried using the same interaction to calculate the spectrum of beryllium-12 Xi nucleus. In this case, this system is described as a one whole state on top of the carbon-12 core, which is coupled with the additional Xi particle. And if we take the attractive P-wave interaction, this one, we get as T equal 1 state as the ground state of this nucleus. And on the other hand, if we take the this repulsive P-wave interaction around here, we get T equal 0 state as the ground state. So to summarize, we have tried a qualitative interpretation of the data of carbon-15 Xi nucleus, and we by interpreting this Kinka and Irrawaddy as the ground state spin doublet, and our finding is that the spin we estimated the strength of this P-wave, spin-dependent P-wave interaction. We find that probably this spin-dependent P-wave interaction is important at least in this nucleus. Okay, that's it from me. Thank you very much for your attention.
Thank you very much. So let's have time for one. Avram.
Although using the spin-spin interaction to split the two 1s states is correct conceptually once you started from a mean field calculation, but doing it the same way in the p states in nitrogen-14 is not complete and misses a lot, because besides the spin-spin and other residual interaction, you have the effect of what I call second Slater integral, the quadruple term, which comes from the fact that you couple different spins and you expand the central part of the interaction, the one that goes like V0 in multiples. And that is the effect that I showed splits things by something like 1.5 or close to 2 MeV. So then the conclusions based on comparing what happens in splitting the 1s states and the 1p states are incomplete from this calculation still.
Okay, so
Okay.
do you want to answer?
Thank you for your comment. And I am not completely sure if the quadruple interaction is really important in this system. Maybe it is this contribution, this effect of quadruple, maybe it is induced by the quadruple polarization of the core, nitrogen-14 core, right? And it is my personal opinion, my feeling, but I'm not sure whether this Xi particle, the effect of Xi particle is strong enough to polarize the nitrogen-14 core. And this is just my personal feeling.
Okay, I mean, if you would hear in person, I would say that is a discussion for the coffee break, and that is now ahead. So thanks again to you and to all speakers of this afternoon and the lively discussion. And we recess at 5:05, 5 minutes past the hour. Thank you very much.
Okay, take your seats, please. Okay, we are about to start this second afternoon session, which will be fully dedicated to the study of the K-baryon interaction, the Lambda 1405, and light kaonic nuclear clusters. So the first speaker is Albert Feijó. He will talk about the K-baryon interaction in P-wave. Thank you.
Okay, first of all, I would like to thank the organizers for this invitation. I should admit I am very happy to be here, not only because the event itself, but also because I am back home. And this is possible thanks to the economical support from Horizon 2020 program. Thanks, Joseph, for taking care of us. Today I'm talking about the role played by the P-wave terms in K-baryon interaction within the unitarized KPT framework. This work has been carried out in collaboration with my good friend Daniel and my new collaborators Angel Ramos and Volodymyr Magas. The aim of this study is the description of the meson-baryon interaction in the sector of strangeness -1, extended to moderately higher energies than usual. This sector has 10 channels whose thresholds range from 1,255 MeVs to 1,810 MeVs, reason why we think that P-wave could play a non-negligible role, because, for instance, we can have production processes involving channels at the opposite edges. Yeah? All such processes are governed by the strong force, and it is well known, perturbative quantum chromodynamics fails in order to describe low-energy hadron interactions. This brings us to chiral perturbation theory, which is an effective theory with hadrons as degrees of freedom, which respects the same symmetries as QCD. The validity of such approach is limited to a moderate range or short range of energies above threshold, and is not applicable in the vicinity of any resonance. But this is not the end of the story, because K-baryon interaction is governed by the presence of lambda 1405 resonance. So to get around this difficulty, we need a non-perturbative resummation. In fact, back in 1995, Kaiser, Siegel, and Weisse reformulated the problem in terms of a unitary extension of KPT coupled channels. This scheme allows us to dynamically generate bound states and resonances. This was kind of revolution, and it triggered a lot of activity in the field. As you see, there are many papers from this period, some of them very important, but here the point is that all of them reach a very good description of the scattering data. And for me, what is even more important is that most of them found the two-pole structure of the lambda 1405. More recently, the eruption of experimental advances renewed the interest on this topic. Proof of that are all these papers here. I'm talking about the measurement of the pi sigma invariant mass for this kind of photoproduction processes by class collaboration. And on the other hand, we have the measurement of the energy shift and width of the first state of the kaonic hydrogen by Siddhartha collaboration, which establishes the K-P scattering length within a 20% precision, which is quite impressive, settling, therefore, the previous tension between Keck and their measurements. Here, I took some figures from several groups published in the last, these works have been published in the last 10 years, so meaning that they are taking into account the previous experimental data, or some of these experimental data. And as you see, we represent here, well, they represent here the total cross-section of K-P going to the classical channels. Here we have the K-bar N, pi sigma, we have aquí both pi sigmas and pi lambda as well. But if we twist a little bit the approach, we can also reproduce processes that take place at high energies. This is, well, this trend has been followed lately. It started with Gu and Oyer that incorporated in their fitting procedures eta lambda, and this trend was also followed by us, and so on. So let's jump to our works. Over these last years, we have been working on the next to leading order contributions of the chiral Lagrangians since they have been not established yet. At the beginning, we pay special attention in reactions which are particularly sensitive to the next to leading order terms of the chiral Lagrangian. I'm talking about the K-bar n going to K-cascade reactions because they do proceed, or they don't proceed through the Weinberg-Tomozawa term at 3 level. In the second stage, we analyzed the relative relevance of those contributions that come in hierarchy next to the Weinberg-Tomozawa term. I am talking about the role of these terms in these reactions. And we found there that the Bohr terms as well as the next to leading order terms play a similar and important role in those reactions. And finally, in the third stage, in order to constrain as much as possible the potential ambiguities in the isospin components in the amplitudes, we incorporate scattering data from isospin filtering reactions. For instance, K minus P going to the eta lambda channels. Yeah, at the end, as a consequence, we found more reliable values for the low energy constants of the next to leading order terms. In addition, in this work, we also developed a model that, apart from these chiral amplitudes, incorporates some resonant contributions calculated by means of Rarita-Schwinger method in order to mimic higher partial waves. And what we found is that this incorporation improves slightly the description of the experimental data, well, by means of providing some structure. Okay, with this in mind, in order to illustrate the evolution of our models, I would like to show you a prediction of the total cross-section of the K-long proton going to K plus cascade 0, which is a pure isospin 1 process, and it's going to be measured at JLab. And as you can see here, well, let me say first that none of these two experimental points have been included in any of the fitting procedures, and these two, the dotted green line and the dotted dice yellow line, belongs to the first and second stage respectively, and these models were developed in the third stage. The message here is that as you incorporate or put more and more ingredients, you are getting closer to these experimental points. So this fact leads us to believe that the inclusion of P-wave terms coming from the chiral Lagrangian could improve, well, I don't know to which extent, but in principle should improve a little bit the description of these processes that take place at higher energies. Okay, if we check out what's in literature regarding the P-wave contributions coming from the chiral Lagrangians, we find these 4 works. The first one in the sector of strangeness equals 0, where the authors develop a model derived from Lagrangian extended up to next to leading order, and the reactions under study, some of them receive important contributions from P-wave terms, and in particular this one was completely governed by P-wave contribution. Then here we have a revision of the kaon-nucleon interaction, and then in the sector of interest we have these 2 interesting works here, both of them limited to low energies. The first one developed from a Lagrangian up to leading order, in particular was Weinberg-Tomozawa and S channel, if I don't remember wrongly, And the second one was more sophisticated because they included also the next leading order terms. In summary, what in this first work, the authors studied if there is any contribution from P-wave and this phenomenology, and they don't see any important trace of the P-wave contribution. But I should say that technically speaking, this work was very useful for us. And in the second work, the authors found a P-wave pole with this 1/2 plus quantum number, mimicking the lack of the sigma 1385, which in principle should have 3/2 plus. This has a clear explanation. I am not going to enter into details here. Okay, let's jump to the formalism. Here we have the chiral Lagrangian, the first and the second order, which is nothing else than an expansion in powers of momentum over a scale factor which characterizes the system. Each building block preserves the symmetries of the interaction, and it's preceded, and they are preceded by constants that are known as low energy constants that are unknown and should be fitted to the experimental data, meaning that they contain all the information of the problem, the physical problem. So at leading order, we have these three contributions. From the first one, we can derive the so-called Weinberg-Tomosawa term, which is this contact term. In principle, this is the significant term in order to describe the experimental data, and the rest of the contributions should play, in principle, a fine-tuning role. Next, we have these two terms, which include these pseudo-scalar couplings, and from which we can calculate the vertices of these diagrams, known as the Bohr terms, or S-channel and U-channel, respectively. Once we derive the interaction kernel, they incorporate two more low-energy constants. I should say that these are also well known. They are the vector axial couplings, and yeah, we know the values from the beta decays. Okay, here we write down the second order, the next leading order terms of the chiral Lagrangian. I should say that it has been common practice to discard all these terms. Well, we limit ourselves to at tree level. Continuing what I was saying, it has been common practice to discard all these terms when you are dealing in one energy regime which is located close to threshold. But now, since we are dealing in a region which is at slightly higher energies, we have checked that they are completely needed. So all these guys which are accompanying each single term here should be fitted to the experimental data because the underlying theory is not able to constrain them at all. I should say that the terms which comes with the G3, once we calculate the Hermitian conjugate of the Lagrangian, vanishes. Yeah. So once we write down or we derive the interaction kernel here at Dirac level structure, this is what we have for the Weinberg-Tomosawa and for the next leading order term. Since we aim to decompose it into higher partial waves, we should pay attention on to which Legendre polynomials they are contributing. So in principle, we should focus on the cosinus of theta, where this theta, or the degree of the cosinus of theta, where this theta is the angle that between the momenta of the incoming and outgoing particles. Here we have a single cosinus theta, so at most we can have S and P wave. Here at maximum we can have here cosinus squared theta, so we have S, P, and D waves. The same could be said for the Bohr-Dirac contribution, so we have just one cosinus theta, so we have S and P. And here the thing is a little bit more, little bit trickier because we have the dependence on the U Mandelstam variable, which depends directly in cosinus theta. So since it's at the denominator, it's going to contribute to each Legendre polynomial. Okay. 5 minutes? Hostia. Well, so we can write it's convenient to write the amplitude in terms of the spin flip and spin non-flip parts. Then this F is an expansion in Legendre polynomials. The same could be said about this G. This is nothing else than the addition of the previous terms. Here, since the good quantum number to be unitarized, which is the one which is in fact preserved, is J, we should redefine our amplitudes. And then, since we have, as I have said, the presence of several resonances in the energy regime we are working or we are dealing with, we should solve the Bethe-Salpeter equation to unitarize when this G is the Mason-Varion loop function, which at the end of the day, after dimensional regularization, incorporates the subtraction constants, which are unknown parameters that should be fitted, despite we know their natural size. And finally, once we have these amplitudes unitarized, we incorporate them into the this expression for the cross section, which is quite neat, and we have extended it for convenience to D wave, as we will see. So here we have all the parameters of our model. I am going to be fast. Okay, then we should feed them, all of them, to this data. I mean, the cross sections, the branching ratios, and the shift and width of the chaonic hydrogen. The criteria we follow to fit it is the chi-square distribution, defined in the classical way, and then we developed 3 models. Well, in fact, this one was already developed in one of our previous models, where we have an interaction kernel which has been derived from Lagrangian up to next to the encoder. We only take the S-wave contribution, and we discard the G and H terms. The second model is equal to the first one, but incorporating the G and H terms. And in the third model, we also incorporate the P-wave contribution. Okay. So here, we plot what we get for the classical channels, since the data we use to fit the models is in the proximity of the k-bar-n threshold. We see what we can expect. There is no difference between models, so meaning that the P-wave contribution is almost nothing. So maybe here we have a little enhancement, but this is due to the fact that the pi lambda threshold is open far below the k-bar-n. Okay, here we have the total cross-section for those channels which are open at higher energies. As we can expect, the 3 models behave similarly at low energies for the case of eta channels here and here, and then they start differing among each other as the energy increases. Okay, for the K-cascade reactions, the thing is completely different, because we have difference already from the corresponding thresholds. You see, at low energies, the model which takes into account the P-wave contribution overshoots the experimental data, but do a good job at higher energies. In order to understand what is going on with the P-wave contributions, we decompose this last model in the GP terms, on the GP components. Okay, here if we jump directly to the eta sigma.
I'm sorry to interrupt you. Please speak on the mics because we are streaming and this is a bad position for mic.
Sorry, I apologize. Okay, we see that in this case the S-wave is the one which is dominating. In this case, the S-wave due to the presence of the lambda 1670 is dominated by the S wave, and here we see that from 1750 on, the 3½ plus is gaining relevance. The same could be said about the K0 cascade 0, and here it comes the shocking thing, that the P wave through the 3½ plus component is dominating the whole process. Okay, and finally, we can wonder if all these ingredients are enough to describe what's going on in these processes, and without touching anything, I mean, keeping the same parameterizations, we just incorporate the deep wave contributions, and you will see they have sizable contributions. The strength is notable, especially for this process and this process, meaning that we cannot avoid the fact of incorporating also these deep waves. So we are working on this now, and let me leave the conclusions here, and that's all from my side.
Okay. There is one question here.
I see that you use, I mean, a dimensional regularization there to unitarize the model. For P waves and D waves that you use, I mean, I think it's fair if you go above threshold as you have done, but don't go below threshold with dimensional regularization with P and D waves. Don't do that. Below threshold. What you have done is okay, more or less. In any case, I would suggest also just to see if there are changes. I mean, to do the regularization, you know, with the cutoff. Because with cutoff, I mean, you have a feeling better, I mean, of what is, how you should cut the P and the waves. If you do dimensional regularization, sometimes you lose the feeling of what the subtraction constant should be. Although I presume you feed it, right?
Thank you for the comment, Eulogio.
Okay. One more question over there.
Can I ask for my own curiosity, in slide number 19, why is that you, in the newest way where you incorporate this next
Sorry,
to,
I cannot hear you, Oton.
In the newest wave, in the elastic channel, what's the reason for losing the cusp at the opening of K0n, anti-K0n? In the first plot in the left, you kind of, I observe that there is a difference, you kind of lose the cusp structure there.
I don't know, being honest, I don't know.
No, I think there is a little cusp,
Well,
but okay.
but okay, it's not that pronounced, but I don't know.
There is no explicit reason for that. Okay.
I think we should move forward, and so I call the next speaker.
Vale, perfecte. Molt bé. Gràcies. I ahí s'arrima o així o què? Així?
Sí, they are going to put...
Així, però el micrófono és este?
Yeah, these are the microphones, so if you have to be here, then, I mean, you should try to be here.
Okay, fine. Okay. Vale. No va, so sí que va. Okay, so let me see. I'm going to talk about, something different. It's lambda 14.5 mediated triangle singularity in the K minus deuteron going to proton sigma minus reaction. Collaborators are, Albert Feijó, Raquel Molina, and Jan Rong Dai. So I talk about, K bar and update, but I have to skip it because, Albert already talked about that. I'll spend some time talking about triangle singularities, which I know is novel for most of you, and then about this reaction concretely. So, fine, let me see. I will be very fast about that because, you already know and because Albert already said. But the lambda 1405 is this funny object, that nowadays, from the perspective that we have about it, we would say that that is the first pentaquark that we already had. I mean, there's, I mean, a consensus, I mean, that is made out, generated from the interaction of meson-baryon and K-bar-N and couple channels, and that we have two, not one, but two lambda 1405 states, which they are already, I mean, official in the particle data book. You probably have seen that already. So fine, I mean, I want to say that it's so old, you know, because the idea came already from Dallis and Twang, I mean, 60 years ago or 70 years ago, I mean, that could be a bound state of K-bar-N and sigma pi in couple channels. And since then, lots of work has been done. But I mean, it was, I mean, made systematic, you know, I mean, and more clear, more compact and convincing, I mean, with the advent of the chiral unitary approach. And I want to always, I mean, mention, I mean, the work of Kaiser, Ziegler, and Weiser, which I believe, I mean, I consider the pioneer of this field, which has been so fruitful later. Later, there have been lots of work, and Albert, I mean, has already mentioned that. And, you know, I mean, people get fantastic results, you know, I mean, now, I mean, for the K-bar-N interaction, going to all the channels and other reactions. Now, the funny thing is, you know, that you see, I mean, the people, I mean, who do K-bar-N, they feed data of scattering, you know, and then they talk about the lambda 1405 or the two lambda 1405, but I mean, they have not used any data of a lambda 1405 production. I mean, 95% of the works are like that. Well, the nice thing of it is just the lambda 1405 or the two lambda 1405 come out as a gift, you know, because you don't feed it, and in spite of that, you get it. It's just really great. It's fantastic. But anyway, the thing is that I insist, and I have been saying that, I mean, in all conferences, that if we want to learn about the lambda 1405, we should use data of lambda 1405. And then recently, I mean, we have fantastic data. I mean, they're from Jefferson Lab, Morilla, and Schumacher on photoproduction. And then, I mean, there are other data which I will mention right now. So, I mean, I must mention, I mean, that some people have taken that into account, I mean, already, I mean, that for the K-bar interaction, that was Ruiz Roca and myself. Later, I mean, that was repeated by Maya and Maisa. And I think the next talk after me, I mean, they will also talk about, I mean, using photoproduction data. So it's catching up, and most welcome. So now, I mean, this is whatever you want to call, you know, because that's the situation. The two lambda 1405 on which everyone agrees right now, I mean, forget about the sentence. I mean, but all of us agree, you know, that there is a pole, two states. One state, I mean, that has this mass around 1405 and a width around 62 times that, 60 MeV. But the other one, the other pole is just here. I mean, you know, is the tremendous discrepancy between the different models. I mean, we most agree that the pole is below this one, and that the width is bigger. This is more or less the consensus. But I mean, apart from that, I mean, there is not much that we agree. So, I mean, and then that's another thing which is surprising. I mean, thanks to Alice Chepley, who produced this transparency, this slide, it's called this, in which, I mean, you see that the different models, I mean, I have taken a few models, I mean, give, I mean, more or less the same, I mean, results for the real part of the K-bar-N amplitude. I mean, above threshold, of course, you feed the data, but below threshold, you know, I mean, that tremendous discrepancy. And the same you can say here for the imaginary part. The imaginary part, you know, I mean, there is more or less agreement around most of the models, but below threshold, you know, the disagreements are really huge, impressive. So, I mean, we need to learn. We need to learn much more about that. And particularly to see, I mean, what happens to these amplitudes below threshold. That's the point. I mean, we navigate there. So, okay, well, anyway, I mean, how can we learn about that? I mean, information about K-bar-N below threshold, I mean, many ways, many ways. For example, one is just to use data on photonuclear reactions. That's great. Another one, I mean, for example, I mean, already this K minus deuteron going to pi sigma, that was, I mean, a reaction. And you know, I mean, there are some rescattering mechanism, which, I mean, the kaon scatters with one of the nucleons of the nucleon, loses energy, and then boom, you now already can produce the lambda 1405 because you have produced this kaon below threshold, losing energy in that collision, or here. Another one, I mean, for example, I mean, you know, there, I mean, the reaction that produces the bound state, K minus proton-proton, I mean, they are in Japan. So again, I mean, this one also, you know, you have this is more or less what happens. I mean, you collide with the kaon. Once you lose energy, and once you lose energy, you are ready, I mean, to produce there the bound state K minus proton-proton. So another one that doesn't require nucleus is this one. This is a curious reaction which was studied by Angel Ramos, our chairman in Magas. And there are no nuclei there, but I mean, what happens is, you know, they have K minus that comes here. That is Nefken's experiment, Nefken's and Prakov. You come with a K minus, but I mean, and with a proton. But the proton, I mean, radiates by 0 and loses energy. And again, you have here K minus proton with smaller energy to produce the lambda 1405. So, you know, there are methods, there are methods, but, you know, I mean, the thing is, we want to learn about K minus proton below threshold. We have to use these reactions because these are the reactions that contain information on that thing. So, fine. And then, I mean, we came with another, I mean, complementary. I mean, all these are good, they are great. We came with another one, which is complementary. Another one in reaction, I mean, which is new, proposed for the first time, which we believe will help also, I mean, to get information below threshold, complementary to the one I have told you before. And this is just, I mean, this reaction. I mean, a proton sigma going to K minus deuteron. Of course, you will do the opposite, K minus deuteron going to proton sigma. Although in GenLab, I mean, they thought about doing that, I mean, producing sigma minus, I mean, secondary beams with photons. But anyway, I mean, here, you know, I mean, you have two mechanisms. I mean, there are one which is led by kaon exchange, another one which is led by pion exchange here. One which requires here the interaction, I mean, K minus proton going to K minus proton. The other one requires K minus proton going to pi sigma. So they are complementary, the two of them. Fine, and here, I mean, you have the Feynman diagrams and, I mean, the Feynman, I mean, rules, I mean, applied there. I don't want to go into details. But only that I put here, I mean, the coupling of the deuteron to nucleus, which I call GD, around there, GD, and the theta function, I mean, I will make it cut off. Later, this is just for illustration purposes. Later, I will make connection of that to the good wave function of Mach light, right? The Born potential. Okay, now let me spend, I mean, 2 or 3 minutes, because I like that very much, to talk about triangle singularities. This is new, I mean, for you, for many of you. And, but anyway, this was fashionable. I mean, Landau introduced that, I mean, 60 or 70 years ago. But it has become very fashionable right now because, you know, among other things, I mean, some resonances which are, I mean, being invented right now, I mean, they are seen, I mean, to be triangle singularities, like the A1 1420 of compass. Now everyone agrees on that. So anyway, let me tell you, I mean, this is very, very, very interesting. It's very easy. You have this diagram here. You have this thing here. And then nothing happens. You can put, I mean, these particles on shell and nothing happens because when you integrate, then you will have always, if there are poles, you will take the principal value and the imaginary part, no problem. But, I mean, there are exceptions. And the exception is the one I'm going to tell you, which creates a singularity, which means the diagram becomes infinite. The contribution becomes infinite. And that's the triangle singularity. When that happens, well, this happens when? The 3 of particles, and I will show you that this is the case. When the 3 particles, I mean, are placed on shell simultaneously, not only that, when the particles 3 and 2, I mean, go in parallel direction, and on top of that, I mean, the particle 3 goes faster than the 2, so they can catch up with the 2 and fuse into the C particle. This is a famous, I mean, Coleman-Norton theorem, I mean, that says that this reaction will develop the triangle singularity if it can occur at the classical level. And the classical level is just that. Particle A decays into 1 and 2. Particle and 1 moves to the right, 2 moves to the left. Particle 1 decays into 2 and 3, B and 3. B goes to the right and 3 goes to the left. So 3 goes in the same direction of 2. And if 3 goes faster, it will catch up with the 2 and fuse to give the particle C. Then you have the singularity. Very easy, very intuitive, and very nice. Now, I mean, technically this is very complicated. This is Landau equations, which are technically complicated. But I can tell you, I mean, that with this collaboration with Nkungu, Chetty and Bayar, we made it very simple. I mean, pedagogical and practically much simpler. And then, I mean, all these conditions are summarized in this thing. Well, Q on is just nothing but, I mean, the on-shell particle momentum when this is the case. And QA minus is one of the two solutions that comes from here when these two particles are on-shell, which I will show you now in a moment. So, fine. Then, yeah, that's it. Very easy. You know, I mean, let me spend 1 minute here because, you know, I mean, when you do that, you do first the Q0 integration. You have D4Q integration. You do a Q0 integration analytically, and then you have this structure here. So you see, you have a cut. You have a cut here, which corresponds to placing these two particles on shell. You have another cut here, this one here, which corresponds to putting these two particles on shell. Now, the pole here is very easy. It's the one that for the decay, the momentum of one particle when, I mean, one decays into two. The other one is slightly more complicated because, I mean, to make this zero, you have an equation of second degree. But we learned to do that in high school. So, I mean, you do that, and you find now two solutions. You find two solutions, because it's a quadratic equation, and you find two solutions. So, you know, the first one, I mean, is very easy. This one, this cut here is very easy, and you get, I mean, what the formula that we always all know. I mean, Q1 is equal this thing, lambda 1/2, etc. And the second one, you have two solutions. And now, you see, it depends on that. QK, this is here, Z, 2QZ, right? I mean, this is the cosinus of the angle. Cosinus of the angle, it comes here. So the two solutions, I mean, of this equation equals 0 depend on the cosinus of the angle. But, you know, you don't have to solve it for any cosinus of the angle because you only have to solve it for when the cosinus is +1 or -1. Why? Because, you know, I mean, as I told you, if you have a pole, you have, I mean, the principal value to calculate, and the principal value is finite. However, there are exceptions. Imagine I integrate over the cosinus detector, and then I have the cosinus, the singularity comes here, you know, here. Well, do we have two branches, one that goes to infinity, one that goes to -infinity? But they will never cancel because, you know, they cannot cancel because, I mean, this is beyond the allowed region. And then you have an infinity. So this is the reason, you know, I mean, forget about Landau equations and all these things. The reason for the triangle singularity is just that, the lack of cancellation when you integrate of the cosinus on the bridge, on the edge, cosinus +1 or -1. That's simple. But then, you know, I mean, here you find out there are the solutions when you solve this second degree equation, and you have there one thing I call QA plus and QA minus, for Z equal -1 and for Z equal 1. For Z equal 1, this, I mean, is negative, and I don't want because I have to integrate over the modulus of them, so this is final. And then I have, you see this case, has no problem because of this I epsilon, and here I have these two things. So then, you see, I have to integrate now. Look at there, how the poles are. The poles are there. QA plus is there, QA minus is on there, QA plus are there, Q on, QA plus, QA minus. And then if I integrate from 0 to infinity on the Q, I mean, I can distort, if I see a situation like that, I can distort the contour, and I get a finite contribution, no problem. But there are two exceptions when I don't get a finite solution. The two exceptions are here. When these two things, I mean, QA plus and QA minus go together, because then I'm forced to go through the middle and be very, very, very close to the pole. No excuses, you will get an infinity. And the other one is when I have, I mean, the other Q on equal QA minus, I mean, that I will get also, I mean, infinity. So this is a threshold effect, I mean, that you can see from here. I mean, you can see because P2 is the momentum, the on-shell momentum that when this is at rest. So if the two solutions are, 5 minutes, okay. If the two solutions are the same, it's because P2 is equal 0. And that means we are at threshold. So this is fine. So, and the other one, I mean, is just the triangle singularity. This is a different one, is the triangle singularity. And then we have the one, Q1 minus Qn, Q minus equals 0. That's when we have the triangle singularity. Very easy to get. So, okay, then I apply that to the diagrams which I showed you there at the beginning, and then I get the triangle singularity. I get the triangle singularity, I mean, around these energies. Square root of S equal to 2,380, around there. You know, I mean, there is also the question of the width of the lambda 1405, and then, I mean, you have to take that into account. I mean, not to be not try to be too precise. But what I know is that around this thing, I will get an enhancement of the cross-section. I must also say, you know, that the triangle singularity, this infinity, is only when the width of the particle, intermediate particle, is 0. If the width is not 0, then you get a finite result, but very, very big. Okay? So fine, that's it. Then, okay, I have here the formulas, I mean, for the calculation of the cross-sections, I mean, of this reaction, and I make transitions from spin up of the proton sigma to the deuteron polarizations. And I calculate the results, and I show the results. I'll be on time, Mrs. Chairman. So, I mean, and then I have here, for example, transitions. I look here at transitions. And I see, I mean, the biggest transition is from up, going to up. A spin up of the proton and sigma, going to a spin up of the deuteron. The others are smaller. And here, I mean, these transitions which I have here, they are very small. You know, look at these numbers compared to that. They are very small, very, very small. Anyway, that's already one piece of information, which is the transition which is most favored. Second, I mean, also have here, I mean, the total. I mean, here the contribution of the high pole and the low pole. High pole was the one at 1420, the one at higher mass. And the low pole is the one at around 1380 or something like that. So the biggest contribution comes from the high pole. The other one has smaller contribution. Here, the green one. But beware, you know, I mean, there is a, you know, a destructive interference between the two of them. So then at the end, what happens is, I mean, even if one is dominant, you know, the two of them are important because the interference is just, I mean, negative. It's just a destructive interference. And that means, I mean, this reaction is also sensitive to the positions of the two poles and the properties of the two poles. So you get extra, you get a very good information because, I mean, you get information on both. So then another thing which is here is, I mean, that you get the two diagrams. I mean, the most important is diagram B. Diagram B is the one that had pion exchange. Pion is lighter, and then, I mean, you certainly, I mean, it's favored. So you see, I mean, things which are logical. And as I told you, I mean, we have, I mean, there are substitutions. I mean, this is the technical substitution to get the wave functions from Mach-Light or the Paris. I mean, we get basically the same results. And also, I mean, this something that was written there before in terms of couplings and propagators. We use now, I mean, the amplitudes which we get in the chiral unitary approach. So fine. And then, okay, this is just, and I'll be finishing on time, don't worry, Anjos. So, you know, this is very interesting because look, we have separated here the real part and the imaginary part. Here, the real part and the imaginary part of this amplitude. I have taken the most relevant transition. So, you know, I mean, the real part, I mean, peaks there, close to threshold. So it looks like we are getting the threshold singularity in the real part. And the imaginary part peaks here. We know, I told you, I mean, we should be 3,000, 2,000, 2,380 or something like that, around there. That's why it peaks. But it is not a peak, I mean, huge, because, I mean, the lambda 1405 has a width, and then, I mean, it has become a broad peak. But the broad peak, you know, with cross-sections of the order of the 20 millibar or whatever, very big cross-section, not small. So, and this is, you know, this thing was sensitive or more or less proportional to this amplitude, K minus proton going to pi plus sigma minus. So it is very curious, you know, because you might expect that because this is proportional, this, I mean, thing, amplitude is proportional to this one, it should be a mapping this, and they don't resemble at all. They don't look at all the same. And you know, this is proportional to that with other factors. The other factors are those that are responsible for the triangle singularity. But you see, they are so important, they distort completely the amplitude. This doesn't resemble at all that, at all. It has lost completely, you know, the structure that it had originally, thanks, I mean, to the structure of the triangle singularity. So there is lots of information there, new, novel information. And this is just the last transparency. So, you know, I mean, we wanted to see that it would be good to discriminate among models, because indeed, you see, I mean, we have taken a few. One is from Alex Chepley from the house. Thanks, Alex, for giving us all the information. And all the difference, and then we see, you see, we have, I mean, substantial difference, you know, differences between one model and the other. So this means, I mean, this reaction is good. The reaction is good to put constraints on the different theories, and okay, is a new thing, and I mean, I hope the Japanese, I mean, or whomever, will carry that out. Iwasaki is already, I mean, thinking about. Thank you very much. Well, we have here with the...
So time is almost up. Well, actually it's up already, but if there is some urgent questions, I will allow that.
Laura.
So, very nice result, thanks a lot. So I was wondering whether you have a K-minus deuteron wave function for us as a function of relative momentum gain.
The deuteron wave function is here, you know, I mean, let's see, when you write there a Feynman diagram, you just have the rules. I mean, you put propagators and you have, I mean, couplings, etc.,
Yeah,
etc.
but
right?
this is in momentum space
so
only.
I had that at the beginning.
You
know,
meant K minus deuteron, right?
K minus deuteron,
Not
right?
the deuteron, no, the K minus deuteron she wants.
K minus deuteron, what?
Yes.
The wave function for K
Yes.
minus deuteron.
That describes the interaction as in
K-
momentum and
For K
coordinate
minus deuteron,
space.
you know, I mean, the interaction comes here already, you know, I mean, the interaction comes, I mean, you know, I already, you know, when I have a K minus, to take into account the interaction, I will have, I mean, we have a paper with, I mean, Angel Ramos, I will let it interact with the K minus, okay? Sorry, with the nucleon and the proton. And it gives me the lambda 1405 as a first step. So that's what we have. I mean, K minus already interacts with the proton or interacts with the neutron. There are two more diagrams that I have not put. And then the interaction is there. So,
Yeah,
you
but
know,
I need the wave function really in momentum and coordinate space.
We would need the K minus deuteron elastic channel,
For example,
elastic
this would
channels,
be good.
and with that build up a wave function. We are not there yet.
Deuteron wave function I put explicitly, you know, I mean, but I mean the interaction I take the...
Angels, you understood what we need, right? Okay.
Good, okay, thank you.
Thank you. Okay. So I think we should move on. Oh, there is another question. Sure.
Hort Lenske.
Elochio, in your last transparency, not the summary, the one before, you showed these different, the sensitivity of the reaction to the models. There are a factor of 2 or more in these models, predictions. Isn't that a serious deviation from each other? Isn't that a serious spread of theoretical calculation?
Serious spread. Why is so much spread?
Because I mean the reaction is very sensitive to the model. I mean that's the point. My point is that the reaction is so, I mean, sensitive to the model that it should serve to discriminate among, I mean, different them, yeah? That mean,
Sub-threshold, right?
Yes, it's very close to threshold, yes, sure.
Okay.
Very close to threshold because, you know.
So that means you are particular.
Yeah, it was, you see,
Yeah.
I mean, it is very close to threshold is there. Threshold is just there where it begins, you know, the scale. So it's very close to threshold, the reaction, yeah. And it's very sensitive to the models, yeah.
But then you are very sensitive to the
Yeah, that's a funny thing that
the
even it's very close to
variation,
threshold, of course, I
just-
mean, but it gives information of the amplitude below. Below because, I mean, it forces the lambda 1405 to be on shell to get the singularity. And that's why it forces, I mean, to get information below threshold. Yes.
Okay, thank you very much. Let's thank the speaker again. And Aleš? Thank you, Aleš. I will, you have 15 minutes. I will, after 10 minutes, I will let you know that you have
Good afternoon to everybody. It's really a pleasure to give a talk at a nice meeting that is organized face-to-face and not online. And I will speak on the pi sigma photoproduction in the lambda 1405 region. And the work was done in collaboration with my colleague Peter Bruns and also with Maxim Maim from the Bonn University. And you can see a brief outline of my talk. And I should really thank the previous speakers also for a nice introduction to the Lambda 1405 physics and to the presentation of the various K-bar N couple channel models which we have. When you take really the models that are derived from the Carl-Lagrangian with the terms up to the NLO next to leading order level, then these models are really kind of a state of the art, and they reproduce the experimental data from K minus proton threshold up very well. So this data, as you have already, include cationic hydrogen, threshold branching ratio, and low energy cross sections. But you also seen that the different theoretical predictions we have for energies below the K bar N threshold, or which was not mentioned that much also in the Isor vector sector, represent some problems of these models, because this area is not restricted much by the experiment. But as already also pointed by the previous speaker, we have the pi sigma mass spectra in several experiments already, and I will speak about the photoproduction reaction, and this should help us in both respects. And I would also like to mention that related topics include K-bar nuclei and the role of strangeness in dense nuclear matter, which I'm sure we will hear more about at this meeting. So in the available chi minus proton reaction, the lambda 1405 is hidden below the threshold, and the resonance can be seen in processes where pi sigma rescatters in the final state, and the example of them is the photoproduction with chi plus emission. And in this two meson photoproduction reaction, the chi plus meson carries away some momentum and energy, so one can scan in the invariant mass of the pi sigma system down to its production threshold. And the formalism for our work was developed by Peter Bruns, and he put it on the archive, and later on we proceeded with calculation of the pi sigma mass spectra with this formalism, and we have just sent it to publication in PhysRFD, so we will see how the review comes, and it's already on the archive. And at the leading order chiral perturbation theory, which we use to derive the expression for the photoproduction amplitude, we can construct the all relevant term from Weinzer-Tomosawa contact terms, then the Born terms, and anomalous contribution. And in these pictures, the directed lines represent the baryons, the dashed lines pseudoscalar mesons, and the crossed circles, these symbols represent places where the photon can connect to. So, for example, in the first picture for the contact Weinzer-Tomosawa interaction, we have 5 of these photon insertions, so it in fact represents 5 different diagrams. And in total, we have 23 graphs, and they combine to form 16 independent structure functions to construct the photoproduction amplitude. But one has to also consider the final state interaction of the meson-baryon pair, and this is visualized in this figure. And so you see we have the 3 amplitude, which is represented by this M amplitude, this first vertex, and then we have the meson-baryon rescattering, and this rescatters to the pion and sigma in the final state. So we need some amplitudes to represent the T amplitude, and for this we take these couple channels K-bar N models, or pi sigma K-bar channel on models that are derived from chiral Lagrangians, and we use the models which I will specify below, and they comply with the unitarity, and our aim is implement amplitudes only is in the S wave, so we need projections on the S waves in the meson-baryon sector, and of these T graphs, and this can be done. And then we consider only the S wave. We have only 4 independent structure functions, and these are used to construct the amplitude, as the equation below the cross-section shows. And you can see also the formula for the cross-sections, which is integrated over the angle of the cone to obtain the mass spectra. So these unitarized amplitudes for this process are taken as the coupled channels vectors, when in the first term on the right-hand side you have the tree-level contribution, and then you have the contribution, the second term. It represents the final state meson baryon rescattering, and so it is composed of the tree-level photoproduction amplitude. Then in the middle, if I go from the right, in the middle you have the meson baryon loop function integral, and then you have the amplitude which is used for the meson baryon rescattering. And for the loop function integrals, you have to regularize them. And we use two different models for the k-bar n amplitudes. One of them is Bonn, which in fact or Bonn approach, which in fact is represented by three models. Two of them were published by Maximum and Ulf Meissner, and another one, which we call BW, was produced in collaboration with colleagues from Washington, so it's Bonn-Washington model, we would say. And in this model, dimensional regularization is used to regularize the loop function integral, so one has to use some mass scales for each channel separately. And similarly, in our Prague model, we also have to regularize the loop function, and this is done in the form of Yamaguchi form factors, and we use inverse ranges. And there is some relation. If one matches these loop functions as threshold, one can derive that for a natural scale of mass scale 1 GeV, it relates for pi sigma channel to something like 450-60 MeV, and for k-bar n to something like 715 MeV. Okay, this is to show you the first results we have for the mass spectra. They are calculated at the center of mass energy of 2 GeV, and we compare with the class data from 2030 by Moria et al. And in these three figures, you see only the Prague model at first. So in the top figure, you have the mass spectra for the pi 0 sigma 0 in the final state. In the second, you have pi minus sigma plus, and in the third you have pi plus sigma minus mass spectrum. And you see that when we only take Weinberg-Tomozawa contact term in our amplitudes, then this is the dotted red line, that then this contribution to the cross-section is very small or completely zero in one case. When we include also the Born terms and the anomalous term, that the cross-sections remain flat, you'd observe no peak there, but at least in the middle case for the pi minus sigma plus channel, one reaches the magnitude which is comparable with the data. But if we also add the final state interaction for the only exclusively Weinberg-Tomozawa term, it is represented by the dashed red lines, and for the complete model, which includes also the Born and anomalous term, it's represented by the blue full line. Then we see that the meson baryon rescattering is responsible for the appearance of the peak structure. And the pi sigma and the first and third figure are relatively nice. The pi sigma 0 and pi plus sigma minus spectra are reproduced rather well. And you could also notice that the Born terms move the peak to lower energies. And I would like to stress the point that it is completely parameter-free predictions. We take the amplitude as they are, so those amplitudes that fit the experimental data in a completely different physics sector, and we can do this at this energy. But now, what happens if we consider also the Born models? I told you that we have three of them, and you see that with the Born models we get quite different predictions. So it is again the case of having four different models which we tested. They reproduce the standard K minus proton reaction data very nicely, quite well. But below the thresholds, you see that we get quite different predictions. At the lower center of mass energy of 2.0 GeV, you even see that the BW model, which is the green dot dashed line, it provides you two peaks in the first figure to the left and in the second figure also to the left. So with the models, you can get either one peak or even maybe two peaks. The data so far show two peaks, one peak, but maybe there will be more precise data. I understand then on Friday we will get a new data which improve on the class experiment at least in the pi 0 sigma 0 sector, and there will be for the first time reported at this meeting. Unfortunately, we do not reproduce so well or completely overshoot the experimental data at the higher energies. But that's maybe because at that energy, the count momenta is too high in this sector. It's about 700 MeV. So our approach, which is based on the chiral symmetry, on the chiral effect perturbation theory, is not working that well. This is also to show that these models provide so different mass spectra below in the lambda 1405 regions, because the amplitudes of these models are so different. And the top, in the left, you have the real part of the amplitude, in the right, imaginary part, and the top is the pi 0 sigma 0 elastic amplitude. In the bottom is the chi minus proton elastic amplitude, and in the middle is a transition amplitude from pi 0 sigma 0 to chi minus proton. And so because these models provide very different predictions in this sector of energies, they provide so different mass spectra. The question also is, can we really manage to reduce the large magnitude of the cross-section we have seen with some models? And the answer is yes, because we can in principle modify the first loop function that connects the 3 amplitude with the meson baryon rescattering one. And we did this calculation for the Prague model in the top 2 figures for these 2 energies, and for the Bonn-Washington model in the bottom 2 figures. And you see that if we really vary the either inverse range for the Prague model or the mass scale, which is used in the renormalization of the loop function, then we can really reduce for the small values of the range, or for this renormalization scale, we can get much smaller cross sections. This page is intended to provide some comparison with earlier models. Some of them were already mentioned, and so in the first 2 by Roca, Osset, and May and Meissner, they really have some kind of a makeshift phenomenological photoproduction amplitude of that form, which is not similar to our approach, because it does not reflect the photoproduction dynamics. Then what is quite similar to our model is the model of Nakamura and Gido, but they use some non-relativistic simplification, have many additional terms, and then there is also a model by Wang and others, with which Eulogio Hosset, I think, is the co-author, and that includes or focus on the triangle contribution, which he spoke about in different processes, and also combined with other processes. But I would like to say that these 3 previous approaches all fit quite a good number of model parameters to reproduce the class data. In contrast, we just demonstrated that what can be achieved with a parameter-free approach based on utilized chiral perturbation theory. So here is my summary. We have seen that the different models provide very different predictions at subthreshold energies, and the photoproduction of pi sigma with emission of chi plus can be used to study this process's subthreshold. But to do that, one really needs to refit the models to reproduce the data well. I think we should come back and make the fit of the pi sigma k bar and couple channel models together, the pi sigma spectra of some process below the threshold with the chi minus proton reaction data. And we believe or hope that the agreement with the class experimental data, which is not satisfactory so far in our approach, quite can be improved by a combination of including the photoproduction data in the fits and also modifying the loop function, or by considering additional contribution to the photoproduction amplitude, which we do not have. Thank you for your attention.
Okay, questions? Eulogio, please.
If I understood correctly, I mean, one of the differences that you have with respect to, I mean, the work, I mean, of Roca and myself, I mean, is the fact that you put an amplitude, right? There at the beginning, you put an explicit amplitude, right? Explicit amplitude for the gamma n going to two mesons, K minus, a meson, and a baryon. At the beginning, you know, in the diagram that you have at the beginning, you show that. Next transparency. Next transparency. Next transparency. Next, this one. Stop there. You see, you have there the model M. The M there is gamma proton going to K plus a meson and B, right? And you make a model for that, correct?
This M amplitude is constructed purely from the graphs which were shown on the previous
but
transparency.
you know, I mean, there is one reason why we didn't do that. You know, I have worked, I mean, with several students with a gamma proton going to pi plus pi proton, okay?
Yeah.
And we needed 67 Feynman diagrams, I mean, for that. I didn't want to repeat the same procedure with the gamma proton going to K plus meson baryon. And I am sure you have not put the 67 diagrams. You have certainly much fewer. I mean, that the model for that is very complicated. A model for a gamma proton going to two mesons, I mean, proton is very, very complicated. And what you do is just, I mean, okay, you have chosen some diagrams. But life is more complicated than that, yeah. That's why, I mean, there, you know, I put a phenomenological amplitude. And the other reason is that I didn't need more detail because, you know, all I wanted to get is just the K bar N, I mean, parameters, I mean, leaving apart from the photo production. So in the K bar, I mean, N parameters were the same for all the energies and for all the data of photo production. So then we could afford, I mean, to put there, parameterize, I mean, the photo production amplitude and put the common information to all the data of the K bar N interaction, which was very small and common to everything. So it was not needed, you know, to be so sophisticated on the photo production amplitude. But anyway, you are welcome to improve, and what you have done is fine. But be aware, the model is very complicated, very complicated.
I believe we could include some more processes and, but.
Okay. So no more questions. Then let's thank the speaker again, and I call the Nina.
Good afternoon, everybody. Thank you. So from interaction to bound systems, I'll speak about Fourier type calculations of K-bar and an N system. So short history after prediction of bound states in anti-Coulomb nucleon systems made by Akaishi and Yamazaki. We performed a series of different three-body calculations of different systems, different states, and different reactions, in particular quasi-bound state in K-minus proton-proton system and K-bar N systems. We found that nobody quasi-bound state in K-minus proton-neutron system and proven it. We calculated near threshold scattering of K-minus neutron, and also we studied conic deuterium, which is an atomic state of the system. So in three-body sector, we did enough, I think, and we decided to move to four-body systems. We solved four-body Faddeev type equations, which can be seen there. They're written in imperative form. And here you can see U are unknown four-body operators which enter the system. There are three-body operators denoted as large T. And of course, the system includes two-body interactions, which is the only input for this system. So if we are speaking about K-bar NNN system, there are two partitions of 3+1 type, which is K-bar plus NNN and N plus K-bar N. And there is one partition of 2+2 type, which is K-bar N plus NN. This system of equations in operator form is written for separable potentials. If in addition we somehow manage to evaluate three-body amplitudes in separable form as well, it means to write down this T in this form, in general it will be a sum of these terms, then we can rewrite the equations, and the four-body equations will look like this, where there are new X and Z unknown four-body operators, transition operators, and kernel functions, or kernel operators. For these calculations, we used one-term separable K-bar N potential, two-term separable N potential, and this is the only input for our calculations. Now for the three-body amplitudes NNN, K-bar N T matrices, and also for the K-bar N plus NN T matrices, we used only one-term separable forms. And finally, when we write down this system of equations in momentum representation, we end up with system of 18 by 18 coupled equations. Now I said we need separable potentials and separable three-body amplitudes. Our potentials are separable by construction, so we need to separabilize somehow only three-body amplitudes. To do this, we used this energy-dependent pole expansion or approximation method, which was suggested by Sofianos et al., especially for Fadeev equations. It looks like this. If we have three-body Fadeev type equations in momentum basis, as it's written here, it's possible to evaluate eigenvalues, lambda, and eigenfunctions, G, of this system from this eigen equation with a normalization condition. Usually it's done when the energy of this eigen equation is fixed. And usually if there is a bound state in this system, this energy is fixed as the binding energy. But when we solve four-body equations, we need three-body amplitudes at arbitrary energies. So to do this, we first solve these eigenequations for fixed energy, and after this, from these expressions, we obtained, but not from solving the equations, but from just evaluating the integrals, we obtain energy dependence from factors and propagators, as is written here. And finally, we end up with the separable version of the separable three-body amplitudes, as written here. So this method which we used here needs only one solution of the eigenvalue equations and calculations of the integrals after this. The method is very accurate. It's accurate already with one term, and it converges quite quickly. So the input for our four-body calculations are potentials, and for these calculations I constructed new nuclear-nuclear potential, which is a two-term separable potential, which looks like this, with some form factors. Parameters of the potential were fitted to argon 18 potential phase shifts, and of course these potentials reproduce proper triplet and singlet NN scattering length, effective range, and of course the potential reproduced proper deuteron binding energy. Here you can see the phase shifts given by our new potential in comparison with our previous nuclear model, and the points are the data by argon potential. The lines are our potentials, but you see that there is almost no differences between the previous and the new nuclear potential. And during these for-body calculations, we obtained byproduct results, namely the K minus neutron-proton subsystem of the system was studied by us before, and I said that there was no quasi-bound state in it. But when I used this new nuclear potential, it was found that there is quasi-bound state in this system caused by strong interactions. I want to notice here that it's namely the state caused only by strong interactions, because there is also conic deuterium and atomic state in this system. And the main interaction for our calculations is, of course, anti-Coulomb nuclear interaction. We've heard a lot about it. And we used three our potentials constructed before for our three-body calculations. Two of them are phenomenological models. One of them has one-pole structure of lambda 1405 resonance, another has two-pole structure of lambda 1405 resonance. And the third potential which we used is chirally motivated potential, which as is usual for chiral potentials, has two-pole structure of lambda 1405 resonance. And all these three potentials with the same level of accuracy reproduce one S-level shift and width of conic hydrogen measured by Siddhartha. We did it directly without some desert type formula by inclusion co-interaction directly. All our models reproduce elastic and elastic chemist-proton cross-sections, threshold branching ratios, and have a peak near the particle data group data for lambda 1405 resonance. And speaking about four-body system, we need to say about subsystems of the system, which are three-body mainly. First of all, it's a K-bar NN subsystem with either spin 1/2 and spin 0 or 1. Both of them contributes. And these are systems, three-body systems, which were studied by us before. They usually denoted as K minus proton-proton and K minus neutron-proton. There are bound states or quasi-bound states in all these systems, and you see binding energies and width for these systems depending on the anti-Coulomb model of anti-Coulomb nuclear interaction, which we obtained. And these are data which are slightly different from those which were published, because these are calculations which were performed using only exact optical anti-Coulomb nuclear potentials. Another subsystem is, of course, three-nucleon system. Only as a spin 1/2 contributes for our four-body calculations. To describe this subsystem, we have to write down new three-body equations, solve them. We found the binding energy of this system 9.5 MeV, which is more than is known for tritium and helium-3, but it's known feature of separable nuclear potentials. And finally, there is something very special for Faddeev four-body equations, or I don't know, probably for five-body as well. It's K bar n plus Nn, which it's a system with as a spin 0, spin 1/2. It's a special system with two non-interacting pairs of particles. And in order to describe this special system, it's necessary to write down and solve once more three-body system of equations. Thank you. Here you can see the results. So I said I used three different anti-Coulomb nuclear interactions, which are written on the left-hand side, and I also used three slightly different versions of nuclear potentials, which are written above. And you see the result for binding energies and width of the K minus proton-proton-neutron or K bar 0 Newton-Newton proton system, which is K bar n with as a spin 0, spin 1/2, and total orbital momentum is equal to 0. You see that, first of all, the results in the same way as in the three-body case strongly depends on the model of anti-nuclear interaction. Especially results for the chiral model or obtained using the chiral model differs from those obtained with phenomenological models. If we have a look at different numbers obtained with different nuclear potentials, we see that the results very slightly depends on the nuclear models when we used phenomenological anti-nuclear potentials. But when we use chiral anti-nuclear potential, there is slightly more pronounced depending on the results, especially for the width of the nuclear models. Now we can compare these four-body results with our three-body results. So here are the three-body results. These left two columns for K-means proton-proton system. And if you compare them, you see that binding energies obtained with the same nuclear potentials looks very similar or are very close to those obtained with for four-body calculations. So binding energy differs, but not so drastically. But if you compare width, you see for chiral potential, for example, it's 48 MeV, and for four-body system, it's 42 or 39, depending on the nuclear potential. So it seems that if we look at the K-means proton-proton neutron four-body system as K-means proton-proton plus neutron, the additional neutron very slightly changes binding energy of the system, but it tightens the system. So the width of the four-body system is smaller than for the three-body system. Here you can see the previous results obtained for the same four-body system. And you see that they are very different. The first one was performed by Akaishi Masaki using G-matrix method. The second two are rational calculations which used some chiral potentials. And the most interesting are the last three, which are calculations which, according to the authors, were performed using the same equations, the same separabilization of the three-body amplitudes, and they even used 2-hour phenomenological potentials. But if you compare the results for the same potentials, anti-count nuclear potentials with our results, you see that the binding energies are much larger than ours. And in contrast to this, the widths are much smaller than ours. So there are some questions to these calculations. And as for another results, you see that the second variation calculations by Barnea, Gall, and others are very close to our results for chiral anti-count potentials. So that's more or less all. So the four-body calculations were performed. Binding energy and width of the K-bar n system strongly depend on anti-count nuclear potential, noticeably on nuclear potential, especially together with the chirally motivated anti-count nuclear interaction model. Binding energies obtained with different potentials are close to those for the K-means proton-proton system, calculated with the same, exactly the same anti-count and nuclear potentials. And as for the width, the four-body of the four-body states, they are smaller than the three-body width of the K-means proton-proton states. Therefore, it seems that neutron added to the K-means proton-proton system only slightly influences the binding of the system by tightens the four-body system. That's all. Thank you very much.
Are there any questions?
I'm not very surprised that you get different results depending on which parameterization you use of the K-bar N and amplitude. You know, this is, it happens always when you do FADF because the results depend on the off-shell extrapolation of the scattering amplitude. And then depending on the model that you use, the off-shell extrapolation will be different and the results will be different. So then I want to make a call, and I will make that again. You know, that there is work, I mean, which I consider very, very important by Alberto Martinez and Kanchan Kemchandani, in which they find that these off-shell, you know, contributions, which are unphysicals because nothing can depend on the off-shell extrapolation, they get cancelled by other terms, you know, which are in the same Lagrangians when you use chiral Lagrangians. The chiral Lagrangians have, I mean, three-body terms, and then these three-body terms that the same chiral Lagrangians, I mean, produce you, cancel these off-shell, I mean, contributions exactly. And then the results do not depend at the end, as they should not, they do not depend on the off-shell extrapolation. So I don't know how you can do that, I mean, but in any case, I mean, if I had to do it, when I do it, I rely upon the on-shell amplitudes because, I mean, the rest cannot give me any contribution. And then, I mean, even if one uses, I mean, less sophisticated, I mean, approaches like, I mean, the fixed center approximation, but the input is good because you only use the on-shell amplitudes, and then you get rid completely of the off-shell effects, which are fictitious. They are just completely fictitious. So anyway, I mean, there are other ways, and you can think of others, but the problem is there, and that's the reason why you have, I mean, there are so different results.
It's not a problem. It's a feature of these equations that it's correct feature. In contrast to this, putting everything by hands on shell is an approximation which is not well grounded, sorry. But I say that this depends, these results depend on the model of anti-Coulomb nuclear interaction, because this dependence is very strong. If you see how it depends on nuclear interaction, the dependence is slight. Yes. So
you will have this problem always, you know. So okay, you want to live with it, it's fine. Yeah.
Okay. I like to ask a question if there are no other questions. I don't want to. Okay. Do you have a physical? I mean, if you add a neutron into a K minus PP system. I would have expected, because of the proton-neutron interaction, which is in the deuteron channel, you would have gained energy, right? And instead, binding energy. Instead, your energy stays more or less the same. Is that because of some counterbalance by the K minus neutron interaction?
Yes, but there are two interactions: anti-Coulomb nucleon and nucleon-nucleon.
That's right.
Nucleon is much weaker. So the main role plays anti-Coulomb nuclear interaction.
In this system?
In this system. So if you add this neutron, anti-Coulomb neutron interaction, which is isospin 1 K-bar interaction, depends on the model, either very weakly attractive or even weakly repulsive.
Okay.
So
it's essentially the K minus neutron interaction that is bringing you this change of binding energy, which is essentially no change in the binding energy. Exactly. So the role of the neutron-proton interaction, the additional neutron-proton interaction is not important.
It seems that it influences this width.
Okay.
But not binding energy.
Okay, thank you. Any more questions? Okay, if not, let's thank the speaker again. minutes talking, I will tell you that there are 5 minutes left. Okay?
Okay, thank you very much. First of all, I'd like to thank organizers for giving me this opportunity to present our recent experimental result on this four-body chaotic nuclear system. This system is exactly the same covered by the previous talk, and we recently took the in-flight K- reaction data with HELIM-4 target. And today I'd like to show the lambda DN final states analysis result. And so, as already introduced, we know the K-bine interaction is strongly attractive as being zero channel. And now lambda 41.5 is widely accepted to be a quasi-band state of the K-bar and N. And as a natural extension, we can expect existence of chaotic nuclei, such as K-PP or K-PPN. And such chaotic nuclei might form a high dense matter beyond the normal nuclear density. And we are also interested in the kaon property change in nuclear medium. So this, in this sense, anti-kaon could be a unique probe for hadron nuclear physics. And for these 10 years, we worked on experimental search for K by NN, the most simplest chaotic nuclear state in JPAC E15. And finally, we published a paper to show the existence of the K-PP or K by NN state by using in-flight K interaction on helium-3 target. And we reconstruct decay particle of lambda proton to construct the invariant mass. And we see some peak structure below the mass threshold. And the important point of this experiment is exclusive measurement of all the final state particle, including one missing particle. And we cover the wide momentum transfer region. And now we'd like to go next step to search for a four-body chaotic nuclear system to investigate the mass number dependence of chaotic nuclei. And the theoretical situation is like this, and there is some calculations on 3-body system, 4-body system, and 5-body system, and they predict some range of binding energy and also width. And yeah, it, as discussed in the previous speakers, these numbers depend on the model of K by N interaction and also an N interaction. But we would like to provide some experimental constraint on this plot. And for the experimental side, there was some such experiment in 2000. And one is a stopped kaon experiment at KK and also a stopped kaon experiment at Daphne. And there was also heavy ion collision at GSI, but these results are not conclusive at that moment. And especially in the stopped kaon reaction, multi-nucleon absorption process is very severe to distinguish with bound state formation. So our approach is to use in-flight kaon reaction where we knocked out one nucleon of target nucleus, and then recoiled slow K- can be captured with residual nucleus to form chaotic nuclei. And in E15, we used helium-3 target and detected lambda P decay product. And to study a four-body system, we needed to add another neutron to the target to use helium-4, and then we can form a so-called K minus ppn system, and if it decays into lambda and d, then we can study this system in the same way with JPAC A15. And we already have some small data set which is taken as a byproduct of T77 experiment at K1.8 VR beamline. And this main motivation of this experiment was to study the lifetime of hypernuclei, but we can take the canonic nuclei data at the same time. And the detector system is almost the same as A15. We used the same cylindrical detector system composed of CDC and photoscope counter. And in addition, we put forward calorimeter to tag hypernuclear production in this Helium-4 target case. But in this talk, we just ignore this calorimeter and we use the same system as E15. We took only 3 days data, which corresponds to 6 gigakeon, and it's about 10% of the helium-3 data. But we can somehow study the lambda D and final state. And this shows the event selection. Using the cylindrical detector system, we can clearly identify pion, proton, deuteron, and we can reconstruct lambda very nicely, and we can also see clear peak of missing neutron from reconstructed lambda D missing mass. And you can see there is almost no background in lambda reconstruction, but we cannot avoid some contamination from sigma 0 DNF or sigma minus DP final state up to 20%. And then this is a observed distribution in the invariant mass of lambda P and lambda D system, and also the momentum transfer in vertical axis. And comparing to the A15 data in the left, we see very similar structure in the lambda D case with helium-4 target. And the main structure of these consisted of the structural growth threshold here, and some cosine-free kaon reaction followed by 2 nucleon absorption with remaining nucleus, and also there are some broad background distribution. For E15 case, we applied some fitting using these 3 distribution, and we did similar spectral fitting with these lambda D data. And this shows a fitting result. And if we extract only this momentum transfer region, then we can avoid the overlap with cosine-free components. Then we can clearly see structure below the threshold. And this peak structure corresponds to the binding energy about 65 MeV and a width of about 100 MeV. And the cross-section is evaluated to be about 4 microbarn. So let me comment a few points. So this binding energy is a little bit larger compared with 3-body K-bar NN case by about 20 MeV. And this is somehow consistent with some theoretical calculation, but we have large statistical error here, and also we are still evaluating the systematic error, but because we cannot determine the background shape from the data itself, the systematic errors will be probably around 10 to 20 MeV. So yeah, it's still marginal whether this discrepancy is true or not. And from the decay mode to lambda d, we can uniquely assign the isospin is to be 0. And if we assume all the constituents in the S wave, the spin parity should be 1/2 minus, and this is our most natural interpretation of the observed peak. But we cannot exclude this sigma star NN possibility with spin parity of 3/2 plus. And to study this possibility, we might have a chance to observe lambda spin asymmetry against production plane, because sigma star will be produced polarized. But the present data is statistically not enough to judge this decay asymmetry. So we would like to obtain more data with Helmholtz target. Okay. And for the future, we are now started the construction of new, larger solenoid magnet system. This human is the same size, so you can see how large the new system will be. And this system consists of superconducting solenoid magnet and 3 times longer CDC compared with previous one, to cover much larger solid acceptance. And we also enhance neutron detection efficiency by using 3-layer barrier neutron counters. And we wish to perform first experiment in Japanese fiscal year 2026 with Helmholtz target to establish this four-body chaonic nuclei with larger and higher quality data. And with this new spectrometer, we can also study lambda PN decay mode with neutron detection. Okay, let me summarize my talk. So we observed some lambda DN final state in the in-flight kaon reaction on helium-4 target as a byproduct of hypernuclear experiment. And this observed distribution is very similar to that observed in, for lambda P state in E50. And this could be a signal of four-body chaonic nuclear system. And we are now constructing a new solenoid spectrometer for further study of this system and also other chaonic nuclei, which will be covered by the talk of Dr. Yamaga on Thursday morning. And we are also seeking the way to take more data with the present CDS, because this new spectrometer construction takes some time. So that's all. Thank you for your attention.
Thank you very much. So are there any questions? Nice experimental results, by the way.
Thank you.
Okay. Okay, sorry. There is one.
Okay, congratulations for the successful finding a peak in the byproduct and test beam experiment, and which is very, very efficient as a beam time using. And I have a question about the real experiment. And the real experiment, how much events do you expect, and how much precision do you expect for the E80 or something? Anyway, the real experiment.
Yes, E80, yeah. So now we are requesting 3 weeks beam time. And with that, we will obtain about 20,000 events for lambda D decay, corresponding to this one. That means 100 times more data.
100 times. Then we can expect the error bar becomes 10% of the present one.
Yes.
That will be great.
Yeah, and we can also study the width and also some reaction form factor that might be connected to the spatial size.
Okay, good luck.
Thank you. There is another question, Abraham, please. I also want to congratulate you because these are very nice results. Okay.
Thank you. Historically, the K minus neutron, outgoing neutron reaction was suggested by Kishimoto.
Yeah.
And he did some experiment on carbon-12 that was criticized by, the results were criticized by many people. But thinking about it, what prevents you for doing this type of experiment in carbon or in heavier nuclei, but looking really for something analogously to the deuteron, to some cluster, to some particular nucleus that you consider? I think you should look into this kind of possibility, generalizing the idea of this experiment. It might work.
Yeah, so the point of this experiment is we can detect all the final particle so that to distinguish other background processes. And if we use a larger target, then that will become difficult. But still, yeah, I think we should consider to do some missing mass method with some tagging. Or yeah, thank you very much.
Okay. Thank you. Thank you very much. I think we should move on. Okay? Because there is one more talk and then the reception. So the last speaker of today. Thank you. Okay. I will give you notice. There is 5 minutes left.
Okay, thank you. Thanks organizers to providing this chance. And I would like to show you our recent works on the meson Bayes scattering and lambda 1405 in chiral-perturbation theory. So this work, this talk based on these two works. So first, the introduction. So for this lowest lying meson Bayes scattering, it's a simple process, but has a very interesting phenomena, as mentioned by previous speakers in this session. So I will go through this quickly. Here, I just want to mention that the K-bar nucleon interaction is very strong, attractive. So the chaotic nuclei is possible, and also generate the lambda 1405 resonance. So for the structure of lambda 1405 has been intensively studied. So especially for the double pole structure of lambda 1405 predicted by the chiral-interior approach. So I would like to mention that currently this discussion is already a part of PTG books. And as commented by the Meissner, this two-pole structure is QC defect, not fantasy, because chiral unitary approach has the chiral symmetry, which is the important symmetry of Lorentz QCD. So basically, the general method of chiral unitary approach is the interaction is calculated by chiral-perturbation theory order by order, and then one can solve the Schrödinger equation or beta-Salpeter equation to obtain the scattering T matrix. However, in practice, the on-cell factorization is always used to neglect the off-cell effects of potential, and also to introduce some cutoff or subtractive constant to normalize these loop functions. This will generate the cutoff dependence or model dependence. Therefore, in this work, we try to avoid these approximations or obstacles, and we tentatively proposed a renormalized framework for meson Bayes scattering. So using the time-ordered theory with the chiral covariant Lagrangians. First, we would like to show the, we want to mention that we obtained the potential and the scattering equation on equal footing. And then we also take into account off-cell effects of potential and using the subtractive renormalization to obtain the renormalized T matrix. First, we applied our model, our theory to the pion nucleon scattering at leading order, and then we extended to spring -1 sector. So here is the theoretical framework. First, I want to briefly introduce the time-ordered Poisson theory, which is simple. It's just to reexpress the Feynman integrals in a form that the connection lines is on cell. So this, in other words, that instead of propagators for the eternal lines, we use the energy denominators for intermediate state. It has some advantages. It can implicitly show the unitarity in the scattering process, and there is a one-to-one correspondence of eternal lines and also intermediate states. And the most important thing is that it can easily tell which diagrams is important or which is neglectable. So then we use the with the help of the Feynman integrations, we can obtain the time-ordered diagram rules for time-ordered diagrams. We perform the Feynman integrals and decomposition Feynman diagrams into some time-ordered diagrams. Then by matching, we can obtain this time-ordered rules. Here I give the diagram rules in TOPT. For the eternal lines, it's same as the normal it's the same as Feynman rules, and for eternal lines, mesons is 1/2 energy, and the fermion is this one, and the antifermion is this one. Here we also have the intermediate state, which is defined as a set of lines between two vertices. It gives this energy denominator. Then we can use these TOPT rules to study meson-Bragg scattering. First, the eternal interaction kernel is defined as the sum of one meson and one baryon is reducible time-ordered diagrams, and then we can use the standard power counting to organize these diagrams. Then we can solve these cup channel equations to obtain the T matrix. Here we want to mention that this Green function is written like this form, which is just given by the TOPT. We don't do any approximations in here. So then we can conclude that the potential and also scattering equation are obtained self-consistently in this framework. So first, for the leading order potential, we use this Carré-Lagrangians, which we have introduced the vector meson implicitly. Here we want to replace the traditional Wimbledon-Thomson-Roller term as the one meson exchange contributions, which has the better ultraviolet behavior, but does not change the low energy physics. So this is our time-ordered diagrams. We can calculate the potentials using the TOPT rules. After that, we can separate the potentials as two parts. One is reducible part, another one is reducible part. Then after we do this separation, our leading order T matrix, which is written like V plus VGT, can be decomposed as these three coupled equations. The good thing is we found that for the age-reducer part, this T matrix, when we take in the cutoff go to infinity, is finite. It does not introduce any divergent terms. And for the reducible terms, it's divergent. Then we use the standard subtractive renormalization scheme to obtain the renormalized T matrix. So finally, we got this equation, which is renormalized. So yes, so then we can freely to take cutoff go to infinity, and to avoid introducing the cutoff dependence or subtractive constants. Here, as an attack of our model, we first apply to the pion nucleon scattering. In this figure, we show the phase shifts. I think the red line is the non-perturbative calculations, and the blue line is the one perturbative calculations, but with vector mass extent. And the green line is the standard linear order calculations with Weinberg-Tamura terms. First, compare with the blue and green lines, we can see that it's the same as we expected. The mass extent contributions is similar as Weinberg-Tamura terms. Second, we want to say that you can see the red line is similar as the linear order perturbative calculation. This means that our non-perturbative treatment for this it's valid, and because in SU2 sector, KPT has very good convergence properties. Then we have the confidence to extend our scheme to the 3-1 sector to study the mass bias scattering. Yeah, we solve the coupled equations in the iso spin basis, and taking the off-cell effects of potential, and also using the subtractive normalization to take cutoff go to infinity, and we obtain the normalized T matrix. In our scheme, is there no free parameters needed to be fitted? So here we listed our predictions for the lambda 1405, which has 2 pole structures. And after we changing the decay constant, we found that the lower pole, the weight increase, and the high pole is decrease. And also our results, especially for the lower pole, is consistent with mice results in 2005. Here we also saw the pi sigma invariant mass distribution, invariant mass spectrum, which is consistent with experimental data. So here we give the couplings strengths for lambda 1405. In this table, we can see that 2 poles of lambda 1405 have different coupling natures. For the lower pole, it's mainly coupled to the pi sigma. And for higher poles, it's mainly coupled to K-bar nucleon. Next, we also predict the isospin scattering length. Yes. For isospin 0, we found that our result is slightly outside the allowed region, but for isospin 1, scattering length is in the allowed region. Yes. Now we also give the total cross-section for the related to K minus proton scattering. We can see that our linear order prediction for the K minus proton to pi sigma is very good and cover very well the experimental data. But our K minus proton to K minus proton or K minus proton to pi 0 lambda is slightly larger above the experimental data. So we expect that maybe this A0 and also this distributions will be killed by next linear order calculations. Up to next linear order, we will introduce one actual tree diagram which has 14 parameters to be fixed. And the T matrix up to next linear order will become a little bit complicated because we want to maintain the scattering amplitude is normalized. Therefore, the next linear order corrections should be perspectively included via this integral form equation. After we solve these equations, we can obtain the T matrix in the particle basis. And here we have to solve the 10 cup channel and describe the experimental data to fix these parameters. So this work is still in progress. So here is my summary. So we tentatively proposed a renormalized framework for measurement bias scattering using the time-ordered perturbation theory with the covariant Lagrangians. We take into account off-cell effects and also using the subtractive normalization to obtain the renormalized T matrix. So then we apply our framework to the pi nucleon scattering and also to 3-1 sect. And finally, we also obtained the 2-pole structures of lambda 1405. So the next leading order study is in progress. So thank you for your attention.
Okay, questions? You're asking a lot, eh? Your quota is almost over. No, it's okay. Please. No.
Okay, then.
It's your...
Shulei, so I don't want you not to get any attention. You want attention, so I give it to you. Then let me see, first, the on-shell factorization is very good. It's not exact, but it's very good, very, very, very good. In fact, it was proved by, you mentioned that Ulf Meissner and Oyer, they have a paper there in which, they justify it using dispersion relations. All you need is that the left-hand cut contribution is softly energy dependent. It's not that that doesn't contribute, no. As far as it is softly energy dependent, it is enough. Second is, you see, you can derive also, I have done that, in a recent paper I can show you, in which I derive, also the on-shell factorization starting from a separable potential. And I get then exactly also the on-shell factorization. So from different points of view, you see that the on-shell factorization is very good. Now, I said that because, when you do this separable potential, you can see immediately the cutoff. The cutoff that you have is nothing but the range of the interaction. It's good to see it from this perspective, the range of the interaction. And then you see one of the beautiful things from the formal point of view that your work has is that you can get rid of the cutoff, right? I know, that people want to do that to have a renormalizable theory, etc. But you see, getting rid of the cutoff, you're getting rid of one physical magnitude, which is the range of the interaction. So it is true, you get, formally a beautiful thing, but you get rid of one important information, which is the range of the interaction. The cutoff is not something you want to get rid. The cutoff is really the range of the interaction, and the interaction has definitely a range that you want to keep. So, it's what we say in Spanish, the remedy can be worse than the sickness. Okay, well, and then the other thing is, and I finish with that, is that you separate also, it is a time perturbation theory, the row meson, well, the vector meson going to right, the vector meson going to the left, these two things, Yes. You see, in chiral Lagrangians, you don't do that, In chiral Lagrangians, you have there the meson propagator, it is 1 over q square minus m square, and q square is thrown to 0 in the chiral Lagrangians. The chiral Lagrangians obtained from this, using that, in the limit when q square is going to 0. So then it doesn't, formally I can understand, but it doesn't help very much, to make this separation when you are going to make q square equals 0 at the end.
You mean the diagram
the first,
A and B,
diagram
right?
A and B, yeah. A and B,
because we follow the time ordered perpendicular.
Yeah, sure, but
so that's why I separated
the question, the thing I would ask you is it really worth doing it? I know formally it's very beautiful, but in practice, is it really worth doing it?
Yeah, but in the, this is the leading order. This is no problem because these two diagrams have been included. But for the one loop calculations, you will decompose one loop as two diagrams. One is in this direction, another one is Z diagram. The Z diagram is higher order. We will remove it.
You remove it. So the Liebman-Zwinger equation, it looks very similar to a Liebman-Zwinger type of approach.
Yeah.
Here you have it. Okay, more questions? No? So we finish the session here. Let's thank all the speakers. Are there any announcements by the organizations? No? Okay, let's go out and start eating and drinking, suppose.